Yeah, first of all, thanks so much for the organizers to for setting up the Zoom connection. So I was supposed to fly to Stockholm, but then my flight got canceled along with a lot of other flights, and then things didn't work out. So I'm really sad to not be there, but happy that the Zoom connection worked out. So yeah, so I was asked to talk a little bit about foundation models and experiments. I saw Anna already talked a bit about them, so but maybe I can also add a little bit of perspective, also what's going on inside of the large LHC collaborations. And so I will maybe start with why I think foundation models have a good chance of being realized in particle physics, because or in fundamental physics in general, because we're in a very good kind of environment to do modern, AI. In these frontier sciences, where we have these very large experiments, we are basically in a ideal environment for modern AI. Not only do we have a lot of data, so everybody knows we need a lot of data to do machine learning. And so, for example, the Large Hadron Collider collected over an exabyte of data, which is much more than what language model companies have to train their language models. But also the data is not just from random data that we have, but it's extremely high quality data that comes from our simulators, which provides us labeled data that we can train on. And so these simulators are very, very good. And so in a way, we have the most optimal data to do machine learning, and so we should be using it. And I think it shows in the way that we use machine learning. And so when you talk about foundation models, another kind of interesting idea is maybe that there's a kind of natural conceptual alignment on what people think a foundation model is and what we've been doing in particle physics for a long time. So this is from a paper we wrote with Matthias and Nicole on kind of exploring or pointing out a close similarity between kind of the usual foundation model language and what we do in particle physics. So when you hear about foundation models, you often see this picture on the left-hand side. So on the left, you have multimodal data. So you have text and images and speech and structured data and so on. And the idea is that this goes all into one big foundation model. And the idea of the foundation model is to convert this raw data into some kind of useful representation that then can be used for many downstream tasks like question answering, sentiment analysis, and so on. And so this is the cartoon that you see, and on the right-hand side, you see what we're doing in particle physics, and it's essentially the same picture. So on the left-hand side, we have multimodal data. So we have our muon system, we have our hadronic calorimeter, we have our electromagnetic calorimeter, our tracking data, and so on. And then we have software that somehow uses the raw data and embeds this into, or converts it into a useful representation of the data. So we don't call this a latent representation, but we call this reconstructed objects. And then this representation of the raw data is very useful for many downstream tasks, like looking for supersymmetry and or looking, doing precision measurements for the standard model. And so it's exactly the same thing. So we have a kind of backbone, which sometimes is called foundation models. In particle physics, we call reconstruction. And then we have a task-dependent head of this network, which might be a neural network, or in our case, might be the physics analysis. And so the only difference between kind of this basically same picture is that our foundation model reconstruction is not a neural network. It's not differentiable, not fine-tunable, and possibly suboptimal. But we can exploit this very close alignment to maybe move towards neural foundation models and do better and do more things with such a neural foundation model. And so I think the trend basically has been to move towards this foundation model in the sense that when we have reconstruction, and it's kind of like a complicated, graph of possible, algorithms. Some are neural networks, and some are classical algorithms like the Kalman filter, and so on. And the kind of general trend has been to move to bigger and bigger pieces in this, in neural network pieces in this reconstruction. So, and the endpoint might be that this just becomes a big neural network that just does reconstruction for us. And so we've seen basically proto foundation models, mostly in the area of jet tagging. So on the lower part of the slide, you see the GN3 architectures of flavor tagging architecture of the Atlas experiment. And you already see kind of the same type of picture where you have lots of raw data with multiple modalities. It goes all into one big transformer, and then it can do many tasks like vertexing and PT regression, jet flavor prediction, and so on. And so this approach has been really influential and then pushing the performance of heavy flavor performance both in Atlas and CMS, as you see on the right hand side, and it's all going up. And we're all asking our question, okay, how much more, how much longer can this go on? And so if you think about how much there's to gain, I think, one of the inspirations is that if you go to these end-to-end neural network architectures, we know that AI can definitely somewhat transform the data into these latent representations in ways that outperform human capabilities. So if you, for example, have a vision foundation model, the neural network will basically find its own types of vocabulary to describe the data in terms of edge detection and texture detection and high level, whatever animal type detection, and use these representations to achieve superhuman performance. And so, if you compare this to the reconstruction analogy, nobody will write like a flappy ear algorithm by hand in order to do computer vision, but it's all learned end to end with neural networks, and there's has been lots to gain in computer vision. And so maybe this the same is true also for particle physics. And so the trend has been to go to bigger neural networks and not do too many smart things. And this has been kind of summarized by this influential essay by Rich Sutton, which is The Bitter Lesson, where he has this quote that researchers seek to leverage their human knowledge of the domain, but the only thing that matters in the long run is the leveraging of computation and things that scale. And so there are many examples in the AI researchers' related learning of this bitter lesson. And so this is the idea that, if you have enough compute, enough GPUs and enough data, you can train these end-to-end models, and they will be better than what humans will do when they try to kind of by hand implement such a backbone for vision tasks or maybe also for particle physics tasks. And so this type of kind of belief that bigger is better, that more scale helps, is not kind of like a hand wavy, vague statement. So of course we all know that a lot of data is good for machine learning. But what's kind of interesting, what happened, roughly 5 years ago, that this became very, very concrete in the sense that it became predictable. And so, researchers found these scaling laws, where they found out that these large neural networks, when you have a billion or 10 billion or 100 billion parameters, they behave basically like very large complex systems like thermodynamics and spin glasses and so on. And there are various analogies on, you can think of the weights of the neural networks as molecules and so on. And the same way that in thermodynamics, you have a complex system with lots of degrees of freedom, but then very simple laws appear. It's the same thing that with neural networks with lots of neurons, very simple laws appears on how the performance scales with more data and more model parameters. And these are called the scaling laws, and they're very simple power laws. If you have more data, you reduce the loss, you improve the performance with some kind of power exponent. And the same is true if you go to bigger neural networks. And then if you go to infinitely large neural networks and infinitely large data, you achieve this asymptotic, floor, that is given by information theory. Okay, so you cannot go to zero loss, but you can, achieve maybe this asymptotic Bayesian limit. Okay, and so if you think about kind of our starting point, that we're in a very good situation for AI in fundamental physics, especially in particle physics, it's really confusing that even though we have more data than the large frontier labs, our state-of-the-art biggest neural networks that we deploy in the experiments are kind of tiny compared to this, right? So we have an exabyte of data, which is more what than frontier companies have. But our biggest neural networks are 10 million parameters, while ChatGPT, trained on maybe petabytes of data, has a trillion parameters. And so we are many, many orders of magnitudes below kind of the state of the art in, frontier AI labs. And but part of the reason is we're not using all of the data to train our models, right? So we have, trillions and trillions of jets, for example, for flavor tagging. But we're training maybe on 100 million jets. And so one of the questions we've been thinking about a lot in the last year or so is, what happens if we embrace this bitter lesson and just try to go big and scale, the biggest neural networks that we have in particle physics to go even bigger. And so, one of the answers of this, why are we using such small neural networks could actually be, that there's a kind of like a bitter lesson in particle physics, because we've already kind of exploited everything there is to exploit, and there's no point of going to bigger neural networks, right? So, yes, the performance becomes better if you go to bigger data sets and model complexities, as the scaling law says. But if you're close to this asymptotic limit, this E here, you're entering a limit of diminishing returns. And so then it doesn't matter, like no fancy AI and machine learning will save you. There's just nothing to be gained because you're already hitting the core resolution limit of the detector. So that's a possibility. And so the exciting thing that happened in the last year is that we can, answer this question because we discovered recently that the same scaling laws appear to hold also in particle physics data. So we've converged on using, transformer architectures and so on very heavily in the especially jet tagging community. And because we use transformers and we use a lot of data, it's maybe not so surprising that these scaling laws also hold in not only in language data and vision data, but also in particle physics data. And we see all the usual markers of large-scale neural networks. So on the left-hand side, it's a paper we wrote on kind of discovering this double descent phenomenon that, if you go to very big models, you stop overfitting, and then you, improve again, after overfitting. We see the standard scaling laws both for boosted jets and in the middle, and also for small radius jets. This is a paper from Atlas. And so because the scaling laws now hold, or seem to hold, we can now make predictions on how good neural networks will become if we train on 10 times more data, 100 times more data, 1,000 times more data, and so on. And we can actually test this with the large-scale data sets that we have available inside of the experiments. So, the good news is we're absolutely not in the situation where we are in the limit of diminishing returns. It seems we're much, much more in this blue area of the untapped potential. Because basically what we found out when, looking at very large-scale data in the experiment, there's still lots to gain. And so I will go through these plots a little bit carefully. So on the left-hand side, you see the scaling law for the performance of flavor tagging as a function of the data set size. On the, notice this is a logarithmic scale. So you have 100,000 jets, 1 million jets, 10 million jets, 100 million jets, 1 billion jets, 10 billion jets, 100 billion jets, and so on. And the data points show you kind of, the performance in terms of the loss function that we use to train the neural network as we go to more and more data. And so it's not only going down, but you see it's going down extremely regularly and, very, very closely following a type of power law that we can fit. And so if you think this is a good fit to the data, then you might also, be convinced that you can trust the continuation of this curve for quite some time. And the first thing to kind of notice here is that it's going to continue going down. So if we train on a billion jets, on 10 billion jets, 100 billion jets, we kind of can predict what performance we expect. And so what was very exciting, because in the experiments we have lots of data, we can actually go to the scale and test it. And so this is exactly what happened. So we went to a 10 billion jet data set, which is 1.5 orders of magnitudes above kind of the previously biggest data sets in particle physics. And we can just test the performance, and the result you see on the right-hand side. And so no surprise that the scaling law holds. And on the right-hand side, you kind of see what this means in terms of physics performance. So on the physics performance, we have the same y-axis, the loss function, but on the x-axis, we translate this into background rejection. And so now you can see that first of all, our 10 billion jet or 8 billion jet data set lies exactly on kind of our fitted curve. And then you can now also see, okay, how can you translate this loss function in terms of in kind of physics performance like background rejection? It's a fixed flavor tagging, heavy flavor efficiency. And so now you can see on the right-hand side, if you go to bigger and bigger data set sizes, let's say 20 billion, a trillion jets, and so on, you can go further and further right on the background rejection, and so you can get better and better physics performance. And in principle, this tells us that maybe there are one or two orders of magnitudes to gain in background rejection, because this is also a logarithmic axis, if we scale our neural networks, to be very, very big. And for COMETA, this is of course very interesting because if you're interested in Dye-Higgs and so on, especially if the 4B final state, B tagging is extremely important and kind of gets converted into hundreds of millions of dollars, because you can maybe achieve the same types of limits with fewer data. Okay, so there's lots of, we're very far from the limit of what we can do with machine learning, and we should go big and go towards foundation models, in the near future. So there's one caveat. So I trust this as a machine learning result very much, because you see that the fit is just very, very good. But the main question, and now lots of people are excited about or are questioning, is, okay, does it hold as a physics result? And so there is this possibility that we've seen machine learning systems exploit environments in a way to kind of achieve some goal, like playing kind of like a computer game, not kind of along the spirit of the game, but just in a way that wins the game, very, very often. And so it might be that now, yes, the performance scales because it's exploiting some detail in the part-time shower simulation or the handling of heavy flavor and so on. And this we don't know. How would this show up? Is if we actually calibrate these jet neural networks and see and compare the efficiency in simulation and efficiency in data. If there's a gap opening up, we see that it's exploiting some dirty secrets in the simulation. If it doesn't open up too badly, then this is actual performance, that we can use in physics. And so the only way to, understand which of these two options is happening is to actually go to these large-scale data, go to, create data sets with 10 billion jets, 100 billion jets, and so on, and just test it and calibrate it and see where we are. There's also kind of like interesting detail that maybe this is also as it's a return of the experiment in some ways. A lot of machine learning work is driven outside of the LHC collaborations because very often it's R&D related and it's very fast and so on. But when we look at the scaling laws, so on the left-hand side is the Atlas plot, and the right-hand side is a kind of follow-up paper we wrote on public Delphis simulations, and there are some related papers associated with this as well. And we see that the scaling law is much kind of more favorable inside of the experiments than on Delphis simulations. So the experiments use full-scale GN simulation, and also the experiments are the only ones that really have 10 billion jets or 100 billion jets or a trillion jets. And so maybe kind of in the future, when we really want to go these large-scale neural networks with billions of parameters, the experiments are the only place we can do this. So this might be kind of like an interesting shift in the dynamics of how machine learning research is done in particle physics. Okay, so as consequences, then we need to think about three things. It's, I think, possible that we basically move towards a new scaling era of machine learning and high energy physics, similar to what happened to language models a few years ago. And so now we need to think about what to train and how to use the models that we train, and then how to get more data. And so a lot of these answers to these questions can be kind of inspired by the machine learning community practices that they showed us what they did with language models, and maybe we can do the same thing in particle physics. And so One of the ideas, okay, if you're going to go very, very big and, train models that have billions of parameters and, costs millions of GPU hours to train, we really want to have a model that has a type of general knowledge, like a foundation model that goes beyond, individual jets, and, understands particle physics in a kind of more all-encompassing way. And so the question is, how do you build such general knowledge? So the way that this has been done in language models is to do kind of either fill in the blank tasks or association games. And so on the left-hand side, I adapted a slide actually to say Stockholm, but somehow I mixed up the slide maybe. So sorry about this. So the idea is if you have language, you can create puzzles synthetically in order to present the neural network with different puzzles. So you have like some kind of sentence, and you can mask out some words, and then you can ask it to fill in the blanks. And the idea is that if you can do this for any language, for any topic, in any type of mask configuration, the only way to achieve this is if you build general knowledge and how about the world that you're operating in. And you can do the same thing with fill in the blanks for images. So you rip out some pixel patches and you try to fill this back in. You can also try to play a bit like memory you did as a child. You have like some image and you're trying to associate, okay, given, maybe randomly rotated versions of the image, or you're presented with a panel of images and you're supposed to kind of pick which one is the similar image and which ones are unrelated images. And so if you can do this for all images, in any orientation and so on, the idea is that you build general knowledge. And so this can also be done in particle physics. And so especially we can use the language model analogy. So we can do this, what's called in German Lückentext. So you have this text with masked out models, masked out words. And so the analogy that you can drive here is that you can think of our simulation pipeline and our reconstruction pipeline as a type of narrative of what is happening in the detector. So you can start with, like the truth particles, like a proton, electron, positron, like a neutron and a photon, blah, blah, blah. And then in the simulation, they become individual hits, then they become tracks, then they become calorimeter cells, calorimeter clusters, and then finally maybe jets. And so it's kind of like a paragraph of what happens in the event. And once you have this paragraph and you turn, particle physics data into language, you can then just train fill in the blank models on this type of text. And so this is something that's called massively multimodal mass modeling approaches. And it's a paper we're still working on this and hoping to release it very soon. That shows that you can do this on kind of low-level detector data that combines multiple types of modalities. And this works very well. So you can then, by kind of adapting the masks, into different prompts, you can use the same model to do different tasks. So imagine you have like a sentence, but only the truth particles are presented, and then everything else is masked. And then you ask the model to fill in the blank. This is nothing else than just asking it to simulate the truth particles, and the model will do it. Or on the right-hand side, you can do something like particle flow, which in this language is you have the sentence and everything is presented to you, like the tracks and the calorimeter cells and the calorimeter clusters, and then you ask it to fill in the blank, which is the truth particles, right? And this is reconstruction. And so by training the model once on this fill in the blank task, you can imagine that by adjusting at inference time which blank to use, this is, like the same model can perform many tasks in the same way. And so this interestingly beats handwritten physics-informed particle flow models and kind of points towards this better lesson. An open question is maybe what type of pre-training strategies to use. And so there's fill in the blank. There's also next token prediction that Anna talked about. But there are also, other physics-inspired self-supervised learning architectures. And so which puzzle to use in order to kind of build this general knowledge is, I think, still an open question. So I think, on this kind of more language-inspired side, the first one was NPM, and then we had OmniJet Alpha, where we kind of see, that this type of very physics uninspired pre-training task also works. and there's a nice comparison paper between the two. And then on the right-hand side, you see, you might imagine, okay, if you want to scale to very large models and jets, want to have things like infrared safety and so on. And there are self-supervised learning tasks that somehow encode this as an inductive bias as well. And so, yes, we might go to large-scale self-supervised training, and in a way kind of go to the bitter lesson, but it doesn't mean that we need to throw away all the physics understanding we have in the world. And then in terms of how we use these models, so one exciting application is that we can then, because now the reconstruction, like our backbone became a neural network, it's fine-tunable, and then you can kind of adapt your reconstruction the same way a graduate student would adapt like the working points and so on, but automatically to your signal. And so this is also kind of related to COMETA on this right-hand side in the paper where we did this comparison between foundation models and particle physics. We show that if you do end-to-end optimization and fine-tuning onto your final, analysis signal, you can achieve, or gain a lot of background rejection by just fine-tuning your reconstruction by not just taking the reconstruction that is given to you, but adapting it automatically with gradient descent to your specific signal. And so this is only possible thanks to the differentiable and kind of adaptable nature of neural networks. And it's one of the new things you can do with the foundation model that you couldn't do with the kind of, C++ reconstruction code. And what's even more is like with neural networks, you can then also kind of actually go into the neural network and access these high-dimensional latent representations, and you can gain even more if you somehow, open up the neural network and pass around these vector representations instead of maybe the physics-inspired representations. And so this works even better. It's part of this comparison that we did. But here, one of the main important questions is how do we calibrate and interpret these high-dimensional latent representations? And there's a nice paper by Francesco and Chris and Tobias and Malte on how to calibrate high-dimensional representations. Okay, so the last minutes I will maybe quickly talk about simulation. So if we go to this future of trillions of examples, actually, we might be running out of data very briefly after discovering that we can use all of this data in terms of that things scale. And so simulation is kind of the key to our AI utopia future. But one of the problems is that it's just super expensive to run because the way that we simulate with Giant is that we do this iterative simulation of simulating individual quantum transitions. And so we can get inspired by AlphaFold and language models on how to maybe go further than this. And so the AlphaFold moment basically taught us that we should find a central problem that then kind of can unlock many use cases simultaneously. And in particle physics, I'm convinced this is basically radiation matter simulation because all of the experiments use this independent of what they're doing. And from language, we can learn how to improve simulation. There's been a lot of progress over the last 10 years on using generative AI to simulate detector responses. But the problem is that all of these neural networks are not adaptable in this sense. So yes, we can train a fast simulation for Atlas, but this fast simulation is not usable for CMS. While Giant I can use for Atlas and I can use out of the box for CMS. And so the question is, okay, how can we create a universal HEP AI surrogate model maybe? One of the ideas could be is, instead of doing kind of very atomic individual transitions with a very basic vocabulary, you can kind of figure out how to do next word prediction similar to what language models do, where you do bigger chunks. And so I'll go through this very quickly. This is our ERC project that we just started, where we basically try to find a next particle prediction model where like a particle comes in, it gets presented some piece of material, and then it just instead of doing individual transitions like Giant, it can do in a single shot the next particles that come out of this volume. And the idea is that if you train this once, you can compose new detectors out of these building blocks, and you can simulate them with these surrogate models without retraining the neural network at all. And so it becomes kind of a zero-shot generalizer. So I'll just show animation here where you can see, okay, the material distribution changes, but the neural network and GAN still agree very well while you're changing the material distribution. Okay, so I'll close with the summary, and I'll let you read this, and I'm happy to answer some questions.
Thanks so much, Lucas. It was a great talk, very comprehensive, impressive results. So we have time for a couple of questions. I see Marco.
Yeah. Hi, Lucas. It's Marco from Genova. So thank you for your talk. So I have a question which also applies to the talk given by Anna yesterday. So beyond, what do you think? So beyond the downstream tasks, do you think there is a sensible way to evaluate the, let's say, representation that the foundation models learned, or like, yeah, in a more abstract sense, maybe in terms of information theory or something like this?
Yeah, so I think there could be some ways to do it. Like, for example, I mean, let's say if you embed all of the data into like some kind of latent space. I mean, the way that, I mean, you can get inspired, like if you take this analogy seriously, you know, that's like reconstructions are foundation models, like we know how reconstruction works, or like what we like about our reconstruction. And part of the reason is that also on the reconstruction side, we have like some kind of compositionality, you know, where it's, you know, we have like an electron container and a jet container and so on, and we know there's a kind of well-known operation of adding electron to the electron jet container. And so I think, you know, you could start trying to maybe analyze these latent representations to see whether or not they have like this compositionality, or, you know, disentangled representations where they maybe kind of save like all the, you know, track related data or all the charged particle related data in one part of the latent representation, and then you know, store some of the other information in another part of the latent representation. And so I think it's possible because it's been done in language, and I think this is this slide, right? So once you have like such a foundation model, like you can, there are techniques on how to analyze what it learns, like what it's sensitive to. Like, you know, CNNs, you know that the early layers are kind of edge detectors, and then the later layers are texture detectors. And so there's this kind of technique called you know, neural circuits that we could use. And so, yeah, I think there's lots of things to go. Now that we are entering the scaling regime, I think, you know, we can just learn a lot from what the other fields did in terms of how to analyze this data, because we're basically using the same neural network, and so it becomes very standardized. And yeah, so I think it's a very interesting question. We should try to study this.
Thank you.
Arno?
Yeah, so the question from Pietro on Zoom. So in slide 13, you show the trend of the loss functions, but you don't show how the performance of physics behaves. So one, did you check the performance in terms of physics quantities, energy resolution? And two, if this is the case, knowing the ground truths, one may think of calculating what's the actual ideal limit. Did you check how far the current algorithm are from that?
Sorry, that was a lot. So I didn't catch everything. So, okay, I caught the first part that we show the trend, but we don't show the physics performance. So I think this is what we tried with this tint plot, where basically we see this, I mean, yes, so I think this was the first question we asked. Okay, we see the losses going down, but like, what does it mean in terms of physics performance? And here on the right-hand side, you see this translation. So there's a one-to-one relationship between the loss and the physics performance. And I think here you see the translation where you have one loss value, but then you have 1, 2, 3, 4, 5 background rejection performance values, and then I think you can kind of make this translation. So the idea is you can go here, look up for the data set size, what type of loss do you expect, then you go to this loss, and then you can map this to background rejections, or you can do this on the right-hand side. And so then I didn't catch the second half.
So knowing the ground truths, one may think of calculating what's the actual ideal limit. Did you check how far the current algorithm are from that?
Well, yeah, so I mean, or maybe I'm not understanding the question, but yes, I think, so we know, or well, I think it's not so easy to know what the ideal algorithm is because well, it's limited by the detector resolution. But we can kind of run the fit here, and you can fit the asymptotic limit here, and so we get a value which is like this thing. And so the way that you can see how far out we away is, I mean, so with the 10 billion data set, we're at this background rejection, and the ideal background rejection that we can get this here. But this is a result from the scaling law of fit. There's an interesting plot in this neural boosted jet paper, this middle paper here, where we can analyze or we analyze how this asymptotic floor moves if you go to lower level data. So you see if you just use, let's say, kinematic information for the constituents, the floor is very high because you're in a way, you know, handicapping your pattern recognition ability. And if you add more and more features about the constituents, you can push the floor down in a very controlled way. And then, you know, if you go to all the possible detector features, this is the lowest you can push this. And so we did some experiments inside of this neural boosted JTAG paper that I think show that we have at least a little bit of control on how to think about this asymptotic limit.
Okay. I think we probably... there's a last one.
Yeah, I have a question, from Menkai, University of Siegen. It's pretty general, and it refers to at least two topics from your presentation. So you mentioned the scaling law, then you mentioned also the framework for simulation, general simulation. And I wanted to ask how we should perceive rare processes in this context, because I'm kind of worried that once we can achieve this level of generality, we might lose something which is super rare and which is not really captured by our experiments yet, because we don't have enough data, for example. But once we collect more data, we might be able to see these processes.
Yeah, so I think it's a super interesting question, and I don't have a good answer, except we have to try and then just observe. I mean, so I think we will first arrive at these large-scale reconstruction level frameworks, and before we arrive at, you know, like super general simulation foundation models, so I think we're not changing both things at the same time. So my expectation is we will start testing these scaling laws with like true Jan simulation. Okay, so that's good. And so I think what we will need to see is whether or not kind of this calibration gap opens up, which you know, maybe one of the reasons could be there are some processes missing, or some processes are mismodeled, and so on. There might be many reasons. And so you should see this in the calibration, which is ongoing right now. But I think the only way to see this is to actually train the models at the scale and calibrate them, and then, okay, maybe it will fail, and then we'll be sad, or it will work, and then it's fine. But yeah, I'm worried about the same thing, and what we need to test.
Thanks. Okay, so let's thank Lucas again.
Thank you for
We'll move to the next talk of the session. Jay, who is here, who's going to talk about the next very trendy argument these days, simulation-based inference.
Okay, hello everyone. I'm Jay, and I'm a postdoc at the University of Wisconsin-Madison. First of all, I apologize for my voice. I've been recovering from a cold infection. I hope I'm still audible. If not, please let me know. Okay, so I'm going to be talking about simulation-based inference. We've been hearing a lot about foundation models in this workshop, which are cool and they look towards the future, but I'm going to be talking about something that's much more low-hanging, just as exciting. So yeah, so before we get started, let's see how we build a statistical model at the LHC. Because if we want to do statistical inference, the first thing that we need to do is build a statistical model, which tells a story of how we, of our physics model. So you could take any physics model of your liking. It could be the standard model, the beyond the standard model. And let's say you're interested in measuring some quantity, some parameter of this model. It could be the mass of a particle in a certain topology, or it could be a cross-section, it could be a coupling strength, etc., etc. The idea is that for a given value of the parameter, you have a probability distribution. Because we are using quantum mechanics, you have a whole probability distribution of how a certain final state is distributed over the entire phase space. So let's say you have 4 particles in your final state. So you have 4 momenta corresponding to each of these particles. And this spans like a 16-dimensional space. And you model the output probability distribution of the 16-dimensional space. Of course, reality is much more messy. So this is not what you observe in your experiments. What you observe is that these final states, these partonic final states, they then undergo something called parton showering. So now you had this 16-dimensional space, nice and easy. It can be calculated by perturbative calculations, but now it evolves into much more higher dimensional final state that is much difficult to approximate using exact analytical formula. So you have another probability distribution of this latent space, which we call C prime, given some value of the final state C. Again, each of these particles in this very high dimensional space then undergoes detector interactions, and you have another probability distribution, C prime prime, and this is again super high dimensional and very difficult to model. So we have a combination of stochastic and physical ways to handle this kind of thing. And then finally, we reach what Lucas was showing. We have like this 100 million dimensional sensory output, which we call X here. And given some intermediate final state C prime prime, we have our probability distribution for this X. And now we have increased the dimensionality all the way from 16 dimensions here in this latent space to 100 million dimensions. So needless to say, this is a very complex probability density function, which is our statistical model that we set out to measure. Now, because all of these latent space are not directly observable and we don't care about a lot of them, what we need to do is we need to marginalize over this entire high dimensional space. So these are probability distributions. So for a given C, you could have any number of C prime according to some probability distribution. So you have to integrate out over all possible latent space. And this is a huge high dimensional integration. It's not possible to compute analytically. So what we instead do is we build a simulation model. So when you have large dimensional integrations, Monte Carlo techniques are your friend. And we build this very sophisticated simulation algorithms over many, many decades. And what we now have is a simulation probability model and something called an implicit model, which is the sense that while you can sample a lot of events from this probability distribution, you cannot exactly compute the probability, the exact form of the probability. But this has been the problem since the beginning of the LHC. So haven't we always been using SPI? I mean, this plot here shows clearly that you have simulations for, Higgs, you have simulations for the background, and you see this nice resonance peaking out with data points available. So isn't that simulation-based inference? In fact, yes. So let's take a look at what traditional inference does. So we have this raw 100 million dimensional output, super difficult to model. So the first thing we do is we reconstruct the exact physical objects from this high dimensional output, and we're going to call these 10 to 100 dimensional vector, which is the collection of this physics object and their momenta, as X. And now we have our likelihood model, which looks something like this. This is common across LHC analysis. So you have a term that computes the total expected event rate, compares that to the observed rate. So lambda here is the expected number of events, and here is the observed number of events. And you have this probability density term, which, as I was saying, is the intractable part. It's difficult to compute. And because you have nuisance parameters, so mu are the parameters of interest that you want to measure, but you also have a lot of nuisance parameters. And to constrain this nuisance parameter, we perform auxiliary measurements. So there's also this constraint term here. And yeah, so this is the form of the likelihood function. But of course, we want to measure this probability density, which is intractable, P of X given mu nu. So how do we do this? Traditionally, what we do is we rewrite this probability density function, this likelihood function. Instead of using x in the probability, we use s of x, where s of x is some function of x that reduces the dimensionality significantly. So instead of having like some 16-dimensional 4 momenta of 4 leptons, we could, for example, just build an invariant mass of this 4-lepton system. And now we write the likelihood formalism in terms of this s of x here. Why do we do this? Because we like histograms. Histograms are amazing density estimators. They're super simple to compute. All you do is count the number of events in each bin. You're done. You have estimated probability. And histograms, of course, are great, but they only work for a small number of dimensions, usually 1 to 3, because as you increase the dimensionality of the histogram, the number of simulations that you require to fill in each bin grows exponentially. But all in all, to say is that we have a histogram estimator, which I'm calling QHist, which is a histogram estimator of P of S of X. And all it does is it discretizes the continuous probability distribution into a discrete one. And now we have our probability distribution. So this is what we have been doing all along. And this is super clever. And this is the familiar form of a product over bin Poisson likelihoods that you're familiar with. This is exactly equivalent to what I've been showing here, which is the full probability, full likelihood model of using some S of X. So the nice thing about this is that it's easy, cheap density estimation. But the con is that you lose sensitive information because now you have this 16-dimensional space that you have reduced into a single-dimensional summary. So what about, for example, we model M for L, but what if there's more information in PT for L or eta for L or anything else? So we lose this. And of course, one thing to note here is that we still have the challenge of modeling this continuous expected rate for each bin, which is not easy because our nuisance parameter dimensions are huge. So we could have like a 100-dimensional nuisance parameter space. And we could model lambda as a function of mu and nu by simulating each time. But as I showed you, simulation is long and expensive. And it's impossible to do every time. So what we instead do is we use something called a history model. So we simulate so we find independent x's in the nuisance parameter space. We simulate for each nuisance parameter an up and a down variation. And then we morph the histograms. So you have a down variation, you have an up variation, and you morph the histograms to form a continuous model. Another assumption we make is that each of these, the impact from each of these nuisance parameters factorize. So I'll get into this in more detail later, but together with these dimensionality reduction, histogram estimation, and this kind of parametric ansatz that interpolates between bins, you have your full traditional analysis. Cool. So why use neural SBI? Because as I said, we are losing high dimensional information. What if we want to model the full probability density without doing x to s of x? What if we want to use the full 16-dimensional vector of a 4-lepton system, for example? The problem is that you cannot build a histogram. As I was saying, it's something called the curse of dimensionality. As you grow in number of dimensions, the number of simulations required to grows exponentially. So histograms are a no-go. So what do? Well, that's where neural simulation-based inference comes in. Because neural networks can also be excellent density estimators. But the nice thing about neural networks is that they work really well with high-dimensional data. They don't need as many simulations. They are smooth, they are continuous, they are differentiable. They can they can interpolate between 2 points very, very well, unlike histograms. So this was first proposed in these MadMiner papers. So the idea is super simple. So you have some parameters of your model, here they call it theta, and you have some simulators here that take as input these parameters and give you some observables. Now the neural network sees both observables and parameters, and it minimizes some loss function, and it models the density exactly. So given enough expressive power and nice enough loss functions, you can use the simulations to build a neural network surrogate. That's what it's called, surrogate, because you input some parameters, input some data, and it gives you the probability density model. And you build these surrogates, and if I had to say what is neural SBI in a nutshell, it's exactly this, that we use these deep learning surrogates for the modeling of probability density. Okay, so that's what neural SPI is. I just want to note that you don't have to model probability density functions because it can be more expensive. So instead, we can also model density ratios, which are much easier to handle. Another thing to note here is that psi corresponds to the model parameters. And so whatever you output is also parameterized on your parameters psi of the neural network. So you can do that because in a frequentist test, which is what we use at the LHC, it doesn't matter if we divide by a parameter-independent constant. Eventually, it cancels out, and you still have this test statistic that retains all the desirable asymptotic properties that come with the profile negative log likelihood ratio test. All of this is to say that you could use neural networks to model the densities, but you could also use neural networks to model the density ratios. Okay, so all excellent. To summarize a very high-level overview, I'm going to be talking about parametric and non-parametric. So we looked at the traditional analysis, right? So we have this M4L. This is like an exactly known analytical or parametric formula associated with M4L. So I give you X, you can compute M4L of X. And for histogram morphing, we also have this parametric formula. So we fit quadratic functions, polynomial functions through simulation points. And so we have parametric simple analytical dependency as our traditional analysis. And then neural SBI is completely non-parametric. And here I'm going to be calling neural networks non-parametric because they have a large number of parameters. So the neural network models both the observable dependence and the parameter dependence mu and nu using something called, using neural networks, which is what we call here non-parametric. So that's the difference. So you have parametric, traditional, non-parametric with neural networks, that's neural SBI. All well and good. Can we apply this NSBI to LHC? For 10 years, this was the main question, and we all tried. But the challenge here is that you have nuisance parameters. As I was saying, it's a very high dimensional space. It could be 100 dimensions. Only sparsely populated. So at Atlas and CMS, we don't densely populate this entire high dimensional space. So we don't have simulations here, here, nowhere. We just have simulations up and down for each axis. But neural networks then don't know what to do in between. So you can pass these parameter values to the neural network, but what does it do here, or what does it do here? You cannot tell the neural network that these are independent axes, do this, do that. They're not that regularizable. So while you can model these density ratios, you cannot sample continuously from this space, and this is where the challenge comes in. So this is why you cannot directly apply an SPI to LHC experiments. But we come up with clever techniques, as we usually do in physics. So one of the things is that we use domain knowledge that we already have been using for traditional analysis in this new SPI, to scale SPI to real LHC analysis. So let's take this density ratio that we set out to model. So this is for a single IID event. So you have some normalization term. Lambda corresponds to the total number of events. And you have this differential cross-section term. So this is the differential cross-section for P sub S. And you have divided by some reference hypothesis. Now, you might be thinking, what is this sample? So this is just like quantum field theory 101. So you have like different topologies, what we call signal, what we call background. And of course, we simulate them independently. We sum them up. Oftentimes, we have a simple model, like a signal strength measurement. So for example, this could look like something like this. So you have signal, you have background, and you have rates associated with signal and background. And that's exactly what this kind of factorization is. But we go one step further. We split this differential ratio part into 3 terms. So some of the times we know the parameter dependence is exactly, like if we are aiming to measure signal strength measurements or EFT parameters, where you have a morphing formula, you have this known parametric dependencies. So we bring that out. So this can be known analytically. But we also have this systematic variation ratio, which we have separated out. So we have this systematic variation part, known dependencies, and this density ratio, which is now parameter independent. The lambda terms can be estimated using his factory, as we have always been doing. It's just the total event yield. But these other terms are what we set out to measure, and the goal behind doing it this kind of way is that we have now independent factorized targets that we can tackle independently. So let's start with this term here. So we know this term, we can compute this using his factory, and the way we compute this is using a parameter-independent neural network. So note that this quantity here does not have any parameters it is conditional on. So you don't need to train a neural network that takes as input parameters, so you don't care if you are sampling from a very dense parameter space. You just have your simulations from the numerator hypothesis, from denominator hypothesis, and you train a neural network to estimate the density ratio. Now, this is a very non-technical talk, so I haven't mentioned how we do this. It's just that you have to trust me that this can be done. And it's super easy. But this is the real culprit, right? Like this is still very high dimensional. So nu is super high dimensional. It could be 100 dimensional. So how do we deal with this? So we use his factory like we have always been using. So first thing we approximate is that in this model, each of these nuisance parameters, nu1, nu2, etc., we assume that the impact on the final likelihood from each of these nuisance parameter factorizes. So that's the first assumption. So we take the probability for each parameter nu_m, and then we take the product of each of these probability ratios. Of course, we still need to measure this. So now do we train a conditional neural network? Well, we still just have, even for each axis, just 3 simulations. So the neural network would not know what to do in between them or away from them. So this is where the second assumption comes in. So again, in his factory, what we do is we simulate 3 points, and then we fit a polynomial bin by bin. Now we do it event by event. So for each event, we compute 3 values. So of course, this is 1 by default because it's just P sub s over P sub s. But we compute 2 neural networks to estimate these parameter-independent quantities. We train a neural network. It estimates this. Again, you have to trust me that it can do this really, really well. And then for each event, from these neural network predictions, we fit a polynomial through this. And that's our assumption 2. And together, this enables us to compute this term here. So now we have all of these quantities. So we compute this using histogram. This is known analytically. This we compute using this approximations. All we have to do is train 2 neural networks per nuisance parameter. And this we computed using parameter-independent density ratios. All in all, I introduced to you semi-parametric SPI. Semi-parametric because it uses non-parametric models for computing these parameter-independent ratios, but then it uses parametric ansatz to interpolate between the outputs of these ratios. So super simple. We took a page from the traditional analysis and we applied it to SPI to make it flexible for C analysis. And this is exactly what we used to make the first ever measurement using neural SPI for off-shell Higgs boson at this experiment. So these are the 2 papers. And just to note here, the historical importance is that ever since the start of the LSC, this is the first ever measurement with real data that uses fully differential, but also multidimensional information. So fully differential, multidimensional, and continuous information to do this measurement here, which is this beautiful result that you can see here. So semi-parametric SPI, and just to note that at around the same time, a Fino paper came out that mentioned essentially the same idea as what we did for the Atlas analysis. Okay, all well and good, but I've handed you a recipe for great statistical power. Now you can constrain your physics parameters. Okay, now you can constrain your physics parameters with super high dimensional information. And not only that, with SPI, you constrain all parameters super precisely. But of course, with great power comes great responsibility. So what we can do is so one of the main questions you might have is that what if these neural networks that we're using as surrogates are mismodeled? Of course, they could be, and then they do not retain the asymptotic properties typical of a negative log likelihood ratio test statistic. So what you can do is always build a Neyman construction. So you can calibrate your confidence intervals exactly for your model. And then you're all set. Even if your neural networks are wildly mismodeled, you could have more conservative limits, but you will never have wrong results. You will never exclude something incorrectly. Okay, I think I might skip this one, but because now we are constraining parameters equally well, we cannot rely on traditional assumptions always. We also want to model this high-dimensional space without assuming that the impact factorizes. There are ways to do that. We cannot train conditional neural networks because they're still harder to regularize. But we can use more complicated parametric formula like was shown in this paper here, which takes into account these cross terms between different nuisance parameters. We could also use Gaussian processes, where the idea is that we have the flexibility of a non-parametric model because Gaussian processes are non-parametric, but they are super easy to regularize. So when you don't have enough simulations, when you just have simulations on the on-axis points, you can force the Gaussian process to do basically the same thing that his factory does. And so they are super easy to regularize. But when you do have additional simulations, the Gaussian process can be much more flexible than a simple his factory model. And just to note, now we are constraining all parameters equally because we're doing this fully high-dimensional measurement. You could have over constraints in measurement if these constraint terms are not calculated using fully differential information. If these constraint terms are computed using some small discrete observable, then their constraint may not be tight, and then you have over constraints, which needs to be investigated carefully. So I think longer term, as a community, we can collectively shift focus towards constraining each of these nuisance parameters where possible, using fully differential SPI measurements as well. And yeah, so what is the future? Well, the future is here. We organized a blueprint workshop earlier this year to build a roadmap towards broader adoption of SPI across the LHC. How can we make this more mainstream? That was the question. We have a huge community working along this. So we have this work here, which does this end-to-end optimization, going from simulations, training, to final results, and then optimizing end-to-end to give us the best possible results using SPI, because SPI does require a lot of training. We have this work from IRISAP, which I'm working on, which has this end-to-end training and inference pipeline going all the way from simulations to the final results in an LHC-style analysis. We also have work being done on workflow orchestration for this kind of SPI techniques, but you do need to train a lot of neural networks and an ensemble of them. Just to note, this is one of the works that has a full end-to-end example. So it has an example of doing a full semi-parametric SPI using a pheno data set, but it can very easily be applied to your own analysis. So I would encourage you to give it a try. Here also, of course, one of the things at SPI that we do is we don't just measure for a particular final state. We also want this measurement to be legacy, to be propagated for future combinations, to be used in various ways. And so one of the things we usually do traditionally is we have workspaces that we can publish, that we can use for combinations. And there is ongoing work to do exactly this for SPI, essentially generalizing the binned workspace into an unbinned one. So I'll leave the details here in these links and also in this talk here. I don't have the time to go through this now, but the idea is that now an SPI can also be part of the standard statistical analysis ecosystem. It's not just a pie in the sky thing. It's something that's here to stay and something that we can be using right now. Okay, so there's no scaling laws associated here. You can start using right now. I presented a high-level overview, and of course, there's no technical details, so don't take this talk as the one-stop thing. I also skipped summary-based SPI, example Sally, which is not covered here. And just to note, a lot of the studies has been done to make an SPI robust and scalable, so you can start, it can be applied right now to LHC experiments. And yeah, more and more analysis that I know of are following the same thing. They're trying to use SPI. New tools and techniques are being developed to make SPI easier, more robust, and more streamlined for mainstream use. And to end the talk, just to note that we are entering the era of precision, as has been the topic of a lot of talks today, including Higgs boson, EFT measurements, and a lot of this. And NSPI can be an integral technology that helps us scale this better. Thank you so much.
Thank you, Dave. I think we have time just for one question. The rest will, I think, we'll take over a coffee break. So, Question? Yes.
Hey, great talk. I have a question about the semi-parametric SBI. So you showed, for example, this analysis done with semi-parametric SBI. I was wondering how large is the gap when you go from full SBI to the semi-parametric one? Not just in terms of constraining powers, but also if you look at like coverage or calibration of the procedure you get.
Yeah, that is an excellent question. I mean, in principle, when we do this semi-parametric stuff, the key part here is this approximation here. So of course, if you had unlimited data from your high-dimensional parameter space and you could train a fully parameterized neural network, then we could do this kind of comparison. The problem is that at the LSC, our truth model is constrained by the fact that we only have simulations at 3 parameter points. So to answer your question, there is no way to actually check how it compares with fully neural SBI except in toy studies. So in toy studies, where you have this simple parameter of interest dependence, it's 1-to-1 if you trained it correctly, but and if you have enough simulation data. But in this kind of approximations, unless we have simulations with a very dense amount of points, it's hard to compare between the two. Of course, the idea is that this will reach an asymptote, some optimality asymptote. It is higher than if you had a fully parameterized thing. How big is the gap? That's hard to determine.
Okay, thanks so much. I think we have to move on. Let's take Jay again. Now the last talk of the session is Luigi, who's going to talk about basically symmetries and Lorentz in particular.
All right. So welcome everybody to the Lorentz equivalent neural network talk. And here I try to structure the talk around 3 questions, which I will try to answer. So first, why we care about symmetries and Lorentz equivariance, as in, so why is it helpful to include these informative priors? Second, how can we do it in particle physics? And for example, what are the symmetries we really care about? And thirdly, for what? As in, okay, for what can we use this neural network? And once we have them, then what do we observe? If I have the time, I'll have some comments on the bittersweet lesson, but we already heard about this from Lucas. And starting from the first point, I want to do something quite challenging. I don't want to just say, okay, this works. I also want to motivate it. And for that, okay, I first introduce what equivariance is. This is exactly the same as covariance, defined in this formula. We're basically saying if we have a function f, we want this, for example, a neural network, we want this to commute with any elements of a certain symmetry group G. And in the case of invariance, then this output will not change if I apply any G to the input X. And so in this sketch here, it means I can go right and down, or down and right. I will get the same output. And then I also have to remind you that what we are trying to solve is always a fit, a very large over parameterized fit. So for example, we try to solve a classification problem. Then the function f we try to optimize for will be the lateral ratio, and the loss function related to this lateral ratio will be exactly the one which reaches P over Q if this is 0. And you can write it in an integral form, which corresponds to the limit which of infinite training data. But clearly this is never the case. We have a limited training data set, and so we write this in a Monte Carlo average form, where we only have capital N data points, and I'm labeling this as L hat. So these two in principle are different. And now we can look at the space of possible functions. This is actually taken from a great book on geometric deep learning. You should check it out if you're interested in the topic. And here we have, okay, the space of solution. This is the one we can actually explore, modeled by some complexity weight. So this is just saying we only have access to the functions inside this space. Let's say we find this solution after running the optimization f at theta. Let's also label the best solution we can find in the limited training data sample f theta hat, and then we label f theta star the best solution we have in this space f, evaluated in the limit of infinite training data. This in principle will not be in the space which also contains the best global optimum. And so once we have these labels, now we can try to look at the error we have from the solution we found. So f theta theta. So this is just the difference of the loss evaluated in at theta and the global optimum. By doing some simple math, you add and subtract some terms. For instance, the loss evaluated at the best solution available we can find in the space we can actually explore, and we can first extract an interesting error, this one here, and then we can add and subtract two more terms. These are the loss from the finite training data size evaluated in f at theta, so the solution we find, and the best we can do in the limited training data regime, and this will fully factorize the error in three terms. The first one in orange is called the estimation error, and this can be rewritten in this way, and it's just an estimate of how far the loss in the limited training regime is from the full integral form. And clearly this scales with the dataset size, and it reduces if the more and more data you use during training. The second one is an optimization error. This is just quantifying the distance between the best solution you find and the best you can get in the limited training data regime. And the third one is the approximation error. So how far you are from the global minimum once you evaluate the best solution you can find in the infinite training data regime. And if you go back to the plot, the approximation error will be related to the distance between these 2 points, here in green. The optimization error will be the distance between these 2 points, and as I said, the estimation error is just a way to estimate the size of the statistical deviation you have in the limited training data set available. Okay, so now what do we do when we introduce a symmetry? First of all, if we are studying a system which has an exact symmetry, then the approximation error does not increase, because I'm reducing the size of the space. I'm only constraining the space to the function I can actually explore, but I'm not moving further away from the global optimum. Second, the estimation error is reduced. This is one of the most powerful points, because you can see it has an improved data efficiency, because now each data point, if you want, in the training data set is not just exploring a single phase space point in whatever X is, but actually it is also exploring all the other phase space points which you can connect with a group transformation. And thirdly, you can also show that if you have a more constrained space, then you have a smoother landscape. So in principle, you can also reduce the optimization error. Okay, so this is why we want to do it, and why embedding symmetry actually reduces your minimization error. Second, how do we do it in particle physics? There are two main, I would say there are two main categories. One is to use specialized layers. So here the idea is I have my geometric input. I have a neural network with the standard, for example, linear layer, and I have to replace all of them with operations which now respect the symmetry. For example, Lorentz symmetry. One example would be to go from a linear layer to an equivariant linear layer. And those are some examples in the literature. We have LorenzNet, Pelican, and Alligator. And a different idea, which I want to discuss in more detail here, first because it's new, second because I spent some time on it, is to have a canonicalization approach, where you define the local frames for each particle, and these are, if you want, architecture agnostic. So now I just want to show you some example on how people implemented these specialized layers in chronological order. So starting from LorenzNet, I don't want to spend too much time here. The idea is to In Lorentz net, you have two channels, one which only takes scalars, and the second one which only takes vectors, so for momenta, for example. And these two channels don't really talk to each other except here. And all the inputs you pass to this multi-layer perceptron transformation are scalars. And so you see that at some point you have a Minkowski product between the vectors, so you always respect the geometry of the space. Okay, so this was one of the first implementation. Then we have Pelican. Is built upon a powerful idea proposed by Hilar, which says that all the Lorentz equivariant, any Lorentz equivariant map can be written as a weighted sum of scalars of these weights here. And in Pelican, this is implemented as a first embedding layer which maps everything into Lorentz invariant. Particular scalars will be nodes in a graph, and vectors will be the edges. And in Pelican, you basically calculate all the possible Lorentz product, all the possible PI/PJ, and you embed them in a matrix. And then to make this permutation equivariant, you build all the possible maps over the two. These are known, these are 15, and once you implement them, you get an exactly permutation equivariant network, and then you aggregate all these maps. Third, we have Alligator. So in Alligator, you define a geometric algebra. So the input is not just scalars and vectors anymore, but you have a 16-dimensional set of inputs. These are represented as scalars, vector, an antisymmetric tensor, pseudoscalar, and axial vector. So this is the first step. You introduce the geometric algebra, and then this is based on a transformer. You have to replace all the operation in a transformer with Lorentz equivalent operations. And this is basically this is just a list of all of them. For example, you see you go from a linear layer to an equivalent linear layer, and you also have to introduce the group operation. So in this case, this is the geometric product. Then okay, so this was the list of specialized layers architecture. Let's move on to canonicalization. Here the idea is rather different. So in this case, we want to define a local frame for each particle, here labeled as L. And this L has to have a very specific transformation. Under a general Lorentz transformation lambda, this has to transform as L times lambda to the minus 1. And we want this because once we map X on in this local space, then the features will be Lorentz invariant. And this happens simply because the lambda to the minus 1 simplifies with lambda, and so in the local local space, the features, all the features of any order will be a Lorentz invariant. And yeah, so you can show this in one line. You can also show in one line that if you want an equivalent output, you have to apply a final transformation to the output, which is the inverse of the local frame. And again, you can show that this then will transform equivalently under a general Lorentz transform. Okay, so I told you we need this L, but to define them, okay, but now we have to find a local frame which respects that transformation. The easiest thing you can do is to take a matrix and put covectors as row, and then by definition, these will satisfy this transformation rule because we know how covectors transform. And by the way, this is nothing new. This is used in general relativity to map curved space into a local flat matrix. And in that case, these are called tetrads. Okay, so I just rephrased the question from how to predict a local frame to how to predict a set of 4 vectors, which we can then put into this metric, And this is the whole idea of LOCA, Lorentz local canonicalization. Or if you want, in Catalan, it is a Boudin. And in LOCA, what we do is to predict 3 vectors for each particles using this equation here. So these will be the 3 vectors. And these are predicted by a very small GNN, talking about a few thousand parameters. This is the phi here. Following this equation, which takes as prefactors only scalars, also the neural network takes only scalar inputs, and is multiplied by vectors. So this is manifestively equivariant. Second, we apply Gram-Schmidt to this vector to go to an orthonormal set, and we predict the fourth one using the cross product. And in this way, we constructed these 4 vectors, which build an orthonormal basis, and they can be used to define the local frame for a single particle. Okay, technical aspect, if you want to be numerically stable, it's better if you use a polar decomposition. This is what we do. Okay, so this is the whole pipeline. This is very simple. You start from your particle data. Let's say you have 4 momenta. You pass them to the FramesNet, the network which predicts the local frame. Then each particle is projected in this local frame, so just multiplication L times P. And once you have these features, which are all Lorentz invariants, you can apply any transformation, so any backbone architecture to it to solve the term-sim task. This can be generation, regression, or classification. Okay, so this was it for this part. Now I want to show you what do we get from this. I will start with a simple regression example. So let's say we're trying to predict a single Lorentz invariant quantity. In this case, it's the square matrix element for this process here, from Z plus 1 gluon up to Z plus 4 gluons. We know the symmetry. This should respect permutation equivariance and Lorentz invariance. And yeah, to see how things scale and what we get from symmetries, I want to start from a simple MLP, which takes as input all the possible dot products. And here I'm just plotting the accuracy. If you want, it's the MSE between the truth and what's predicted. Okay, you get this curve. Then you can start to introduce a better data structure. So we know this particle data, so it's better organized as a graph. And so we train a GNN and a transformer. This is now introducing permutation invariance. And you get these two lines here. You see that you have a better scaling towards higher multiplicity. And finally, you can put things together, symmetries and better data structure, and you get these 2 lines here. In this case, we trained the 2 transformers, alligator and loca, and you see in this case you get the better scaling and the better performance. All right. The second example is tagging. You know, this is well, a good benchmark for in high-energy physics. And on the left-hand side, I want to show top tagging. This, background rejection for top tagging. This is just an history of developments, incremental developments, went from simple BDTs to much fancier architecture based on transformers and whatnot. And here you see that if you want to maximize performance training a single network, then the Lorentz equivalent architecture, these are all at the top. If you want to go beyond that, you have to do something on top. So this is typically adding more data in a pre-training plus fine-tuning way, if you want, with foundation models. Second, so another example, this is the jet class dataset. Here I just want to highlight again that equivariance always wins. This is a much bigger dataset. First, equivariance always wins, it's at the top. And second, you really see the improvement thanks to LOCA, for instance, because in this case, we train the LOCA versions of well-established architecture, for example, ParticleNet and PART-T. And in both cases, by just adding this FramesNet and equivariance, we improve the performance for both of them. We have the LOCA ParticleNet here and the LOCA PART-T up here. Okay, final point I want to make, symmetry breaking. So if you talk to an experimentalist, they would say, okay, once you hit the detector, there is no Lorentz invariance or equivariance anymore. And indeed, for tagging, this is the case. The tagging score is not a Lorentz invariant quantity. And again, thanks to LOCA, we can do a quite fair comparison between non-equivariant and equivariant transformer, because we're adding a few ingredients on top of the standard vanilla transformers. And here, this is a quite complicated table, so I will delete part of it and just look at the AUC. So the upper, the better. So there are 2 ways you can break the symmetry. You can either restrict the neural network to respect the subgroup of the full Lorentz group, and this is called an hard symmetry breaking or architecture level symmetry breaking, or you can break it at the input level in what's called a soft symmetry breaking. This is done by adding either spurions which are invariant only under the subgroup of the symmetry group, or by adding additional scalar inputs, those also invariant under the residual symmetry group. And in this case, for tagging, we expect that this is the residual symmetry group, so boosts along the z-axis and rotations around the beam-axis. And indeed, in this case, both the architecture and the input symmetry breaking gives the same results. But then, okay, if you go to full Lorentz group, the performance is lower. Now we know why, because we are increasing the approximation error. If you look at the architecture and you move towards a larger symmetry group, the performance also goes down. We know why, because we are increasing the estimation error. But if we now look at the input symmetry breaking, you see that the network is retaining the optimal performance, even if you go down to a non-equivariant neural network. And this is nice to see. And our explanation for that is that in a transformer, you can actually build the interaction in the attention matrix between the spurions and the scalars and the other particles. So the network has the freedom to restore or break the symmetry in different phase space regions. So this is kind of a automated way to tune your symmetry breaking. And okay, so this was my last point and my conclusion. So why are we doing it? To improve the efficiency in our data and to reduce the minimization error. How do we do it in particle physics? By introducing a graph structure, permutation, and Lorentz equivariance, if needed symmetry breaking. This is just a shout out to the work we did. Like I spent a lot of time with Jonas in having an efficient implementation of Loca, and Jonas spent a lot of time on Alligator. So these are efficiently implemented packages, and you are free to try them with just a pip install. And thirdly, for what? As far as we know, we can apply it to any task with geometric inputs. This should work. And then what? You can maximize performance, which is a valid argument given the future ahead we have at the LHC. All right, that's it. Thanks.
Thanks so much, Luigi. Comments of questions? I see two. First, Marco, and then Anna.
So thank you for your talk. This is great work, and I know it's nice to see these things, especially if you are a bit theoretically inclined. And so I have a question on performance. So I mean, commonly people say that including symmetries in networks helps, especially when you don't have that much data. Okay, so it helps in the low data regime. But once you have really lots of data, and especially if you go into some over-parameterized regime for your networks, it doesn't matter so much. Okay, so this is not necessarily my opinion. But so first of all, I would like to know if you see this effect, and then whether you find this maybe you mentioned it, I don't know whether you find networks that include symmetries, you find them harder to train, maybe because it takes longer, or because you mentioned that I think you mentioned that the loss landscape is smoother, but I don't know. So are these harder or easier to train?
Yeah. Okay. First question. That's a good one. So I can go to the extra. So okay, this goes under the bittersweet lesson. So if you have a lot of data, you can just throw more data at your problem, you will reach the same performance. And we did a few studies. So one of them is this one. At least in this other regime, we don't observe that the two network achieve the same performance, tend to the same performance at least. So in this case, again, this is the regression example. We generated a Z plus 4 gluons dataset, which goes up to 10 to the 8 training samples. And up to this data regime, there is still a gap between the local transformer and the transformer. So if the two do converge, then you need much more data. And at some point, I mean, this has to be the case. At some point, if you have infinite training data, a neural network is a universal approximator and should be able to learn the symmetry. But do you really want to generate that much data? I don't think so. Second is preliminary. So we did the same for tagging, kind of try to derive the scaling law. These times are at a fixed. So we always train until convergent, but we look at fixed computational cost. What is the best neural network? And again, this is a jet class, so maybe it's not the biggest data set, but for instance, if you fix the network parameters, you always win. Both here the equivalent architectural alligator and the local. And also if you look at other metrics, for instance, the energy, like we estimated the energy in Joule. And again, you have, if you want to maximize performance at a fixed energy point, you should still use equivariance. So, yeah. The second part of the question, are these harder to train? Does it take longer? So for this another difficult part of the job, because you have to implement in an efficient way. And for these networks, they are a little bit slower than a standard transformer, but not a lot. I would say around 20-30% slower. So it's reasonable, it's manageable. And about the training, we did observe some instabilities in training. We're still trying to improve on that side. The main takeaway right now is for some parts you need float CSU, especially if you're working with 4 vectors in a highly boosted regime, then this becomes tricky. Yeah, and this is the problem for alligator. You have these highly boosted particles, while for local the problem is shows up in the local frames, because then you have the boost factor, and this cannot be too large. Like if you reach numbers like 100 or so, then you see the same instabilities. So we're trying to solve them. Right now, those are not a real limitation to the training. This still works. Yeah.
Thank you. Next.
Yes, thank you very much for the nice talk. I think one of my questions is also related. So, in this bittersweet lesson, is the only difference between the OmniLearn and the alligator that they have a ton more data? And would it be possible to train alligator on the same amount of data or the same type of data, or is it like some incompatibility in what they are doing and the tasks they are doing?
Yeah, it's basically what I'm saying here. No? I think you're referring to this plot. Like recently, Ben and Vinny published this OmniLearn, which is the model with the best background rejection for top tagging. And you say, okay, here they just threw more data at it. But in principle, yes, it should not be a roar. It can also be a hand. So you do both. You throw a lot of data at your transformer, and you also have symmetries.
Yes, because that's then what you showed on the next plot. So I was wondering, like, is it possible to train your model on like this data set, or is it something? Because I know, for example, like we are using tokens, and they are very difficult to make, Lorentz equivariant. But so in principle, it would be possible to throw all of this data also at alligator and then see what happens.
Yeah, we're doing it.
Okay. Last very quick question, if any. I don't see, so let's thank the speaker again.
Right, welcome back from the coffee break. We have another working group 3 session today, and the idea here was to go look a little bit towards the future. So we start with Pamela first, so will tell us a little bit more about the high Lumi potential. Pamela, the floor is yours.
Okay, so I will make a summary of what we had done a year ago now. That were the projections for the high luminosity results of Atlas and CMS. Unfortunately, we had only 3 months to do them. They tell us 3 months in advance, so we had to choose only a selection of physics results that are not representative of all the things that we can do at high luminosity LHC. But we had very few people, and really little time. So essentially the results that I will show are either statistically dominated or they won't be improved for decades to come. So as you all know, we are here in the middle of 2026 and we'll stop, we'll have a long shutdown, and then we'll have this start of the high luminosity LHC phase, which will bring us from about 500 inverse femtobarn to hopefully 3000 inverse femtobarn of integrated luminosity. We had two different approaches to extrapolate our results, but I have to say that our results are quite conservative because they are all based on run-2 analysis, completely published and simply extrapolated. So there is nothing, all the systematics, everything, it's really the real ones and even conservative ones. So we had two scenarios, one that had the experimental systematics from run-2 analysis squared with the square root of luminosity that we have seen more or less, it's what is happening with the years. And this is the more tricky point, half theory uncertainties, because as well we have had big advances in theory in the past years, but of course it's difficult, right? And the Monte Carlo statistics, which it's a reasonable assumption with our CPU availability, etc. Then we had an S3 scenario where we had a number of additional improvements that were the only ones that were already published, but actually they were very small ones, and we had the similar numbers for Atlas and CMS. It was just 5% on BJET's tagging and tau hadronic performance and improvement. But as you have seen yesterday, they were larger, and actually they are even larger now with new taggers. So you already understand that it will be different. So what is the future of Higgs? This is how it looks for ChatGPT. And for us, it looks more like this. So these are the couplings that I'm showing of the individual particles of the Higgs. And this is in this scenario 2. As you can see, we will get to 2-3% precision for the ones that are well established. But the interesting thing to see is that the dominating error is the theoretical one. So actually, experimentally, we could go lower than this. And the other thing that some people reminded me to remark on this slide is that here the theoretical uncertainties are already halved. So this will be the problem. On this plot on the left, we have a dependency from the width of the Higgs, etc. So we made also a plot where we have ratios of these couplings with respect to the standard model 1. And there you have a bit of a cleaner picture, but it doesn't change much. So the good point is that since 2020, even for a single Higgs analysis, we had improvements that are already written here on this slide for all these channels. So even if these channels are very much established, we still had improvements, and of course the big improvements will happen for the channels that we have not yet observed and that are still statistically dominated. So if you want to remember it, we will go from about 10% precision to 3% precision dominated by theory. Another thing that we did, and this also nicely linked with the talk that we saw yesterday, are some bins that are statistically limited, or some analyses that are statistically limited. So of course we projected the Z gamma and X to mu mu, and these are the numbers that we will have with 2 and 3 inverse aptobarn on the precision on the signal strength. And below we have also 2 bins at IPT. So it's the Higgs to gamma gamma bin higher than 650, and a VH to BB bin higher than 600 GV. You saw yesterday from a talk that CMS, I think it was the EFT talk, CMS has at high PT in VH some excess. So of course it will be very important to get good precisions on bins like this. So now it's lower, the excess, but we can even reach the 600 GBB. So then the thing that will be really one of the biggest or highlights is really the potential of the Higgs boson, which will mean to look for 2 Higgses this time in the future. And you've seen this plot also yesterday. So this is the famous Higgs potential. And at 3 level, this has this very simple form. And the only unknown parameter is this lambda that is directly proportional to the rate of appearance of the Higgs. So of course, if we measure that, we measure the Higgs potential. And the big problem, and the place where we can really gain, is not only that for every Higgs events that we see, there are a million that looks like it, but it's really the problem of how well we reconstruct them. Because if this, it's all the events recorded at the LHC, and I'm showing 1,000 times magnification lengths, the yellow dot here are all Higgs events, so single and Higgs, more or less in scale. We made an effort to make this plot. And the 2 Higgs events are the blue dots. But these are only the ones that are produced, not the one that we reconstruct. So if I take another magnification lens, what we are at present reconstructing is this red part, and all the rest is left. We cannot reconstruct for various reasons, but as you have seen again yesterday, we are doing a lot of improvements. In particular, also the trigger is killing us and many other things. So we have a lot of room of improvements, and we are actually doing these improvements as much as we can. So of course, observing that 2 Higgs in nature will, and even not observing it, would be a major milestone, because it has a tremendous impact on cosmology and on theoretical physics, and in particular on the disappearance of antimatter in the early universe, or eventually to the stability of the universe. What about the beginning of the universe? So instead of having this shape that is this bottle of champagne, the Higgs potential could have this shape that you see here in the bottom. So at the beginning, when there was electroweak symmetry breaking, the Higgs boson was in this position, that it's not an overall minimum. And then it can go to the minimum where we are now. And this would mean that there could have been a violent electroweak symmetry breaking with a first order phase transition. Actually, what we are interested in general is a strong first order phase transition, because this is the only way that we could have electroweak baryogenesis. Because essentially what would happen there is that within these bubbles, because essentially the universe had a first order phase transition, so like water that goes from liquid to gas, it was boiling. And in these bubbles, there could be the conditions to have more matter-antimatter. It's a necessary condition, not sufficient, so we need also CP violation, but we would need this to happen. And this happens only if there is a strong first-order phase transition. At least this is what the theorists that work with us told us. What happens is that essentially it all boils down from having this continuous crossover when there was the electroweak symmetry breaking, and having a first order phase transition with these bubbles. There are also consequences on the end of the universe that you can look at in specific models, but I won't go into that. But in principle, there could be another minimum, which I find a very fascinating idea, the idea that in reality we are going from a minimum to another, and that the universe could be metastable also in the future. And there is an indication, of course this is can be a bit controversial, but okay, if the standard model is valid up to the Planck scale, and we use the top pole mass and the Higgs pole mass measurement, the central value of our measurement now indicated that the universe is metastable. We cannot yet exclude fully the absolute stability, but if we measure better these quantities, we could. And I will show you also this. So both beginning and end of the universe, we could revolutionize it and maybe find also new physics. So let's assume a standard model Higgs for the moment, and if it would be the standard model Higgs, we get, as was anticipated yesterday, at the end with free inverse Upton, 7.6 sigma, but the important number to remember is also that in just 6, it was actually 5 because we did these projections at the beginning of 2025, 5 years before we were saying that we could get only 4 sigma, okay? So this is a huge improvement, and we are improving, I think at the same speed, we are improving very fast. And this could lead to 26% on lambda free. But again, I say it, even if I am recorded, I'm sure of what I'm saying, we will get probably below 20%. I'm sure about that. In any case, it's my opinion. So this will be really, we will get to know this Higgs potential very well. So this plot also, you have seen yesterday, it's the combination and the contribution of all the different channels. This is on lambda free, but also on kappa 2v. That also it's very important to establish. Another thing is, well, what if it's not the standard model value of lambda free that we'll find? This was a very debated topic, and we didn't have a plot to show it, because indeed you really have to observe this diagram, the triangle diagram. There is an interference, and depending on the value with the box diagram, and depending on the value of lambda free, you can have more interference, and there is a region around the lambda free equal 2.3, so it's not standard model, where this interference is maximal. So it was thought that the LHC could not measure that. Instead, we can. These are 1 and 2 sigma bands. If the lambda free value is measured with respect to the true value, okay? And you can see that practically in most of the cases, we exclude at more than 2 sigma the standard model. And with the improvements that we will have, we will exclude it also very close to 1 at the end, I think. And right now, there is just 1 point where we are at the border somehow. Then it depends what are the deviation, of course. Then another interesting thing, it's looking at 3 Higgs. So this for now looks, maybe this is not so promising. Actually, I think it will be promising. It will certainly help us a lot. Because, of course, if you don't look only at 3 level, there is a contribution for the quartic Higgs coupling that I was not showing before. And essentially what you can have is that you produce 3 Higgses in the final state. And we did the projections also for this case, where we left both kappa 4, the quartic couplings, and kappa 3 free to vary, by looking at using then the final state when you produce 3 Higgses all decaying into Bs. So you can already imagine that if you have large improvements in the B tagging, these kind of channels will profit a lot about it. And also that this is only the 6B channel, but you can have other sort of channels like with gammas, with taus, boosted channels, etc. So we can certainly improve on that one. That is now 100 times the standard model about. But the other point is that then you can combine it exactly as we did with single X and IX and with all the rest, and you can really constrain a lot of contemporarily. It can help to constrain and understand better what we are observing. So this is all to be seen, but I think we can achieve much more than what we have now, and there are already some indications also of new channels added even by CMS. Then what does it mean? Because I was defending these things and I got all sorts of questions like, yeah, okay, we get 20% of the Higgs potential, who cares? I got this from physicists, so maybe some of you will think the same thing. And so we decided that we wanted to quantify why it is important to get this precision. And so what we did was that we tried, using this strong phase order phase transition, we looked at very generic models that could change the shape of the potential. So in red, we have our potential, the standard model potential, and then variations of it that are very general. They would imply new physics at a higher scale than the LHC. But they would all allow a strong first order phase transition. And so this is an EFT dimension 6, EFT dimension 8, a logarithmic deviation of the potential, we had a logarithmic part or an exponential part. So here it enters the knowledge of kappa lambda. So the black line is the standard model potential, And our result is totally data-driven. So unless you use this precision around a certain potential, and then you can use the precision and you can plot it in the whole range. If you want to be agnostic and be just data-driven, as our results would be, this is our result is valid only very close to the minimum, which is this zoomed part that we show. But the behavior that you see in the big curve is kept also in this lower part, so I'm showing it for this reason. There are 1 sigma and 2 sigma bands with the precision that it's still 26%, so it will be better in the end. We know it already. And you see that we plotted all these potentials, but actually what we plotted, the alternative ones, are the lines that are limiting the region where we can have this strong first-order phase transition. That it's all, let's say, on the left here and below here where the arrows are. Otherwise, there cannot be a strong first-order phase transition in these models that are generic. And as you see, at 2 sigma, we are excluding them all at the end of the high luminosity LHC. That would be, if this happens, that would be quite a very strong, it would be really a very strong statement, okay? And a fundamental one. Then someone might say, correctly so, yes, but you said that the new physics should be higher than the standard, than the reach of the LHC. What if, and there was a similar question yesterday, the new physics is at a scale that can be reached at the LHC? Then what you can do, because of course there could be tons of models, is to look at the most simplest extension that could still give you a strong first-order phase transition. And these are the scalar models, singlet models, so there are other models that add an additional scalar. But if we have that, the LHC has a very strong advantage on other type of accelerators or whatever, in its reach, that is that this singlet particle can decay then to, it's a resonance, it can decay to Higgs, to Z's, or to tops. Actually, you can use much more channels than what we used. So again, we are very conservative in what we are showing. We just use this because we had them ready on that time scale, but we can do much more than that. And so we projected them, and we decided to use them in this scalar singlet. Now, these plots look very colorful, and the reason why, the reason why we chose this projection, because you see here we have a projection that it's a very conservative one, so there is a choice for the model parameters, but we have scanned them nearly all. And we have a projection in the portal of the model and the mixing angle. And we just chose this, one because it's conservative, one because it is what is shown always by Lisa, because essentially we have a strong first-order phase transition in our case in this area here, that it's hashed, and Lisa has it here. They have only half of the figure. You have to have a bit of fantasy to understand that this is only half of the figure. And what they can exclude is this part here, and we can exclude a bit differently, as you see. So going back to my figure, if we start from that, you can see that we can exclude with various different ways. So with indirect contributions from single Higgs, with the di-Higgs searches, that is this light blue, with the searches of resonances, and here we can nearly exclude completely, in this case, the strong first-order phase transition. But in the other cases, it's much stronger than this. And if you look in another projection, that is the one with the coupling of the Higgs to ZZ versus kappa free, you see that these points are corresponding to this area here, and in reality what is left over it's this line here. It's very difficult to exclude everywhere. In any case, it looks like this, all better in all the points. Then there is an unlucky projection that is not making justice to us, because if we want to project it for all the points, then the exclusion changes here for the resonant part, and then you cannot plot it anymore. But I will plot it anyways. And then you can only show the lambda free and the single Higgs, the kappa Z exclusions. And in this plot, they look like this, 1 and 2 sigma. So you see that you would leave open all this area, where then you could improve. But reality is that here we are not showing the full potential of what we are doing, because we can plot also what the resonances would do. And we cannot plot it rigorously, but by plotting what I've been showing before for the resonance, that again, it's not all the resonances, we would get something like this. And then you can compare it with what you will obtain at future colliders. And essentially what I want to show you is that the gain, even by FCC-EE on that specific model, is what these arrows are showing. And this is it. It's really, and it's conservative still. So in terms of Higgs physics, what the high-luminosity LHC will do is really striking. And this we have to remember. Having said that, the stability of the electroweak vacuum, there as well, it's, we hope from projections that we could get a precision of 200 MeV on the top mass. That would be this red area, or otherwise you could have a larger exclusion if we use less advanced techniques. This will have to be seen. But from CMS projections, we would get this 200 MeV, and from Atlas and CMS combined, the mass of the Z at 21 MeV, of the Higgs, sorry. And if we get this and the central value stays where it is, then we will be able also to exclude the stability of the universe by the end of the high luminosity LHC, for what it would mean. So I will skip this slide. Because I think I've discussed enough what are the consequences. But then, of course, we can also test in an orthogonal way. That was also discussed yesterday by looking at vector boson scattering. That is also very interesting because, as you all know here, I don't teach it to you. It's very important. The Higgs mechanism and the vector boson scattering, they cancel each other, and otherwise we would get divergences. And what we obtained is that between 2 and 3 inverse afterburn, we would have the discovery. So this is the expected significance on the longitudinal W scattering, and we would reach a precision of 20% on this process. We also had top physics projections, and we did it because in the case that the FCC-EE will not run at a high energy enough to give us top physics, this might remain the legacy results for many, many years. We hope, of course, not, and that we can run this important part at the FCC-EE. But in any case, what we saw is that, for example, EFT constraints from TT gamma, TTZ differential measurements are going to improve a lot with respect to the present status. Here, the higher the bar, the better it is. This is it's with the 3 inverse afterburn per experiments and various Wilson coefficients. We looked also at the 4-top, and I'm showing it here because this is the red line is the expected, so the precision that we'll get. It's 6% on the cross section for 4-top, but this is the experimental precision is much lower than the theory precision. And the theory precision right now, the uncertainty is the limiting factor. So again, it would be very important if theorists could improve this calculation. Of course, everything is very difficult. And from the top Yukawa coupling, so we can also extract from 4-top the top Yukawa coupling. That it's interesting because it can be extracted also from TTH. But this is an orthogonal one because here in this case of the 4-top, the Higgs is off shell, so it's a bit complementary. And we projected it in 2 cases, that in the case that TTH is parameterized or not as a function of the top Yukawa coupling, and you see the results here. So what I want to say is that I didn't mention a couple of things. First of all, that from our projection, the charm Yukawa coupling will be known with a sensitivity of 1.5 times the standard model value. But we have seen yesterday that there are big improvements in the tagging. So this again will be better than this. These are the precisions with which we will know top Higgs and W masses. And on top of what I have discussed, and of course the top quark physics will stay for many years, the results, unless we get the top threshold scan, which is going to change at FCC. So I mentioned improvements, and I want to give some examples for you to remember. They were already showed, some of them yesterday, I think, or even all. So we are surpassing our projections, and the examples are the 4B final state in CMS, BB gamma gamma in Atlas and CMS, and here I've been cautious because it's larger than that. We saw even 30%. So the improvements, apart the statistical ones, are between 10 and 25% already now, and only 1 year has passed. And this comes from trigger, better flavor tagging, machine learning, new channels also will be added and are not yet there. They have been mentioned also, boosted channels, better categorization. We can also use charge tagging within jets, which might be an improvement. And there are improvements also on triple X with new analysis, as I was mentioning. So we are essentially going from this red little circle, we are expanding it within this blue one that I was showing you. And just to show the improvement that we had between 2020 and 2026 in the main channels. So my conclusions are that I think that the near future at the LHC, and I didn't talk of many other things, searches, of many other things that we are doing because we didn't have the time to prepare them, will be thrilling. And so I look forward to it.
Thank you so much. Very inspiring. Let's see if you have comments or questions. Please.
Thank you very much. I have a question about the projection for the di-Higgs case in the scenario when the theory uncertainty does not decrease. So you keep the uncertainties as they are now on the theory side. How would the projection change?
But it's statistically dominated.
Okay, good. That's good to know.
It's really statistical.
Thank you.
Anything else?
I have one, maybe like some closely related to your slides, but I was part of one of the people who were kind of putting the field because of the searches for supersymmetry and exotics. There was any talk about exotics and prospects for Halloween?
We didn't have really the time, so we really worked like mad. But there will be large advancement. It would be nice if the studies would be done in a more extensive way. I think we should do it.
There was one case, for example, for long-lived particles that we know is a big area of research, but then the limitations are really technical. We need the reconstruction in place to be able to do that. And so it's not easy to project because it's going to be a new detector. We need new algorithms. And so there we were debating ourselves, like how do we do this? So some of these are really limited by the tools we have. And
here we are not using the new detector either. We have seen yesterday, for example, that the pileup is not changing anything, right? So I really think that maybe we should redo it at the beginning of high luminosity LHC and
as soon as the reconstruction part is
there,
some new analyses that are coming up, people decide to project it anyway now that we have them. So hopefully we'll get more than what we have of it. Other comments or questions? If not, thanks a lot for coming again. And we continue with Jorge, who will tell us more about the far future. So we're looking also at future collider scenarios as soon as we have the slides.
Let me see. I have to point down here, right?
Yes.
Very good. Thank you. Okay, yes, this talk is also connected to the European strategy update, more about the outcome of this process, which I guess you know, concluded roughly a week and a half ago. And the main purpose of this strategy update was actually to provide a recommendation for the next collider that will run after the LHC. And as I also guess you know, the recommendations of the European Strategy Group was that this could be the future circular A+/- collider, either in its original form or if money is an issue on this scope form, which I will discuss later, but it's also connected to Pamela's concern about whether FCC will be able to do top physics or not. Because of these recommendations, first I was invited to discuss global EFT fits at circular colliders, at future circular colliders. Because of this, I will focus the discussion around the physics case of FCCE, but I will also include the case of the comparison with other projects, as well as complementarities with the program of the next logical step after the FCCE, which would be colliding protons at 100 TeV, close to 100 TeV. So this is schematic representation of all the different colliders that were proposed for this strategy in the intensity and energy plane. Aside from the FCCE, we also have other circular colliders like LEP3, which wouldn't be able to run about 150 GeV. We also have linear colliders, which this is not very intuitive. Okay, you can follow. We also have linear colliders, which in principle had the advantage that could run at 2 energies at the level of 1 or a few TeV. Muon colliders that were proposed to run at energies at the level of 10 TeV. And as I said, if FCCH follows the FCCE, you will be able to collide protons at the level of 85 TeV. Now, focusing again on the case of the FCCE, it's expected to run at different thresholds, starting from the Z pole to the W threshold, the peak of the Z Higgs cross-section, and all the way up to slightly above the 30 bar threshold, around 65 GeV. In principle, is characterized by a very high intensity regime, which is optimal for precision physics, where the access to high energies will be provided by the next step, the FCCH. Okay? What I will do before showing the results of the EFT fits that we did for the physics preparatory group to aid the decisions of the European Strategy Group is discuss a little bit the technical details of the fits. First, we restrict to do a pure dimension 6 SMEF analysis in the Warsaw basis. As you know, in the Warsaw basis at the level you have at the level of 2,500 operators, which make things very difficult to manage. Also, if you allow flavor anarchy in the sense that you allow all these operators, typically the flavor constraints will push the bounds way far the energies that you expect models of the electroweak scale solve some of the issues. So because of that, we assume that the new physics respects U2 to the 5th flavor symmetry and CP conservation at the scale which we assume to be the cutoff of the EFT, 10 TeV, which is basically the kinematical reach of the muon collider. With this, we have some type of flavor protection, which allow us to see what electroweak Higgs and top measurements are telling us about the operators that survive the symmetry. Now, notice first that in order to define the symmetry, you first have to define what is the third generation, the direction that remains invariant under this U2 symmetry. And we take this third generation direction to be the one of the top quark. Okay? So, after choosing this symmetry, oh crap. So, we have a total of 124 operators that enter in the fit, but in practice, if you look at the observables that were included in the study, several of these operators only enter through renormalization loop mixing, and also proportionally to the weakest couplings of the standard model. So we neglect those, coming to a total of 84 operators that we include in the fit, together with all the standard model input parameters. That we impose at the cutoff scales of the EFT, which we run down using the one loop RG evolution down to low energies, the scales where we measure the different observables. We did that using only one loop RG evolution, which at the time this study was prepared was available in the literature. But later you will have a talk by Alejo where he will discuss recent developments, including the two loop RGs in the EFT. And after that, we compute the corrections to different observables using the MW-MC G-Fermi scheme, which is the one that is most commonly used also in LHC analysis. We truncate the dimension 6 contributions at the leading order at 1 over lambda squared, so we work consistently with the dimension 6 approximation. And in some of the observables, we also include the finite next to leading order pieces, in particular for the electrorepresentation observables and for the Higgs production, which brings the advantage of giving you sensitivity to interactions that you might not be sensitive to because you don't have enough energy, but you can see through radiative corrections, like for instance, the Higgs self-coupling entering through loops in Higgs production at the FCCE. Okay, this table kind of summarizes all the many inputs that we received from the different collider projects, starting as the baseline with all the work that Pamela and all the high-level people, the LHC people provided to set the baseline of these studies. And let me just highlight a little bit what we have in terms of electroweak Higgs and top measurements. For the case of the FCCE, as you probably know, and I already mentioned, first it will run at the set pole, which means that you could repeat all the program of electrovision observables. If you want to get an idea of what you could do, think that when we run LEP, we collect at the level of 10 to the 7 set bosons. At the FCCE or LEP3, you will be able to run the so-called TeraZ option, which would provide a level of 10 to the 12 or even more set bosons. At the WW threshold and above, at LEP you have 10 to the 5 W boson pairs, compared to 10 to the 8 at the FCCE. With these statistics, you essentially could achieve an improvement by 2 orders of magnitude in most of the electrorepression observables. And also by measuring the boson process above the WW threshold, you can also get information about things like anomalous gauge couplings. From the point of view of Higgs physics, we include the projections that are obtained, including production in Higgs Tralum for all the machines that were proposed to run at energies around 100 to 100, around 240 GeV, and also for those running at higher energies where the W boson fusion process starts becoming also important. We also include the projections computed in this channel. With these production mechanisms and the luminosity of the FCC, this gives you the level of 10 to the 6 Higgs bosons, which will allow to obtain a determination of the Higgs coupling at the level of 1 per meter, as we will see in a bit. And if we run at the 50 bar threshold or above, first by doing a scan of the 50 bar threshold, you could also obtain a new determination of the top mass, and also by looking at the differential information of the plus and minus going to TT bar, you could obtain properties like the top electroweak couplings. A little bit of extra information, because what we did was not just taking the inputs from the different collider projects, we have to do a little bit of messaging of those, because in principle, the projections that each of the projects prepared were using different methodologies, different assumptions for systematics, so it's not easy to compare them easily. So to do a more apples-to-apples comparison, what we did for the case of the Higgs projections was to take a common set of inputs among the ones provided by the different projects and recompute from that the projections for all the different colliders. Similarly, the electrorepression observables, systematics there play a very important role, and each collaboration made different assumptions. So what we did was recompute the projections for this, assuming a more common set of assumptions for the systematics, and anything related to theory systematics, we added separately. In this regard, we consider 2 different scenarios according to what we expect the precision for theory calculations will be at the time we build the FCCE. First, we include this so-called conservative scenario, which is what we think we can get to by using the methods that we use to compute these observables nowadays. Essentially, going to 1 extra order in perturbation theory. But in order to see what could be the actual target of these theory calculations to try to match experimental precision, we also consider a more aggressive scenario where we go 1 extra order in perturbation theory to obtain this type of projections. This, as we will see, has a strong impact in the interpretation of the perturbation observables. And also, aside from this, as I said, we also consider in the fields the standard model input parameters as floating parameters, and this is actually also important, and we float this according to the experimental precision provided at each of the different experiments. So with this, I move already into the discussion of some of the results, highlighting part of the things that were used to prepare the physics briefing book, starting from the case of Higgs physics. First, here, if you're interested in your favorite collider, you can look at the corresponding color code. As I said, I will focus mostly on the FCCE, given by these different shades of blue. This clear blue, if you run up to 240 GeV, the full FCCE program, and the combination of FCCE plus HH. And also, here is the high luminosity, which is what you have to use as a reference. In the left panel, we will have the results of the EFT analysis translated in terms of sensitivity modifications of the different single Higgs couplings. Here, if you look at the couplings that induce, let's say, the dominant Higgs decays, you see what I was mentioning before, that in principle, at any of the machines, as long as you combine the runs at two energies, one to around 240 GeV, and another run at energies typically above the 30 bar threshold, where you also become sensitive to double boson fusion, you could reach a precision at the level of 1 per million. However, if you look at the channels at the rare decays, here it is clear that even though future plus-minus colliders might bring small improvements with respect to the high luminosity, the high Lumi precision will be what remains until the time that we build the FCC-HH, where we can repeat again these measurements and finally go below 1%. But this is one of the results that will be dominated by the LHC and will stay like that for a long time. On the right panel, what I have is something similar for the for the Higgs self-coupling, which, as Pamela said, gives you information about the scalar potential, in particular about the structure away from the minimum. Starting from the roughly 30% sensitivity to this coupling that Pamela discussed, the FCC cannot produce or cannot see this coupling via Higgs production. It doesn't have enough energy. But it could see the effects of this coupling in single Higgs processes where it contributes through quantum corrections. In this situation, if you have measurements of two different energies, so you can disentangle the effects of the self-coupling from contributions from the other couplings that enter a leading order, plus information to remove or disentangle contributions from any other operators that enter at the same loop level, then with the precision of the FCC measurements, you would be able to improve the sensitivity of this parameter slightly below 20% in combination with the high Lumi measurements. This is a bit worse than what is expected at linear colliders, where by running at energies of 500 GeV and above, you could obtain a sensitivity at the level of 10%. But still, the biggest improvement in this regard will come from either muon colliders or FCC-HH, at which point you can measure this coupling at the level of a few percent. Moving now into the electroweak part, this BC plot, the upper panel is showing something similar to what I showed for the Higgs couplings, in this case for the interactions between the Z bosons and the different formulas. And without going into too much detail, this line is just showing you that the FCC in general could reach precision at the level of 0.01%, in some cases even beyond. The question is, what does this mean in terms of sensitivity to EFT scales? That is shown in this lower panel, which is a bit difficult to interpret because when you go to this type of interpretation, where here what I'm showing is the EFT interaction scale, the limit that you would obtain, the solid colors correspond to the results from the global fit, and the triangles, the results from the single operator fits. You see that these two are very different, which means that there are very large correlations in the fit. This is just reflecting the fact that this particular basis is not very well aligned with the electroweak measurements, which is why we chose this other representation to compare colliders, because the effective couplings is closer to what you're measuring experimentally. In any case, what you can see from this figure is that this 0.01% precision or better means that you have observables that, by looking at the single operator fits, could get sensitivity to new physical effects characterized by an interaction scale at the level of 100 TeV or above. But I also mentioned that the theory uncertainties play an important role in the interpretation of the electroweak results. To illustrate those, in this figure, what I did was just compile the results that you would obtain for the same couplings under the different theory scenarios. But let me just focus on a few of them, just to show here with these T bars what you would obtain with the conservative scenario, the solid color, the aggressive one, which is what we took as the baseline, and these empty little boxes is what you would obtain if you completely neglect all theory uncertainties. From this figure, first, you can tell that the conservative assumptions have a significant impact in terms of the precision that you could obtain in the interpretation of new physics. However, the aggressive scenario seems to be quite close to what you need in order to match the experimental precision of the different colliders. However, take into account that, as I said, this aggressive scenario means that we will be going from next to leading order precision for the electrical servos, roughly 2 loops today, all the way up to 4 loops. So that is actually quite challenging also in terms of the time that we have until this collider is here. Looking at the Higgs, I will not stop much here because the summary is that we are good. Okay, here, even in the conservative case, which is much closer to, for instance, if you look in terms of the production, would mean going to next to leading order. Today, we already know partial next to leading order results for the Higgs-Stern cross-section. And you see that the conservative and the other 2 scenarios are quite close. So from the point of view of Higgs, we are more or less okay. Doesn't mean that there will not be needed progress, particularly in Higgs-2-glu-glu, another type of case, but it's much more accessible, more reachable compared to the case of electroweak precision observers. Moving on to top, another busy figure. Here what I'm showing is, again, the bound on the EFT interaction scale from operators, let's say E plus E minus TT bar operators, or interactions that modify the top electroweak couplings, or the top Yukawa, in this case. Here is another place where, if you look at the results of linear colliders, you see some of the advantages of going to higher energies, as long again as you have 2 energies above the TT bar threshold. Going, for instance, to 550 and then 1 TeV. Whenever you get to 1 TeV, you see that you get better results, and that's because if you just have 1 energy above the TT bar threshold, you cannot disentangle the effects of, let's say, the operators that modify the electroweak couplings of the tops from things like 4 Fermi interactions. However, by looking at 2 energy points, you can look at the different scaling of the operators with the energy to try to separate the different contributions. Still, another thing that you can also see is that the FCC still retains very, very high single operator sensitivity to these operators, and this is coming from the electroweak precision measurements. And also, the last thing I want to highlight here is that if you want to measure the top Yukawa with significant improvement with respect to high luminosity, the best thing is again the FCC-HH, where this bound basically corresponds to something at the level of 1%. With this, in the last part of the talk, I want to discuss a little bit this scope FCC scenario and what is the impact that would have in the EFT interpretation. First, let me define what this scope FCC scenario is. As I said, this is driven essentially by trying to make the project a little bit cheaper, and it consists on removing the top quark runs, essentially the threshold and slightly above, also decreasing the RF power such that the synchrotron radiation power goes from 50 megawatts per beam to 30, and instead of having 4 interaction points, just get 2, and this would be the savings. Now, what is the impact on the results that I showed before? This is shown in this figure, where now the y-axis, what is telling you essentially is how much worse the result of the DSCOPE FCC is with respect to the original program. The first column shows the comparison of the FCC only, and this one, what happens if you also consider the combination with FCC-HH. But let me just focus on the case of the FCC discussion. You see, this blue line corresponds to the impact of removing the TT bar threshold run. What happens when you also lower the synchrotron radiation power and when you also subtract the 2 IPs, though these 2 could be actually interchanged because the only effect that they have is to lower the luminosity of the collider. What you see is that the removal of the top run has a strong impact in several of the couplings, but in particular, it has a huge impact in terms of being able to get sensitivity to the self-coupling. If you just run on 1 energy, as I said, then you lose any sensitivity to learn anything more about the self-coupling with respect to the high luminosity. Something similar can be seen in several of the other figures comparing the FCC with the DSCOPE case. As you can see, in some cases, the removal of the top quark run has the biggest impact for the electroweak operators. Part of this is due to the fact that you wouldn't be able to measure the top quark mass, which is one of the biggest sources of uncertainties in the electroweak field, but also that you are removing one of the highest energy that you have at the collider, and some of these operators are driven by the boson measurements at higher energies. On the other hand, if you look at the single operator limits, you see that the effect is much milder. And this is just a reflection of the fact that these bounds are completely dominated by the electroweak precision measurements, the TeraZ run. And here, essentially, instead of having 6 10 to the 12 Z bosons, you will have the level of 10 to the 12, so it's not a dramatic impact. This is obviously also what would happen for the case of the top physics operators. Then you lose the most by just removing the top quark run. But again, the single operator bounds remain very similar because the sensitivity is driven by the electroweak measurements. Putting all together, how does this COPE scenario compares with the other colliders? Well, essentially, aside from the removal of the top run, the other two items amount to reduce the total luminosity of the project by a factor of 0.36. What this means is that this could be a bit better than LEP3, but not much. Okay, so that is basically the impact of this COPE FCC. To conclude, I don't know how am I doing with time? Good. Then yes, I just have a few summary slides where I wanted to summarize the results of these EFT fits, also bringing a little bit of information from flavor, which was also key in order to decide for the FCC. And to do that, I will use this type of figures that we prepared for the discussion that took place at the Senate Council in March, where we tried to summarize the results of the EFT analysis in this type of circular plots. Essentially, each slice of this plot, what is doing is representing one type of EFT interaction. The color code of the outer rings, what they are telling you is what are the measurements that provide roughly the leading constraint on each of these operators. Now, each of these classes, of course, contain different type of interactions. So what we did was subdivide all of them in 2 or 3 sectors to add a bit more of granularity, where each of the sectors correspond to interactions that would be sensitive to one particular circle. For instance, here, for the His gauge operators, things that would be sensitive to His to blue, His to gamma gamma, His to Z gamma. Then, what we did was to take all the different colliders that were entering the comparison, and we take the high luminate C, which is the baseline, we compute what is the maximum improvement with respect to the high luminate C, and we distribute all the other colliders according to how well they do in between these two. Then, that distribution, then we map into a ranking between 0 to 4, which we illustrate in these figures using this grayscale. The idea is that by looking at those sectors where things are less dark or brighter, you would have more sensitivity to see what effects could be hiding in the corresponding EFT interactions. Okay? So this is the result for the FCCE, but the idea is to look at these figures side to side. And here what I'm showing is everything for circular colliders, the FCCE plus HH, the scope 1, and the LEP3. You see LEP3 again is not much different from the scope, but also you can tell that the scope of FCC with respect to the original project is significantly worse. But also what you can tell is that the best sensitivity in general is obtained when you combine with the HH. And this is because the FCC-HH combines all the precision of the FCC, but also with the access to very high energies, which is the other thing that I didn't discuss so much, which is the fact that for any EFT interaction, you know that there will be some process where the effects grow with the energy. So you also benefit from going to very high energies, as it is shown here in this figure, by looking at the bounds that one obtained in 4 Fermi interactions entering into 2 fermion processes. As you can tell here, the FCC-HH actually improves the bounds on this type of operators a lot with respect to FCC, making it comparable to potentially muon collider. Or in those cases where you're testing contributions to processes that are quark going to jets, there is nothing that can compete with the machine. So because of that, this shows the best sensitivity at almost all the different sectors. There are things like for electron operators where linear colliders can do a little bit better, and in general, that is also something you will see if you compare the FCCE with the high energy linear colliders. You see that there are places where linear colliders do better than the FCCE, but also in general, the FCC has more bright than dark than any of these options. And part of that, if you look, pay attention, it is coming also from the flavor program, which we didn't discuss at all during this talk. Okay. So with this, I just want to conclude. I'm not going to read the conclusions. They are long. And the only thing I wanted to mention is, okay, this talk was completely focused on the future colliders, but I also wanted to conclude the talk reminding of another conclusion of the strategy, actually the highest priority, which is that the completion of the high-limit problem is still the highest priority in particle physics, because I guess we all understand that the physics potential of any of the future colliders is great. It will require a lot of effort to make sure that the FCC becomes a reality, but we also need to make the effort to make the most out of the collider that we have today. And with this, I conclude. If you have any questions, please answer them. Thank you.
Thanks a lot for the talk and for the massive amount of work that went into this strategy. Please, go ahead.
Thank you for the very nice talk. I have multiple questions, but let me ask only two. So the first one will be connected to the last plot which you showed for the for this comparison of the scoped FCC versus other proposals. So your final plot in this topic. I wanted to ask.
This one?
No, the previous one. For the descoped FCC, you had this comparison for the operators. Yeah, this one. So if I get you right, are you saying that FCC EE descope does not really have many benefits as compared to Lab3 or LCF?
Is that a statement? Or
It's a question. Are you saying that here?
From the point of electroweak physics and Higgs physics, as I was saying, the descope is very similar to Lab3. Now, the descope is something that you will do if you don't have enough money to build the normal FCC. Also because even if you don't have money to go for the full FCC, you will still have the tunnel that later on will let you go to FCC-HH. So the descope FCC EE is a strategic decision that goes beyond the physics potential. Okay, but yes, your statement is accurate. This is not much better than Lab3 and comparable to the first stage of a linear collider, for instance.
Yeah, but I think the cost is comparable to LCF 550 of the scoped FCC, right? It's 12-13 billion francs. So.
But then you lose again the access to going to to essentially the 100 TeV collider, because if you go linear, you will need to do the linear tunnel and then also the 95 kilometer or the whatever kilometer tunnel for the FCC.
That's true, but I think for EE it's hard to get money for FCC-HH if you can't build FCC as a full project, I think.
Sorry, say it again?
I'm saying that it's probably hard to get money for FCC-HH if you can't build FCC-EE as the full project, right? If you're going with this scoped FCC-EE, it's
but if it is difficult to find money for FCC, then it will also be difficult to find money to the 550 GB collider. And the thing is, if you build already a tunnel for the scope FCC, at least that part you have already covered for the time whenever you build the FCC-HH. If you decide to go along the linear option, then you need to find a way to keep a long-term vision for the access to very high energies. So, but again, these are considerations that go beyond the physics potential of these machines. These are more like strategic decisions in terms of the long-term vision of the field.
First off, one thing to keep in mind is that for the descope, that means you're moving forward any future program by 3 to 5 years at the very least. So this is also part of the discussion, not just the cost. Suppose there were enough money, there would still be considerations for descoping in order to bring forward a PP program by 3 to 5 years at least.
Yeah, not only that, there is also the issue that, okay, part of the discussion about the scope FCC is that if eventually you manage to get more money, many of these descoping items could be reverted. Okay. So you could recover part of the original FCC EE program. So all goes together into. But you have also another question, right?
Yeah, I have another one more on the physics side. So if you can go to your slide 17. You mentioned that that different projects deliver different systematic uncertainties, and I think it's a fair thing because, for example, for LCF we have polarization.
No, of course, there are things that are common to all colliders and things that are specific of each collider. The things that are specific would retain from one.
Okay, so also systematics for polarized beams was preserved here. Okay, perfect. Thank you.
It was a fantastic talk. Thanks a lot.
Thank you.
Super clear. I think there was one thing that I saw in a different talk given by a different person, that it's not directly inferred. If you go to the last slides, because you compare the FCC with Lab 3 or the FCC with the linear collider in this nice round plot. But in reality, I think that if you compare the linear collider with the Lab 3 would do better.
The linear collider, okay. It depends, okay, because that, I mean, it would do better in some aspects, yes. Sorry, let me just make it clear. So you're saying if you compare Lab 3 with which linear collider option, because you need to specify the area.
Yeah, I don't know because I don't see them on the same axis.
Yes,
but I think nearly most of it. Well, in some aspects they will do a bit better, right? But
yeah,
overall the
area.
Lab 3 is better than, not the FCC, then the Lab 3 is better than the linear. This is what I want.
In some places, Lab 3 would be better than the linear, for instance, in the case of all the constraints from flavor. Those depend only essentially on the sensitivity, on the number of bosons that you have. In terms of this physics, then the discussion becomes a bit more complicated because it depends on what you compare with. The first linear collider option, 150. But yes, overall, I mean, if you keep in mind that the EFT is mostly flavor, then having access to a strong flavor program is also very important. So probably that's, I mean, I don't think I gathered in the backup all these figures, but okay, yeah, I mean, it depends on
question because I only saw the slides and I wanted to understand your figures.
Yeah. The flavor part was one of the main considerations.
Exactly, because
preserving.
If you look at the different capabilities in terms of electrode or Higgs, once you go to high enough energies, things are very comparable. But flavor is something that distinguishes the projects quite clearly.
Which then has implications on detector design, all that, so it's quite relevant. Anything else? Please, Luca.
Yes. Thanks a lot for the talk. I have one question specifically on the self-coupling, because you show that it can be measured indirectly from levels, but
I don't count it indirectly, but yes, I know.
No, okay, can be measured from single hits, let's say. But then I have the impression that since it's always combined with the Illumi LHC, the improvement that you get from E plus E minus is quite marginal.
Essentially, what you get is a measurement at the same level as the high Illumi one, which when combined brings this improvement. Yes, if you just take the FCC on its own, it would be at the level of sort of 30%, similar to the high Illumi LHC, which is why I made sure to highlight here that this result is in combination with high Illumi LHC, which also highlights the importance of the high Illumi result.
Yes, exactly. And if you hope that, okay, now we have the projection at 30%, we discussed already, could be a bit better. I guess also.
I know. I don't like to focus too much on the self-coupling because the self-coupling to me is something for the FCCH.
For FCCH.
Yeah.
Okay. Yeah, thanks.
But I mean, it's important to make this type of remarks because it shows the importance of actually, again, completing the high Illumi program, collect all the luminosity, because I kind of agree. I think you mentioned before, we would do better than this 30%. So.
It's the usual hadron plus electron positron synergies. Any other comments or questions?
That's one which might be silly. So in one of your plots, I see that the muon collider is compatible or slightly better than FCC. Do you have also the round plot that you made at the end for the muon collider?
Those plots were to illustrate the comparison of the last round of colliders that went to discussion with in the Senate Council. At that point, the muon collider had been already excluded because of other considerations. I mean, the technical readability, and we don't have an estimate of how much it would cost. So at that point, it was decided that the muon collider, it is not considered for this strategy. So I don't have them, but I could compute them. The problem also in the muon collider case is that several of the, and also of the FCCHH, is that we also don't have very comprehensive studies of the whole physics program that could be done in these machines. I mean, even at the high Illumi LHC, I agree with Pamela, we don't have a very clear picture of everything that could be done with the measurements that will be available with all the data. So all these results, I mean, just show a little bit to what extent we know information about these projects, but it is not showing what we don't know. Let me just put it like that.
We have also very clear cases like triple X. We still don't even have anything.
Yes.
Real projections for FCCH. Just thanks again.
Thank you.
continue with Daniel, because one of the challenges we had in the past was to find data sets where we could develop algorithms in a generic way, also within COMETA. So we have asked Daniel if he can tell us a bit more about the open data set and usage in CDS.
Yeah, thanks for the invite. It's a bit of a change of energy, a little away from the sort of high-level physics analysis. But here I want to talk about open data, in particular this open data set that we're working on with developers from ACTS and in general Atlas and CMS and FCC simulation and reconstruction experts. So I'm a member of Atlas, where I am the machine learning convener, and I spend quite a lot of my time working on tracking. But this is really not an Atlas talk. This is open data. And the idea here is that we're using these totally open software systems to produce data that can be used as a playground. So if you have some interesting reconstruction algorithm that you want to test out, you have some high-level analysis idea that you want to test out on realistic data, the goal is, can you do it? You know, could you have done it 2 years ago? I think it would be difficult. Can you do it today, either on Collider ML data or on Atlas or CMS open data? I think the answer is more optimistic. So the open data detector is not a real detector. In fact, that's kind of the whole point. It's never planned to be built. It's virtual, but it's realistic. I mean, the geometry description is in some ways as realistic as that of many FCC proposals, and Atlas and CMS. And it's compatible with the Key4Hep ecosystem, which is really nice. We use ACTS for a lot of the reconstruction algorithms in Collider ML, which is a framework that does any kind of tracking reconstructions that you need. And it's currently assumed to be adopted for Atlas Phase 2 upgrade, as well as Phaser and SPhoenix and some others. And then there's this particular open data set, which is kind of a tagged or frozen instance of the full pipeline of open data detector, Key4Hep, MadGraph, Pythia, blah, blah, blah. I'll show you the pipeline in a second. The idea is to really freeze these and use them as challenges, use them as benchmarks for reconstruction and analysis. So, okay, why produce a data set on a detector that will never be built? One reason is that there is no pressure to keep the data closed. It is open from the moment you produce it. You don't have to report to anyone. You don't have to ask for permission from anyone. It's quite modular. As of the last 1 or 2 versions, you can chop and change pieces of the detector. You can remove the calorimeter. You can add in a muon system. You can switch out pieces of the tracker. And of course, it begs the question, couldn't you switch out pieces of a CMS tracker or an Atlas tracker or an FCC module? And the answer is that is really the plan. It would be nice to be able to apply the Key4Hep framework to HL-LHC systems, and this is in some ways a step on that path, I think. And of course, hopefully anyone feels comfortable using this because it already uses a lot of the ideas from the CMS Phase 2, Atlas Phase 2, and FCC detectors. So it should feel kind of familiar, even though it's not any of those. So why full simulation? Why not do some large Delphi's open data release? They are out there, and they're very good, and you can produce more data from them in general because it's faster. But at the end of the day, if you want to build really large ML foundation models, there is early signs that they can start to memorize, especially fast simulation, if your simulator is not realistic enough. This is not an attempt to replace any of those fast simulations. And indeed, you might have a foundation model that trains on both full sim and fast sim, and I can talk about that in a minute. But if you're interested in producing low-level data, tracks, color clusters, raw hits, cell deposits in the calorimeter, you have to do this with full simulation. And that begs the question, why low-level? Why aren't we just feeding high-level objects into our machine learning models? Well, hopefully last two talks have convinced you that ML is improving sensitivity and reducing uncertainties in a lot of reconstruction and analysis tasks. Flavor tagging is kind of the poster boy of that trend. And the assumption is, as you go to lower and lower level, there should be more and more subtle clues of Higgs, di-Higgs, BSM physics that you can detect. And even if you draw a line philosophically and say, okay, we shouldn't go below clusters, we shouldn't go below tracks, it doesn't make any sense, you can factor out those things. It still begs the question, well, what is the best representation of a track or of a cluster? And I don't think anyone really believes that we have absolutely the best representation today for what those objects are. And so we should study, how do we represent them? How do we tokenize them? How do we patchify them? These are all concepts that are really open questions in large ML models. So, I mean, could you go from the lowest level directly to a bump hunt? Almost certainly you can. Of course, that might be a very, very inefficient way to do your physics search. But then what do those intermediate objects look like? And so the idea is we would like to present a full open data set that includes all of these objects. And so you can study which one is best. So the current kind of landscape of open data looks something like this. I guess I made this maybe a couple months ago, so it might even be already out of date, but broadly Atlas and CMS have done really great work in releasing huge open data sets that are, you know, as of 2026, pretty easy to access. But of course they skim a lot of the physics in that data set. They don't release all the low-level data. And so in this kind of taxonomy, we're calling these kind of medium level. If you're lucky, they include tracks and clusters and things down to that level. And then there are some slightly higher level objects that are also either derived from Atlas or CMS data or produced from scratch. And then there have been traditionally some less effort spent on releasing very low-level data, in part because it requires full simulation, which is very expensive, but also the infrastructure just wasn't there. So that's kind of this quadrant of the plot that we tried to patch. So as of right now, this is the state of the data set. We have some standard model channels which are available at PyLab 200. So this data set is quite explicitly targeting high Lumi LHC. And then we have data sets that are for PyLab 0, but then also include dedicated PyLab channels, so you can roll your own, or you can mix and match. So the goal here is that we simulate actually PyLab 200 completely from scratch. So PyLab 200 parton generation goes in, and the full simulation happens. This is wildly inefficient, but it means that every PyLab event is totally unique. So there's no way you can memorize from one event to another, which we are starting to see in some large ML models. So you can pip install this already and load them. They're on Hugging Face. These are the objects that are available now. Your favorite object might not be there, but it should be soon, and I'll talk about that in a second. So here's the full pipeline. It looks a little messy, but it's actually not so complicated, and in general, it's quite a bit less complicated than a typical in collaboration pipeline. So we start with parton generation, which is all standard state-of-the-art, MagGraph, AMC, and NLO. We include some BSM channels there. The goal there is we want to enable things like long-lived particle studies. Here, Higgs portal has a long-lived particle that you can do your large radius tracking on, for example. Z prime is an interesting bump hunt channel. Hidden Valley has interesting missing jets, missing energy. So these are kind of challenge data sets that are all available at low level. And then we have kind of standard candle, Drell yarn data sets, and then some nice Higgs, di-Higgs, and TTH data. So this is not very controversial. Maybe the one kind of novel thing here is that the typical process for including pileup, say in Atlas and CMS, is you would produce your hard scatter event and then you would overlay your pileup. Makes perfect sense if you want to make 1 billion of these events. That's kind of the only economical way to do it. But it means that if you're not careful, your big fancy ML model will see the same pileup event multiple times. It might even end up in your training, validation, and test, which is kind of the original sin. You shouldn't do this, right? And so the whole expensive thing with producing these pileup 200 events is that every pileup sub-event, every pileup interaction is completely unique. And so in reality, even though there's only, say 100,000 TT bar events, they include, 20 million interactions in them that are unique. And then we generate a kind of realistic finite beam spot, and then we simulate. So we simulate with this open data detector geometry description. It's the tracker is kind of inspired by the ITK, the Atlas upgrade tracker. The eCal and HCal are kind of inspired by HGCal of CMS, a little bit of FCC detectors. And again, we have this kind of Frankenstein's monster 3 Tesla solenoid, which is somewhere between Atlas and CMS. So the physics should somehow be an interpolation between those two. The tracker is really quite realistic. Most of the team are tracking people, so a lot of effort goes into this, and it uses all of the same machinery in ACTS that goes into the Atlas tracking system. So it has wide coverage up to 3.5 ADA, ample layers, pixel strips are realistic. The long strips are also sort of like Atlas and CMS kind of 1D strips that need to be resolved into space points. So all of this is quite realistic. And you can see that in general, the sort of scale of the data per event is similar to an Atlas event. So in an Atlas event, you have something like 350,000 tracker clusters. In ColliderML, you have something like 250,000 tracker clusters. So it's a big data problem. If you want to throw a transformer at that, you have to work really hard to make it fit. And that's kind of the point. It's challenging. The calorimeter is a little bit less developed. I mean, the geometry description is realistic, and it's more or less a port of some FCC detector proposals. In particular, the eCal is a silicon sensor. The HCal is scintillator cells. And we have some simple digitization that we have on this first release. But the full calibration, full digitization depend on having good particle flow, and I'll talk about that in a second. So then we actually digitize the tracker. We do this with a very similar system that is done in Atlas, which is this geometric digitization. We actually figure out where the energy was deposited in the pixels of the tracker, and then resolve that into modules. And then we reconstruct tracks. All of ColliderML is, if you excuse the ML in the word, it's not using ML to do the reconstruction because we want to provide sort of traditional baselines. We want, the community to come up with their ML methods and beat these baselines. So we use traditional tracking here. We have a combinatorial Kalman filter that extends these seeds and provides fitted parameters, and then does a fairly realistic ambiguity resolution. So we get quite high quality tracking. So for example, here's the tracking efficiency, the technical efficiency, which is comparable with, say, Atlas CMS tracking efficiency at pileup 200. So this is kind of what you would expect to see in Atlas CMS, for example. And then the, the big open question mark is these missing pieces, particle flow, jets, and kind of event level. So right now you can get what we call release 1, which is the low-level objects and sort of a first set of data. We've partnered with Hugging Face to get this data out and to actually benchmark how you can release this kind of data in a sort of industry system rather than a sort of CERN-owned system. And they've given us quite some nice hands-on help with breaking up this data into something that's very ML friendly. And it is ML friendly. So already there are groups using this to do some quite fun machine learning applications, as well as traditional reconstruction. So of course the tracking is all quite state of the art, so that's a nice place to test ML. But also because it's full simulation, you can train your generative models on it. I'll show in a second the particle flow, which of course it would be nice to be able to beat with ML. And then detector optimization is one thing that I mentioned, where you can modularize the open data detector and potentially improve precision, improve sensitivity to your particular search. So one thing that we showed last year was you for sure can implement machine learning based tracking. For example, this GNN for ITK pipeline, which we developed for Atlas tracking, can be applied more or less out of the box to Collider ML. And just as a proof of concept, because Collider ML comes with all the sim level timing, you could say, well, what if you had timing on some of the layers? What if you had something that looked like a high granularity timing detector? And indeed, we can do this. We can smear some of the timing on the outer layers, and you can kind of emulate what a HGTD would look like. And then you can do, quite realistic track reconstruction studies, including or not including this sort of timing. So you can play around with different configurations of the geometry and test these kind of ML reconstructions. Of course, in some sense, like a holy grail is, can you go directly from low level to tagging? This, again, just a proof of concept, is can you do Higgs tagging based on track level and cluster level objects? And it should come as no surprise that if you include lower and lower level objects, then your Higgs tagger improves. Of course, it's more expensive. Your model has to consume not just 10 objects per event, but maybe 100 or 1,000 objects per event. But it does show that these kind of studies are possible. So what is missing? The muon system is now there. It's still being validated, but it is at the moment quite expensive to simulate for reasons we don't quite understand. There is some large punch through. A lot of particles get through the calorimeter more than one would expect. And so they reach the muon system, and that needs to be simulated. And these tubes are quite expensive to simulate. So it's there, but there are some tweaks to be done. But the nice thing is that just even having a muon system means that Pandora now can consume the ODD. That was kind of the missing piece. So to my knowledge, Pandora, which was not produced for high-Lumi LHC purposes, far from it, to my knowledge, it has not really been tested thoroughly in a high-Lumi environment. There was some work, I think, in CMS to see if it was a possible algorithm suitable for HGCal, but I think it was generally agreed to not work, and then Clue was preferred. But what we're seeing is that actually with enough tuning, it might be possible to have Pandora working okay for a high-Lumi collider or high-Lumi detector. It needs to be tuned, of course, but you can see that generally at energies above 1 GeV, these particles have pretty good resolutions. It works, the jet response is decent, and it, of course, gives you not only particle flow objects, but also calorimeter clusters, which you can use for your machine learning algorithms. and the point is, of course, we don't want to produce an absolutely awesome jet resolution, because we want people to come along with better ML models that beat these jet resolutions. But it is already decent without too much tuning yet. It's extremely slow. I mean, Pandora was not built with HiLumi in mind. It runs at something like 50 minutes per event per thread, because there are a lot of sort of triple for loops that were not written with this kind of system in mind, but it could be quite significantly sped up. And then there's still a bunch more fun things to do. I mean, you could re-simulate these events with Delphis and then provide both a fast sim and a full sim view of the exact same parton generation, train contrasted learning or some self-supervised model on to convert between fast and full. Diagnostic channels, a lot more data. At the moment, it's kind of order of 1, 2, 3 million events. Of course, it'd be nice to have something more like 1 billion events, which is perfectly conceivable with pilot overlay. And then having a system for people to be able to contribute their models and contribute their algorithms is I think, key. So one thing you can already do is run these simulations locally. As of the last few weeks, you can import ColliderML and run ColliderML.simulate whatever you want to simulate. And it pulls this full pipeline as a Docker container and does this in Python. But of course, not everyone on their laptop has the capacity to simulate millions of events. So we would like to offer simulation as a service with the NERSC Super Facility API. Begs the question, who's going to pay for it? And the initial idea we have is to offer credits, where as a user attached to your Hugging Face username, you have some credit account. Maybe one credit is, say, 100 pile up 200 TT bar events. How do you get credits? Well, of course, you need to post high-quality reconstruction algorithms or analysis algorithms to the leaderboard. And if your algorithm is good enough, you receive credits. Hopefully, this creates a sort of virtuous loop where people are incentivized to produce better and better models, better and better algorithms. I mean, a lot of this is based or inspired by the original TrackML challenge, which some of you are probably familiar with, which had this very nice idea of a TrackML score, one number that captured tracking. That's not probably possible for all Collider tasks, but still having some agreed upon cross-collaboration, cross-project metrics would be very nice. And I'll leave it here. This is available today, but there's still a lot to be done, and I'll say thanks.
Thank you. Very interesting. Questions or comments? Many. I'll start from Richard.
So, quick question. This is really, really cool. This is really exciting. So, putting on my BSM hat, I have a load of UFO and BSM models that are used heavily in the LHC environment, and I would happily volunteer my time to push in some of these BSM models, heavy neutrinos, extended Higgs sectors. How do we need to chat with you individually, or is there already information to contribute to this?
Yeah, there's a missing piece here, which is the community element, which so far has been kind of, internal locked off Mattermost channels, which is not very sustainable for like community input. Probably the way to do it will just be some GitHub discussion forums, but in the case of, really hands-on taking UFOs and producing large BSM datasets, that probably still should happen kind of one-to-one for now.
Okay.
But maybe it's a test case of how to do it more generally.
Yeah, I had a similar question to this. Let's say, for example, that I want to do some study that doesn't need only PTL, but also some other generator, or to try, calibration. Some network that could auto-calibrate, for example. So would it be possible to also, or is there some view in future where people would sort of, let's say, develop part, because you have this nice chain where you sort of put each thing into their own box, so assume that each box is sort of modular, and someone can contribute to developing some part of the code in there, but also in the end they will produce a new data set. So would this also be like open data set, not in the sense that people can openly use it, but also openly contribute by using their CPU time, generating some samples, and possibly then putting it as another part of the big data set.
Yeah. Okay, so there's two questions there. I guess the last question is kind of about how the data propagates and stays open. The idea here, at least, is like if you use the sort of collateral credit system, any data you produce will automatically be pushed to Hugging Face for other people to use it, right? So it's kind of open from minute one. Now, if you want to, of course, embargo it so you can do your studies yourself, that you would have to do it kind of on your own money. But the first question, I guess, was about the modularity. For sure, this needs to be more modular, in part because Pythia is not actually appropriate for some of, I mean, for example, you can see we have gluon-gluon fusion for Higgs. The vector boson fusion, we've been told in MagGraph and Pythia, is there's some bugs, actually. And so we need to switch, if we want to do VBF, we need to switch to some different generators and showering. And so we want this to be modular as well. So yeah, yes, it should be modular.
Just a quick question, follow-up. How many people are working on this? Because this is a big project.
I mean, define working. I mean, there's probably 16 people that would put their hands up and say, like, they're doing it. Yeah, let me say that.
Thank you.
Was one more question. But this was similar in spirit. So the question was about when I have a particle level sample of my favorite particle shower hybridization model. Can I just provide this to you and you do the detector simulation, etc.? If I would, for example, be interested how an uncertainty propagates to simulated data?
Yeah, I mean, a lot of the work that went into this was not like the pieces themselves, but how they talk to each other.
Sure.
So ACTS didn't know how to talk to EDM for HEP, and EDM for HEP, like DD for HEP, was struggling with some of the FMC inputs. So a lot of the quote-unquote pipeline is really just us making sure everything can consume the standard formats. And so, for example, you can, for sure, plug in, you can kind of bypass this. You know, if you have, some partons already generated, they can be passed directly to Pythia. Or if you already have FMC files, they can be passed directly to DD for HEP simulation. And from then on, everything else follows. So that's all kind of plug and play. Making it super user-friendly is still to be done. But again, like the UFO case, having test cases like this makes the next person easier, even if for you it's a bit of a headache. Yeah.
Thank you.
Yeah. I have a short, very practical question. Let's say I want to use this data set. How big should be my infrastructure? Like how much memory I need to download it or to load it?
You can generate something like 1 million Pilot 200 events with around 10,000 node hours. In our case, COMETA has 128 cores, so it's something like 1 million core hours to make 1 million. Okay, it's kind of a nice one-to-one mapping. 1 million events, 1 million core hours. So it's expensive.
Yeah, well, I don't have to generate them, so I'm really referring to the dataset you published.
To actually just get the data as is.
Yeah.
It depends if you wanted to download the whole thing and have it sitting on your laptop, then it's something like 30 terabytes, Parquet files. That's because, of course, you have tracker hits. Every calorimeter contribution is in there. So if you only want to do dedicated studies of VAX clusters, particle flow objects, I mean, it's orders of magnitude smaller. Yeah, it's big. Of course, it opens the question of, are we really, I mean, is that the future? Are people really going to download 30 terabytes and have it sitting on their machine? Or are they going to train on the fly? And because this is what Hugging Face is really set up for, and they do some awesome throughput. You can load in, 10 gigabytes at a time, all set up nicely with your PyTorch data loaders, and then throw it away. I mean, this is what the LLMs are doing, right? They only see each token once. You might have a situation where you only ever see one particle flow object once, or one tracker hit once. So it doesn't make sense to save it locally, right? Yeah, you just need a high throughput downloading speed.
is this Hugging Face connected to some services like Amazon or something like this, where we can have like very high bandwidth to it? Or?
That's a good question. I actually don't know what their backends are.
Okay.
Probably, I mean, they're smart people, so there probably is some high bandwidth connections. Yeah. Yeah, we should ask actually. Yeah.
Because it would be maybe the easiest entry point, right?
If you already have your training code or something set up on some cloud infrastructure or HPC or something, yeah.
Anything else? Maybe going back to the previous question about special physics cases that we have not considered before, can you comment, Daniel, a little bit more on large radius tracking? Is this something you have available, or is it more on the developer side to try algorithms for LRT and then have the physics models attached to it?
So the data is there, right? So there's these Higgs portal that they have a lifetime of around 8 centimeters or something. So they're really a nice, challenging large radius sample. Out to that distance, Atlas at least is like pretty inefficient, even with the dedicated large radius tracking. I don't know what it is, 20%, 30%, maybe more, 30%. So if you beat 30% on that data set, you're already in the contention for like really, you know, significantly increasing sensitivity to a very well motivated ESM scenario. On the ML side, I mean, for sure we have some ideas like that, the GNN5TK approach, where you build a graph and you try and find your large radius tracks with the graph approach, does work, and we have some early studies, you know, inside Atlas, but it's probably not ideal. Actually, having some kind of end-to-end transformer-based approach is probably more promising for these large radius signatures.
Okay.
Which maybe some people, maybe or maybe not, some people are already working on.
So in that sample, you do have displaced tracks, but then one can still develop the algorithm to improve that. That's what you're saying.
Yes, exactly. So because we're just using these primary tracking, the kind of baseline for those is pretty bad, right? I mean, it's 0% basically. This system cannot find large radius tracks as it is currently. The seeding and the tuning is not tuned for large radius tracks. But I see your point. It would be nice to release dedicated baselines.
Maybe just a baseline, yeah.
Yeah, good point.
All right. If there is nothing else, then thank you, Daniel. Thank you to all the speakers.
Okay, it is 31, so we already given you 1 minute to skedoodle in. Before we move back to the short scientific talks, we still have a wonderful little session on things that are adjacent to actual basic science, which is, you know, being inclusive in basic science and communicating basic science. So we'll start with the Working Group 5 update from Flavia, and then for those who were here in the outreach event, there's an extra outreach for you, again by Freya.
I wouldn't label it as an outreach event.
It's outreach to them. Is it InReach?
It's InReach.
It's an InReach event for you.
Outreach training might be off.
But yeah, anyway, without further ado, Flavia.
Thanks a lot. Oh, hello. Welcome back from lunch. This is going to be the report on the Working Group 5 of COMETA. I'll tell you what is the Working Group 5 and what are we doing in here. So the first thing, the Working Group 5 of COMETA is inclusiveness and outreach. So according to our Memorandum of Understanding, encouraging public awareness of fundamental research in particle physics, improving gender balance in the field, implementation of inclusion policies. The work group leaders are myself and Carlos, and we also have a science communication coordinator who is Richard. And then we can see here some of the places where you can reach us. And within COMETA, we have 89 members on the Working Group 5. Now, what are the goals of this working group? On the outreach side is to engage and communicate to the public about all of the motivations and the outcome of our action. So this includes communication to the public, dissemination to the scientific community, and also valorization, which is about societal, economic, and policy impact. And we also want to, in the inclusiveness side, monitor and ensure the diversity and inclusion in the action. And in this case, in the case of the EU cost actions, this includes geographical spread, especially the ITC countries, which are the inclusiveness target countries, gender balance, and career stage. So to start with the diversity statistics here, for the geographical diversity, this is our statistics on the inclusiveness target countries. So the total number of COMETA members is 342, and we can see it here, the plot of how many of those are non-ITC. So we have about 63% non-ITC and about 28% ITC countries. And then we also have other things such as the near neighboring countries and international members and things like such. And we can see here a time evolution of the ITC and non-ITC members. You can see over time we are increasing as a network, so we have more and more members, and the fraction of ITC countries is now a little bit stabilizing there. There's a little bit of ups and downs. We had more ITC countries in the early on, but then the more that we be going, that this has been unbalanced a bit. So for all of the actions in cost, normally this fraction of ITC is about 50%. So we are not doing as the benchmark on this target in particular. The second thing is the age diversity. So the EU has this young researchers and innovators category, and they categorize this as people who are aged younger than 40 years old. So you can see here that members by age, we are very young. In all of the actions, on average, they are 45% younger than 40 people. We are 65.2% younger than 40, so we are very young action, and I think this is very nice. Some of us will be out-aging the young researcher innovators soon. This is my last year where I am part of this. But it's very nice that we also have a lot of PhD candidates and master students who are also part of COMETA, and I think this really is beneficial for our actions. Now, for the gender diversity, here is the percentage of women, in this case in the binary definition, which is not ideal, but it is what we have for this statistics. So we have here that we have about 28% women in COMETA, which is less than all of the cost actions, but you have to remember, all of the cost actions is across all of sciences, not just physics. And then when we compare this with other benchmarks in our field, so for example, the CERN 2025, it's 16%. If you count only STEM, of course, they have the 25 by 25, but then include the non-STEM careers on this 25% benchmark. And Atlas, as of 2025, we are about 24% women but if you count only under 40, that's about 28%. So I think we're doing very well also in terms of the gender, considering the field that we are within the range of Atlas under 40. We also have statistics on the STSM grants. So STSM grants are the grants that you can get within COMETA to go visit a scientific institute and to make some work with some collaborators in other countries which are related to COMETA. So the total number of STSM grants granted so far have been 46. And we can see here, those figure of merits here are from the number of grants, but if you do similarly for value in euros, it's very similar. So we have about 40% of those STSM given to women, about 26% from people coming from ITC countries, and 80% to young researchers. And if we look to the second kind of grants, those are conference grants. So this is to do dissemination in conferences from COMETA subjects, and those have been the total number so far of 32, of which almost 90% have been men. So, but the thing here is that we have way less women actually applying for such grants. So please, if you want to go travel and disseminate, and you're a woman, apply more for those such grants. And then for those conference grants, about 25% have been to ITC countries, and almost 90% to young researchers, which also makes sense in here. Now some statistics about some of our meetings. I'm not going to go through every single COMETA meeting because there's a lot of them, but I like to show what the general meetings. We are right now on the third general meeting. The first one was in Turkey, in Izmir. So we had then 58 registered participants, of which about 30% were women, 32% were ITC members, and we have about 75% people under 40, which were the young researchers. The second one, which we had last year, was in Krakow. And then there we had 52 registered participants, of which about 30% were women, about 30% were also ITC members. In this case, we were not tracking people's age, so we knew that we do not know exactly how many were the young researchers, but we had about 20% of PhD students. And then we are right now here in Stockholm with 65 registered participants, of which close to 34% are women, about 17% are ITC members, and 23% are students. So this is the general statistics that we have for our general meetings. We also have the COMETA schools. So we have one school a year, and all of the schools that we have planned so far were held in ITC countries. The very first one was in Latvia in 2024, and it was the Baltic School of High Energy Physics and Accelerator Technologies in August of 2024, of which we had 30 students participating, of which half of them were from ITC countries. The second one was the Machine Learning for Physics School, which was held last year in July in Slovenia, in Ljubljana, where we had 54 students, of which 22 were coming from ITC countries. And then you might be wondering, where is this year school? And this year school is going to be a school on multi-boson physics. Is going to be in the end of August, early September in Split, Croatia, which is a beautiful, beautiful place, in case you do not know. And the registration is still open until June 7th. And so if you have any PhD candidate who are working on multi-bosons and they want to spend 2 weeks learning a lot of very interesting stuff in Split, please ask them to register before the 7th of June. Advertise this widely, it's going to be excellent. We have also, in terms of dissemination, we have a new CERN Docs website that you can see here, a screenshot, how it looks like. And our website is the focal point to communicate with experts, non-experts, and the general public. And if you see here all the things that we have it in there, we have all of the links to all of the colloquia, for example, all of the events that we've had, the travel grants, publications, newsletters. It's really nice. So if you want to learn more about COMETA, go to our brand new website. We also have active presence on social media, purely due to Richard's efforts. So thanks a lot, Richard, for this. We have several platforms with varied degrees of activity. So we have a YouTube channel, a Twitter account, a Facebook, and a Blue Sky. And
also a LinkedIn account, but it's inactive.
Sorry?
A LinkedIn account as well, but it's inactive.
Yes, we also have a not so used LinkedIn. And then here we have this very nice API, which you can show here how it works. But then there's a cron job that can make things being posted here and there by themselves. So that's very useful. So if you have, for example, a paper that you put the COMETA tag on it, it gets into our all of our social media automatically via this API, which is very nice. We do not have analytics as we used to have in the past, because you have to pay for premium in order to have this on Twitter. And we will not enter into details, since this is being recorded, of why we refuse to give money to Twitter.
We should talk, there's ways to do it.
We also have a COMETA publications database. So all of the publications produced by members with scientific pertinence to COMETA, such as papers, proceedings, reports, theses, talks at conferences, poster, outreach talks. We can have a COMETA the year a number report number. So the way that it works is that you have instructions in our wiki, but you can also send an email to us from the Working Group 5. We go into the spreadsheet and then we give you the number, and you can see here that 2025 we ended up to number 52 output, and then for 2026 we are at 2608 so far. And then if you do have some archive paper that you're about to submit, please ask us, and then you can add the report number when you submit it into archive, and then you also have this automatic spread to all of our channels and social media, so more people can get to see your paper. So that's good for you as well. We also have outreach events, which are always coupled to COMETA meetings. So those are planned in advance with the local organizers, and they will try to strive to be hybrid between informative and very fun. And of course, some of you were here yesterday for the very excellent talks that we had about the Nobel Prize. and about understanding the Large Hadron Collider. You can see here some of the preliminary pictures I took with my phone, which are not as good, but we do have our photographer at large who will be sending way better pictures later of this event. So we also had similar outreach events in all of our other general meetings, for example, which are also normally very well attended and very appreciated by the local community as well. We also have a newsletter, which has once a month you get a summary of all the key happenings in COMETA. For example, publications, upcoming events, job openings, advertisements for grants, and abstracts, for example. And if you want to be into the newsletter, you can fill this form. If you check these slides, there's like a link for a Google form, and then you just fill a few things that you want, and then it gets into our newsletter. And I would like to thank all of our editors, Mohamed, Marin, and Stefano, for doing an excellent job. So thanks a lot. Let's give a round of applause for our newsletter folks. And then if you want to be on the newsletter, you can also send them your information or go into this form. It's very nice. And I read it every month. I hope everybody does. We also have our colloquia series. So those are virtual colloquias, which are about to be inter-working group activities. They are supposed to be interesting and understandable for the whole community. They happen once a month. And I would also like to thank our colloquium committee, with Nicole, Jaco, and Mikael. And they have been organizing these colloquiums now for the past year, and it's been a lot of very interesting things that we've had. We also have some statistics on the colloquium. So this is the current topic distributions. If we do this between experiment, machine learning, AI, and theory. So you see here that the theory now is a little bit more than the others at this point, but this also fluctuates a bit. This is from all of them. As of last year, for example, theory was in the minority. So I guess we are still trying to overcompensate a bit that the theory was under a third last year. And we can see here the number of colloquium live attendance when we have on the Zoom room. So normally we have between 20 and 50-ish people attending online. That varies a little bit, but also afterwards it goes live into YouTube. So afterwards, all of our colloquia go into our YouTube channel, and then some of the most viewed, then it gets more than 100 hits each afterwards. Sometimes we get a little bit behind on the actual uploading to YouTube, so there's a couple of colloquias there which are not quite uploaded yet, but we are trying to make this a little bit quicker turnaround. And also the videos are reposted to social media every Thursday, so there's always something ongoing.
Another cron job.
Another cron job that happens for all of our YouTube channels. So if you missed the colloquia that you wanted to check our YouTube channel, and then you can go and see it again. This is a screenshot from my own YouTube, and you can see that I watched the Sally Dawson's myself, because you have the little red bar here of how much I have actually watched this afterwards. And as upcoming speakers, so we have here the list of the colloquias that we had for 2026 and their titles, but they have two upcoming speakers. One is Johnny in June 22nd, and then we have Gautier also on July 27th. So stay tuned for when the actual titles are going to be announced. And there's also an ongoing satisfaction survey about the colloquium. So those are very, very preliminary results, but you can see here that I'm not sure, yeah, this is large enough. The first one is, how satisfied are you with the COMETA colloquium series? And you see here, most are between 4 and 5, which are very good. And then how satisfied are you with the selection of topics? People also seem to be generally satisfied with the topics. Most of the people learn about the COMETA colloquium series via the mailing list. So if you're not part yet of the COMETA as a member, you can go and register. And then you can be on the COMETA all mailing list, and then you get to learn about the colloquium. And then what type of speakers should we focus on? And a lot of people here says that the current selection is fine, which we also try to strike a little bit of balance between more senior people, a little bit more junior people, and have like a good diversity on the speakers as well. And now to finalize, we want to, as Working Group 5, we want to continue to work towards our goals. So thanks everybody who have contributed so far. And we also also need you. So send our information for your COMETA newsletter. So check the form if you have anything that you want us to spread the word about. And we would also always happy to have volunteers to help organizing outreach events, disseminate our results, and spread the word about COMETA. So if you are interested in that, you can always send us a message, and we are happy to integrate you into our working group. So with that, we would like to thank you.
We definitely have time for questions, which I know you have plenty. You're just shy. Correct?
I have to admit I am not so familiar with European diversity jargon. So what is an ITS country?
ITC, so it's the... where is it?
Inclusive target country.
Inclusive target country. So
yeah, no, this I got because you defined it, but you didn't say which countries it was.
Yeah, so this is a definition that includes mostly Eastern European countries and
low
Portugal.
Resource countries. Low resource countries. So everything, including Eastern Bloc, but also some of the Mediterranean countries, Cyprus, for example. These extend to the nearest neighbors, including Turkey and Israel.
As Flavia said, it's mostly the eastern side and Portugal. They kind of sandwiched Europe.
And so the idea is to essentially compensate for the availability of resources in Northwestern European countries.
Yeah, oh, I support these things. I just didn't know who they were supporting. That was.
Questions? Yes.
I have a question about the age division you showed at some point. I think it was slide 5 or something. Do we have some benchmark for this? I don't know, the whole CERN community or something similar, because I'm curious to see the benchmark, not only for COMETA, but in general in our community.
Yes.
Because I think this is a kind of a global picture of the community, right? More than the COMETA. So I'm curious to see if there is a difference with respect to the whole community.
So for CERN, I'm not sure where we would see this data in particular for all of the users, but within experiments, when you have the plots with the statistics of the population of the experiments, you can find that information, which is how I knew, for example, the benchmark for gender, that how much was it for under 40 for Atlas. I put the Atlas numbers because this is something I'm more familiar with. CMS, I know for sure has the same kind of statistics and benchmarks, and also the other large experiments at the LHC. So this is something that at least from the experimental communities we can have the benchmark.
CERN also has in their annual report a whole section.
But is it just the CERN staff or users?
The breakdowns are not clear, I know, because it's in tables, it's not.
But on that note, it is definitely retrievable from CERN, provided you give a good reason, because they happen to really pride themselves in that pyramid they show of the 27 being the mode, age for CERN users, so they definitely have that information available. Any more? We have time? Yes.
I might have one which is borderline a proposal slash a question.
Yes.
For the outreach part, do you have plans for like making schools of science communication also to integrate with, I don't know, social medias and stuff to create content? This ugly word, but you know, to also teach how to speak and create something like that.
Well, it's a very, very good topical question, because no, but we have Freya with the next talk, which is kind of exactly
introduction. It's the first half hour of a standard media training. You get that in university.
Yeah. So it's a good point. No, we don't really have plans right now, because it's not necessarily something that COMETA can really carry. We already have things to do. But
in principle, someone could propose it for a workshop. In principle, I mean,
oh yeah, in principle that is possible.
If this is something really what people want to do, then we will, of course, the core. This would be proposed, submitted to the core group for discussion, and if there's popular support for this, we can treat it like a meeting.
Yeah. So something that Flavia didn't go through but mentioned. Flavia listed the schools and general meetings, but there are many smaller meetings all throughout the year, and Working Group 5 has not had one, so actually maybe a good point.
We could. And yeah, I know now there are other in other countries, they're having more and more of this kind of training. So for example, at NICAF, we had a workshop for training for science communication and media training, which was offered for PhDs and postdocs. which happened last month. And it was like kind of like a first of its kind at that level in the Netherlands, and it was very well received. So the idea is to make the first one, and then we can have more after you see that it's well received and well attended. I'm sure other countries are starting to look into this more.
Practically every university has media training as part of their doctoral school. So typically you just need to look at all the too many points that you can get in ETCS for your doctoral program, and it will be one of the ones in there. If you're a PhD student, for postdocs it's much more complex. There are things like what Nick offers is really great. CERN also offers one. It's very, very good. It's expensive though.
But if CERN offers something, then maybe this is something we can discuss seriously as a workshop.
The CERN version is for 10 people every half year, and it costs 3,000 per person or something.
Per person?
I've done it. It's very good.
I'm sure it is, but...
Well, it better be.
It better be for that money, I agree. But this is like the media training that journalists also get. So they have like people who, like the trainers are on the BBC News. That's the level. So this is maybe not where you want to start.
Okay,
So I have something to... So yeah, I have done that one as well, and it is indeed expensive, but sometimes you can get it for free if you happen to be in some certain role.
That's true.
So, and you know, obviously this will be more related to things that CERN is like, you know, proprietary, let's say, like if you are like outreach coordinator.
So we could reach out and see if we can have...
But maybe it's kind of fun.
It's a good idea.
But maybe if NICAP has such a strong education outreach training, maybe we can look into having a meeting, a workshop at NICAP, or a working group 5 workshop, working group 5 oriented workshop to organize something for next year.
Yeah, for us we have one of our professors. He's a professor in Leiden for science communication, so he spends part of his time with doing this. We also had Clara Nellist, who does a lot of social media and outreach. So we had quite a few people who are embedded with us who can help also giving this kind of training. But of course we would be also happy to host something and have people from abroad also coming and helping. It's a good train connection to Hamburg.
Still asking for more if there's any. Okay, I'm not going to torture you. Let's thank Flavia again. And yeah, we continue with sort of exactly what you asked for. So now you have to ask at least 5 to 6 questions after that talk. So. Freya, I think you're up. I'm not entirely sure why everything is black.
Because it's still being loaded. You get to look at a beautiful CMS picture. So indeed, I want to give you a talk that's mostly intended as a motivator of why you would like to spend time on this. Because people are busy and people already have many jobs. And so the sort of working title of this talk is also is why should I be investing time in outreach and science communication? And I hope to sort of be able to convince you that this is not just for the general public, but that you also gain from it. So I wanted to start with a few motivators of why we do outreach. And also remind you that when you do outreach, you need to be very careful. This is a picture. It's obviously not real. And I can tell you that particularly this picture, that is also obviously not real and part of the same campaign of CMS for Star Wars Day a few years ago, is actually used all the time in conspiracy theories. But this one, I guess the general public can see that it's not real, so that's great. So this talk is about communicating what we do and why you want to spend time on this. And one of the things that I want you to be super aware of, I nowadays spend a substantial fraction of my time I'm a senior professor, so I sit in committees. And I sit on a lot of committees for funding. And I sit on a lot of committees for funding with people from other physics fields and even from other STEM fields. And I can tell you that the majority of our colleagues from outside particle physics also say this. Particle physics has done nothing since the Higgs boson discovery. So just for that reason, just if you care about just getting a grant so that you can work, it's worthwhile doing science communication. And I think that's very, very important to realize. So there are other reasons to do it. Science communication and scientific literacy is a very important contribution to improve the world, if you care about that. To make sure that science in general is supported. For example, I don't know who is following the developments at the moment in the US, where they are cutting essentially all, well, they're telling our colleagues that they're not allowed to work in any international collaboration, and at the same time they're cutting all the science communication budget. So this tells you how these things are sort of related. A lot of the ideas about open science and the very, very broad way we work in our fields, including particularly networks like this, are also based on open science principles. And you can also communicate about that. You don't just need to communicate about your paper. Many of us ended up being scientists because we were inspired at some sort. I sometimes meet people that are postdocs, or actually I met the first person who is staff now even, that went to an outreach talk when I was like a PhD student or so, and they're like, oh, you inspired me. And I never really thought about it like that. But of course this is true, because I was also inspired by people who did this kind of thing. So you're also giving something back to the community when you give these kind of talks, or when you go into the media, or when you work on all different kinds of outreach, because this is the point that I'm hopefully going to try and make in a few slides, is that outreach can be many, many things. Also very important, it can help improve your career in many different aspects. And I don't just mean the fact that you have a little outreach section in your grant proposal. I mean that the skills that you gather from doing science communication also make you a better scientist, make you a better university teacher, and make you write better grants. And I think all of these things are very important, and depending on where you are in the career, you'll know which one is important for you. But this skill set is important, and there's only very few places where you can easily practice it, and it's not like you magically get from zero to being able to explain why your work is interesting. And so doing sort of like low-level outreach is a really great way to sort of practice these skills. One may also say, I want to do this because I want to explain what the scientific method is, just because I see around me, or maybe even some of my friends, I see that the scientific thinking is sort of, science is under pressure there. I totally agree, and it's one of the reasons I do science communication, for example. And this, of course, has been happening for a very long time. When I was in university, back in the Stone Age, one of our professors had a newspaper column every week on Saturday, and this was just a guy who taught first year classical mechanics. So these things have been going on for a very long time. So this is not new. What is new, of course, particularly if you say compare to just after the Higgs discovery, of just when the LHC started up, is that a lot more communication is done not in newspapers but on things like social media. And so that means that you have one extra way to communicate, and this is how you should look at it. It's not the only way to do outreach, it's a way to do outreach. Just like writing scientific articles, talking to school kids, giving talks to retired engineers that all have their own theory and their wife thinks they're very smart. That is, there are many different things you can do. So that is the one thing that changed since the mid-2000s. The other thing that changed is that particle physics is in some sense a victim of its own success. The communication that we did for the Higgs boson was extremely good. To be fair, some other communication we did was not so good. I'm talking about the black hole stories for CERN. So, but even there, if you actually ask people on the street what they know about CERN, they will know about the black holes and they will know about the Higgs particle. And in some sense, maybe that this is a very good example of the effect of the famous PR joke that there's no such thing as bad publicity. I don't know, but you can at least explain that these black holes are obviously not being made and we haven't seen them. So, so we are in a position, compared to, say, the 90s and early 2000s, where people know who we are. They know about our field. They know at least some buzzwords. So this is an advantage. And depending on the country, this means that you can. Some countries are really taking advantage of this as well. And they are really sort of building relationships with all sorts of media channels, not just individual social media channels, but really working on relationships within science communication, within the sort of the journalism world and things like that. And if you ever get to do a real media training, this is what you will learn. Part of the media training is about how to interact with journalists and understanding how they work and they think. Because this is very important. The classical example is if a journalist emails you, you need to reply straight away, because typically they have a deadline for 3 hours from then, and if you don't reply, they'll just pick somebody else. So you need to decide fast, and you already need to have done the media training beforehand. And yes, all this sort of communication is needed. So this is a YouTube window in, well, let's not call it porn mode, but in anonymous mode. So I have turned off YouTube. It does not know who I am. It even does not know my location. And then I type in CERN. And this is what you get, just so it's very clear. Does this work? Yeah. So 80% of this is conspiracy theory. So this is what somebody who's interested in CERN, who knows nothing, what they see when they try to find resources on social media. And some of the work that we try to do for us that actually work on social media is to try to sort of cut through this noise. And there's a lot of noise. And I can also say some of these things are so much better than we could ever do. I have much respect for them as far as the science communication side. Not what they're saying, but they are very good at communicating it. So how do we communicate particle physics? How do we do that? And the spoiler already says there, the best way to communicate anything is to make it personal. So let's first start with some examples of what not to do, because I think that's always the best way. And this is also how I mentor my postdocs. I don't know what to do. It's like, well, why don't you make a list of what you don't want to do, and then you sort of, oh, why is it not? It's an animated GIF. Is it this is the PDF, so the animated GIF does not work. I will link the animated GIF later from the COMETA Indico page, because the animated GIF is very, very good. This one was made by Achintra Yao. They worked during the observation of the Higgs boson as one of the communications interns for CMS, and they made a very nice animated GIF that summarizes what happens when Atlas and CMS start doing their normal editing and start talking to journalists. Exactly, So what happened was, the journalists went to Atlas and CMS, they asked, okay, what happened? And Atlas and CMS start to create this sort of endless scientific sentence about certain scientists discovered the Higgs boson, so Atlas and CMS, no, it's Atlas and CMS collaborations that discovered the Higgs boson, and it's not the Higgs boson, it's a particle that's consistent with the standard model Higgs boson as predicted by, and you completely lost it, to the point that in the end the journalists ignore you, because if you do things like that, and if you interact with journalists the way you interact with your colleagues, they will just ignore you, and then in the end they go like, scientists discovered the gold particle. Yeah. So if you want to get more than that, you need to get to their level, and you need to get rid of all the jargon, and you need to reflect on what your jargon is. Reflecting on what your jargon is very, very difficult, because we are scientists, we use jargon all the time. Jargon is great. It's a very, very effective way to communicate, because otherwise things take way too long. But if people use different words for different things, they will just not understand you. And we don't even realize sometimes what other people do not understand, even other scientists. And if you do a good job, and if you get rid of the jargon, people will understand you, and they will understand also why things are interesting. But you do really need to actually make the effort to do that. So what is very important in that context is to put yourself in somebody else's place. And this is actually true for everyone. and for everything. So I now want to do a little interactive exercise to make sure that everybody is awake. So, so here are some examples of when you communicate, how that changes as a function of a different group. So when you talk and have a discussion in your weekly university group meeting, what is important there when you have when you talk to each other or you give a talk?
Use your hands.
Or just talk.
Or just talk.
I know I'm very scary.
Content itself and the results and the raw essence of it.
Yeah, for those of you who are professors, what is the thing that students mostly do wrong? They forget that you have 20 other students, and they assume that you've been following what they have been doing for the last 2 weeks every second. So give a summary before you start. Also very important. So that is. So another example: if you communicate or if you write a journal paper, is this different than a university meeting? Why? What can you assume that people know versus not know?
Between which two groups, sorry?
Your university group meeting and a journal paper. Let's go for...
These people will not be in your collaboration, so they will not know what you're, I guess.
Exactly, so at least you need to explain the collaboration jargon. Eh? As a fun fact, in CMS at one time we had 3 things called Castor. So even we had our own jargon that we didn't know. So does that change if you submit to Science or Nature or maybe even PRL?
You have to contextualize things properly.
Yeah, why is that?
Because those papers are meant also to be read by people not so close to your community. Then when there are no papers, it's another story. But a priori.
Yeah. Yeah, if only because the editor needs to understand whether it's interesting. So even if you want to be super, super pragmatic, yes. So, but indeed, so I want to make this point, and I picked these examples first because we do this all the time. The only thing is that we don't think of this the same way when we start thinking about science communication. So when you talk to your family, this is exactly what you also need to do. You need to think, what do these people already know? Where are they coming from? And then you communicate in them in such a way. That's also the same if you talk to a journalist for a newspaper. You need to think, what do these people know? What is the audience of the newspaper? What do I want them to learn from this? So this is the most important thing about any time you communicate as a scientist, independent of whether this is in a paper, at a talk here, like the COMETA meeting, or anything like that, is that you need to think, it's not about what I already know, that I know what I know, right? It's about how I get this information to the other person, and what do I want them to learn. So the name for all these groups is stakeholders. So stakeholders is communication science jargon. And the stakeholders for particle physicists can be separated this way, where this pie chart is not proportional, but so this is sort of the idea of everybody that you could in principle be communicating to. And of course, it's different if you communicate to, say, donors to see if you can get another 3 billion for a future collider, than if you communicate within the HEP community. Or it's also different if you want to communicate with the government versus journalists, for example, or other scientists. Like I said, other scientists are also a target audience you should not forget, because other scientists approve our grades and approve our grants. So, so science communication can have many, many, many different aspects, and some of it is also super didactic and useful for physicists amongst each other, and even within the field. So one of the things that I did during my career is that I started up the CMS briefing program. By now, I think 70% of all CMS papers have a summary that's written for the general public. And again, these slides had animations. I forgot to upload a nice PDF. But here you can sort of visualize there. You can visualize that you have a very nice electron going through the CMS tracker and creating Bremsstrahlung photons. And this is actually even closer to this specific action, because this is an explanation using actually just a root plot to explain how EFT fits work. And it's a very nice thing. So I will also upload the animations when I am done after this. But this is a very, very, very good way to explain, even within our field, to sort of get started. And these things are, of course, these things were originally intended for social media. So when you think about stakeholders, you really need to think about both how simple you want to go and and depending on how simple you go, you reach different people, you reach different stakeholders. And here you sort of see a summary of all the different things as far as complexity and as far as how difficult it is to communicate at these people, just to get you some idea. So the communication I do is mostly here on LinkedIn and here on the other social media. CERN communication has moved over the years and is now getting very close to the Cats Are Funny and Taylor Swift is My Hero communication. And I don't think there's anything wrong with that, just so it's very clear. This is also super important to communicate there. And as I said, I think the one thing I want you to get from this message is that any good outreach takes into account who you're communicating to. That's the most important thing. That's where you should always start from. And that means you need to plan. So if you're going to do something, the first thing you do, independent of whether you're going to make a board game, whether you're going to decide a weekly podcast, or whether you're going to talk in a school, the first thing you really need to do is to have a plan and to really think about who you're going to talk to. And this does not need to be fancy, but you at least need to realize, hey, what am I trying to do here? And of course, those plans change, and that's fine. This is not a problem, but when you learn, you will also know and learn from yourself what works and what not, because a lot of this is super individual. It's because, as I said, the connection that you make with these people is sometimes even more important than the actual science that you give. So here's an idea, a sort of a graphic that gives you some idea of how easy things are to do versus how long in advance you should start. So if you have, say, a paper and you want to do communication about it because you, of course, think that your paper is fantastic, and that's your right to think that. And then you need to think, who do I want to communicate to? And depending on that, you need to do different things. And if you really want to go in the direction of, say, press releases or even CERN news, you need to start in time. Practically every university PR department, the CERN PR department, all of the other science communication departments, they all have quite hard deadlines that you need to hand in things very often 3 weeks before. So if you want something to go out, it's important to do that in time. This is particularly important because if you deal with journalists, real journalists, as soon as the result goes out, the clock starts ticking. So for them, a result that you presented at a conference 2 weeks ago is not news, but exactly the same result you presented at the conference today is news. So that means you need to have all the press stuff ready when you present the thing at the conference, just so it's very clear. So that means you should make science communication not an afterthought. This is really important. You need to think in advance. Do I want to do something? How much time do I want to invest? Because if you make it an afterthought, and you are at great risk of the fact that actually the work that you invested is not going to pay off at all. And this can be super frustrating, and of course will also feel like a waste of time, and arguably maybe it was a waste of time. So that is how I want to close. So communicating things and thinking in advance about what you want to do when you have a result should not be an afterthought. And if you do that, the nice thing is your colleagues will also read your paper. There are by now very nice metrics around. So this, for example, is Altmetric, but there's a few where you can actually monitor, and yes, your universities also monitor these. And you can see how much impact your paper had beyond just mere citation. So Altmetric is a metric that keeps track of every time your paper is mentioned on social media, is in a newspaper, or anything like that. And it's really very powerful. If you go to your university, I don't know if the Cost Action keeps track of it as well, but any university website nowadays has Altmetric or something similar that they keep track of as well. So it's not just number of citations. And yes, these numbers are typically, of course, higher than the number of citations. So that's all I wanted to say. I hope this gave you some idea of the sort of basics of science communication. really basics. I strongly suggest that everybody, particularly everybody of a certain career stage, does a media training at least once in their career to sort of learn the basics and to be prepared when the journalists call, because they do call. And at that time, if you don't know what to do, by that time they're going to be gone and they're going to go to somebody else. So that's all I wanted to say. Thank you.
So, any questions? Yes.
All right, I'm going to ask a question I've been wanting to ask since we invited you. All right, going back to things that have changed since the Higgs discovery, and you mentioned social media.
Yeah.
It's not just the proliferation of social media, but the sheer explosion of bot accounts, of more bot accounts. You know, not all social media is the same now. And so my question, and I've been struggling with this with our own social media, is the ecosystem on the modern social media and trying to get beyond the background noise.
Yeah.
Because we are competing now, not just with the bot accounts, but also paid subscriptions, social media influencers, and every combination you can imagine. How do you deal with this?
So I think there's a few aspects to this. I do think that you should give the general public, at least a sort of somewhat educated general public, depending on the country, this changes, a certain level of credit. So I can tell you that one of the reasons I do not bot my, I'm probably some of you know that I make a social media post about every CMS paper that comes out, which also means I read every CMS paper as one of the 4 people in the collaboration that reads every CMS paper. And I on purpose do not bot that. I do bot it in the sense that I queue the post, but that's the only thing I bot about it. That means that if I make typos, they stay in. That means that if it's slightly wrong, I keep it. But the fact that this is a human, people still realize that. This is also why I do not post AI-generated images, for example. So there is a certain level of science literacy there that you can rely on. People know the difference between a bot account and a not-bot account. That does not mean that you're going to reach everyone, but I am not that worried about that. What I'm much more worried about is not reaching people at all because of the noise. So you do need to use some of the same tricks that the bot accounts use. And this is, for example, why I do use scheduling tools. Just so it's very clear, you talked about cron jobs. By now, of course, there are much better tools on the market, and there have been for a while, where you just give it all your text and your images, and then it checks when all your followers are online and it posts them. There's quite a few of them. Many of them are based in the EU. They do not steal your data. We can talk afterwards. So that's
the important one. That's the important
that is very important. And this is also how I do, for example, all the analytics. So I reach with everything together, I reach about 200,000 people per month. And this went from 200,000 people mostly on Twitter to 200,000 people spread out over the 5 platforms. And because I'm using these tools, I can sort of, I know that the number of people I reach is about the same. Now they're just more spread out. And I do communicate different depending on the platform, because the people on LinkedIn are different than the people on Blue Sky, than the people on YouTube, and then the people on TikTok. Yeah.
So the people you reach on different platforms, as I said, are different. So which platform is the most rewarding? Is places like Twitter still worth it, or?
I left Twitter, so for a year, I actually have opinions about you guys still being on Twitter, but I
have opinions on us.
Exactly. So, but it's a very difficult discussion. So I can tell you why I left Twitter.
Yes,
and
please.
maybe then you won't applaud anymore.
Uh-oh.
So I am data-driven. Mm-hmm. And I noticed that with exactly the same thing that I was doing, I went from reaching 200,000 people per month to 2,000 people per month. Mm-hmm. So I will, of course, claim that all of this was completely about principles, but it was, for a very large part, about the fact that the algorithm is just tuned to a level that nobody saw my tweets anymore unless I gave Elon Musk my money, and that wasn't happening. So...
So you did see this, because I was.
Oh, I totally saw it, because I actually I'm doing it. I have been doing this seriously for a long time, so I could see I could see the change in statistics.
It was anecdotal for me, but it's okay. It's validation that you saw this too.
Yeah.
Okay.
So so that is the real reason I left Twitter. That is, and so let me also make it very clear: the reason why I was on Twitter was not to reach the general public. I was on Twitter because the journalists are on Twitter. So I was only there to give opinions about science things, so that I came into the newspaper, and that's what I really cared about.
And thankfully, in the last 6 months, they have genuinely started migrating to Blue Sky quite en masse. So,
but of course, the scientists were already on Blue Sky, and the journalists are just following. So they also need to get this information. This is a two-way system. So that's why they moved. Yeah. I think they're just as pragmatic as me with my statistics.
Good.
That's yeah.
Yeah, I wanted to come back to this infuriating statement or question that we hear about what has happened in particle physics since the Higgs discovery. And I've tried to address it in certain talks and so on, but I'm curious to hear how you think we should communicate around that.
I think that we are too humble about our results. And that does mean that we need to reflect and actually think about why our results are important. If you do, let's do a first observation of triboson production. It's a very good example. Maybe relevant, or diboson, a special diboson measurement, considering this is a network, sure. If you say, yeah, this is a derivative result and it's not very important, then nobody's gonna be interested. But I can tell you, just if you look in the newspaper, what is in there is astronomers measure yet another exoplanet. Is that really so different?
No, I completely agree. But it's still hard, I find, to find a kind of an acceptance of that. Even though we say it, they don't really listen to that, I think.
No, but you should, of course, it's your job to explain why this is important and new. That is your actual job. Yeah.
Yeah, so I think you're very right about what you're saying now, and we are understanding completely our results. And I realized it when I was doing this projection for RCC, for LH high luminance LHC for the diheds, right? Because we say the precision that we get is 26%, and even physicists will tell you, who cares? So the same could be done for RCCEE. If we would find some examples that show how important it is to reduce this precision on the parameters, or we have to find, because there are theories, there are big important results and conclusions that we can take. We just go for precision, for us it's clear, but for the general public no one cares.
Exactly.
But in reality there are big consequences, so we should try to materialize a bit more.
So one of the things I'm planning is to actually do a little retreat with some people who do a lot of science communication, and we're going to just lock ourselves up. We were actually hoping that the CERN press network, the ECPR, like the press officer network of CERN would do it, but we've been asking for talking points for physicists for about 4 years. I actually remember asking for this while wearing a mask at CERN during a workshop between 2 COVID waves, so I can know what it was. And this is super, super important. Also, by the way, I would say in the context of Future Collider, in the context of actually internal communication, because there's a lot of people who don't know why we want to build a...
Also for students,
yes,
right? To get them involved. I saw the difference on students, right? Because when I say, oh, but it's important, you can really say something. For some reason they don't know it, because they don't...
No, because like I said, the joke one of my favorite jokes, that was actually, so our group leader said this. So she did not think it was a joke. I thought it was fantastic. So she said this last week, and she said that she learned more about someone's machine learning thesis, why it was important, from the video they made for our Instagram channel than from the 1.5 hour PhD defense. And that was a senior physicist. So you should definitely not underestimate that, even like when you try to communicate at that level, that also your colleagues get something from it. Because like I will happily admit that if somebody does flavor physics, I have no idea what they're talking about. This is, for me, I might just as well be a layperson. It's a B2 random combination of Greek letters for me, as I always say. So that is this is totally true for everyone, right? You can't know everything, and communicating that way is super important, both in reach or inside the collaboration and outside. And these things sort of flow, and very often you can use things for 2 things or sort of repurpose them.
6, 7 questions, but I will just do one.
I'm here during the coffee break.
So when you showed like all the conspiracy theories, like for me it's quite easy to find arguments to defy those crackpots videos. But the ones I'm more worried about is the particle physics is dead by my book and find the reason why. Because sometimes they have points which I struggle to reply in an efficient way. I would say, okay, this is wrong, but I will take like 7 hours to explain you why. And,
but in some sense, yeah, you need to. So I can tell you, I was recently invited to do an online podcast, which was me versus Sabine Hossenfelder. Oh. And I said no, and not because I don't want to debate Sabine Hossenfelder, but because of who was hosting the podcast. I looked at all the other podcasts, and everything else there was conspiracy theory. And I was like, I do not want to support this. And some of these people, they are very close to the science populist, science denial, conspiracy theory. And sometimes it's very, very important for us to also explain why what we're doing is different. But the way to explain that we're different is not by giving a long answer. It's to still do the work and compress it into the one sound bite, sadly, for you. So that's the work. Because indeed, and I can tell you that what they're really, really good at is the personal link. So there's beautiful communication science about the best way to deal even with like highly radicalized people in sects, in extreme right movement, is to not actually talk about facts, but to talk about feelings. And only once you made the connection, talk about facts. And this is sometimes the way you need to go. Yeah.
We have time for one more.
There was a question there, way in the back.
It disappeared.
Maybe when we want, of course, to be spread this excitement about science with people, and you said we don't want to undersell what we're doing, but how do we balance this with ourselves not becoming populist, sensationalist? Because one reason I think why we undersell it is because we like to be factual, neutral, measured. We don't want to say something wrong accidentally because that also has its own dangers. So how do you balance that?
That is very difficult, and that is why I think people need to do media training as well, and why everybody, because very often you need to learn that when you simplify things, that indeed you will need to simplify. So I will give you an anecdote, which is a fantastic anecdote, and then I'll stop.
That's okay.
When I was organizing the physics briefings for CMS, I got into a huge fight with a team who were, it was the team that was doing the running top mass. So the people that were essentially measuring that the measurement of the top mass, because of the links to perturbation theory, you could say it sort of changes as a function of the energy scale that you measure it at. Very, very interesting results. Super, super difficult to explain. We wanted to explain it as simply as possible. And I told them, you're not allowed to have the word renormalization in your briefing. They got very upset with me. They got so upset that they got emotional and they started to insult me.
Oh, cool.
Yeah, it was fantastic. So they insulted me by saying, this was a postdoc insulting me, a full professor at the university. I might hire them later, of course I didn't, but that's something else. They insulted me by telling me, well, at my university, bachelor students know this, so you must work for a shitty university. I was like, now, I've taught enough first-year bachelor students to know that first-year bachelor students do not know renormalization, and I have a very thick skin. And more or less after that, I just rewrote their briefing without asking. And it did very well. It was released by CERN and everything, and it made lots of newspapers as well. But sometimes this needs to happen. So you do need to give something up. So you cannot communicate at the same level of technicality that we do. And that's also not needed. You do not need to talk about the technical parts. You need to talk about why things are important and how they fit into the big picture.
And with that,
yes,
I think we can thank you.
I do want to say while I sit down one more thing, which is we only talked about really science communication in the sense of communicating your paper. But there's a lot of other kind of outreach, including like making board games, doing things that are more about what generic particle physics is like, and it's also super important. So that's all I wanted to say.
So we thank again. And now I think without the break, we move straight into short talks. No, the break wasn't supposed to be there. It's okay, all is in order. All good? Oh, no, I was literally about to say, who is taking over? Cool.
Yeah, thank you, that was fantastic.
Okay, so we continue with 4 short talks. And the first one is by Clara, who's going to tell us about multi-boson processes in EFTs with on-shell methods.
Thank you. So I'm Clara from the University of Granada, and today I want to talk to you about multi-boson processes in EFTs via on-shell methods, which is a project that I started during a research stay in the University of Padua. Okay, so let's start with a bit of a summary. I first want to convince you that it's still necessary to study the Higgs, which I don't think I have to do for this audience, but okay. Then I will talk a bit about the amplitude techniques that we've used to treat this problem. I'll describe the workflow for this on-shell method that we use, as well as the cases in which we are applying it to. And then I'll specify all of this to a specific process, which is the double Higgs production via W bosons. Okay, so the complete understanding of the actual dynamics of the Higgs boson is still a major question to be addressed in the LHC program. And if we want to solve this problem in a model-independent way, we have to deal with an effective treatment. There are 2 main ways to do this, which are the SMEFT and the HEFT, and they differ specifically on how they treat the Higgs boson. In the SMEFT, as many of you will know, we still treat it as a doublet. Meanwhile, in HEFT, we decouple it from the non-physical ghost of bosons and treat it as a singlet. But how do we tell them apart? How do we know which one of these actual effective field theories is the one that better describes the real dynamics? Well, there's a lot of work on this field using geometric techniques, multi-boson correlation pattern study, and also analytic positivity bounds. But the route we are taking here is related actually to the on-shell bootstrapping program, which I will try to explain a bit now. Okay, amplitude methods represent a change of paradigm in the sense that we move on from a field theory to a particle theory, in the sense that we don't take the degrees of freedom of a particle and embed them inside a field. We just directly deal with these degrees of freedom. And in the sense that we are actually working with reducible representations that actually are these particles. And this actually translates to a method in which we take the S matrix and we apply the basic principles that we want to not violate, such as locality, unitarity, and invariance and their symmetries. And we take a really general expression and bootstrap it. This is really advantageous because, as I said, when we are directly dealing with the degrees of freedom, we don't have redundancies. We get to really compact expressions, and we also have something that is really algorithmically efficient. This can all be achieved using a specific formalism, which is called the spinor-helicity formalism, which basically takes the particles and represents it via spinors. In the case of massless particles, it's really easy. We just need 2, which are the angle and the bracket that you can see there, and they just have to satisfy this equation right here with respect to their momentum. And when we move on to massive, it's a bit more complicated because we have to, saying it easily, let's say, consider that a massive particle is like a sum of 2 massless in a sense. So instead of having 2 spinors, we will have 4, and they again have to satisfy one relation with regard to the momentum. Okay, so how are we going to use this? The method that we are using to distinguish the 2 theories consists of, first we take into account the on-shell amplitude and the EFT amplitude, starting of course at the 3-point level, which is the smallest building block that we have. We match both amplitudes, and then employing a random kinematics generator, we take this equation that has a lot of kinematic variables apart from the on-shell coefficients and the Wilson coefficients, and we move on to a linear equation. Doing this enough times and evaluating enough space points, we can get a linear equation system that we can solve and actually get the actual on-shell coefficient just in terms of the Wilson coefficients. Once we have this information right here, we can plug it in the 4-point functions And then the 4-point on-shell amplitude that in principle would depend both on the 4-point coefficient and the 3-point coefficient, we'll see them also in the example more easily. They will only depend on the 4-point ones and the Wilson coefficients, which is not a problem. And this allows us to just go again and have a recursive procedure. Okay, where do we want to apply this to? We want to apply this in multi-Higgs production processes. And why? Because in Heft, single and multi-Higgs production processes appear at the same order, which means that just to start with, we will expect to have differences in the speed of convergence between the both theories. This was already applied by my collaborators in a paper that came out last year for the case of gluon fusion up to triple Higgs production. And they did observe that once they moved to 5-point processes, there was indeed different orders of convergence speed between the both theories, being Heft more fast in its convergence than Heft. And we now are working into moving on to massive vector fusion. We are considering processes that involve W and Z, also photons, but okay. And it's a bit more involved just because what I said before, the formalism is a bit more cumbersome. And now I want to specify all that I said for just one of the cases that we are working with, which is the double Higgs production via W bosons. Okay, let's start with the on-shell amplitude. As I said before, a 4-point amplitude in general, we have this aspect, this appearance that we have right here. We have first the non-factorizable part, which will be constituted of a sum of non-factorizable modes. In this case, we have 9 non-factorizable modes that are multiplied by a coefficient that will later on be expanded on the Mandelstam variables to achieve all the different orders in the EFT that we want. Apart from that, we have the factorizable part. In this case, we have 3 channels, the ST and U, and we only have to consider 2 different 3-point vertices, and in total, 4 order 3 coefficients. So with this, we see that we have the 9 coefficients here, and then another 4 here, and that's what I was talking about before. This first will be reduced from the 3-point matching, and then we can move on to the 4-point matching. Okay, this is the full result that we have up until now, and I just want to highlight a couple of things. The first thing is that already at the 4-point order, which is different from what my collaborators saw in the previous project, we already see differences in the convergence order. We are seeing coefficients that are generated at order 8 in SMEF, but are already generated at next to leading order in Heft. Also, we did see already the correlations between the on-shell coefficients. We can see that in the coefficients involving 1 longitudinal or 2 longitudinals, we have in the SMEF operator column that there are a lot of them that are generated by the same operator. Meanwhile, in the Heft column, we can see different operators that are actually generating these coefficients. Okay, the question marks that we have here are just contributions that we expect to be generated probably at next to leading order, but by operators that we haven't studied yet. And with this I reach my conclusions. I just wanted to say that unfolding the true nature of the Higgs is still a question that we have to address. And in the effective treatment, this leads to a follow-up question, which is, does MEFT or Heft better describe its nature? And in this work, we are using the on-shell amplitude methods to look for measurable differences between the 2 theories. And we are extending the previous study by also considering external massive vectors. So far, we've already been able, at the 4-point level, to find differences in the speed of convergence and also the correlation effects. But we want to further extend this study to consider both 4-point processes that involve more vectors and also triple Higgs production. So yeah, thank you very much.
So first of all, this was a really nice presentation. I didn't realize you guys were doing the on-shell methods. So I want to ask a technical question on slide 8. Yeah. So I don't think you did anything wrong. It's just I want to know your the perspective of you guys on this. So the end result, when you add up all the diagrams, that's a gauge invariant result. The precise organization, though, depends on the gauge. For example, the unitary gauge, there's no Goldstone goes on. Whereas this exact same calculation, if you were to go into a general arc C gauge or a Heptolf gauge, Feynman gauge, there'd be a Goldstone boson. And in that case, this organization that you're presenting, which I'm sure is correct in this gauge, looks different. The sum is the same, but the intermediate steps is different. Have you guys thought about how to approach this in a general gauge, or do you guys just not have these artifacts because you're immediately doing the bootstrap?
I mean, if you work in the on-shell method, you are never considering this kind of considerations. I mean, there's no gauge present at any point. There's gauge present when you move on to the EFTs. In this point, you do have to choose the gauge. But here it's not even present because gauge means redundance, and in on-shell amplitudes you don't have redundance.
I mean, but your starting point, you're still dealing with the Lagrangian, and you have to gauge.
No, you don't. I'm just dealing with the fact that I have vectors and scalars, but I'm not considering a Lagrangian at any point. I'm just considering the most possible general interaction between these.
Okay. Thank you.
May I quickly follow up? But you said that you have indeed gauge dependence when you're in the EFTs, right? Or did I hear?
Yes.
And why is that? Because for the EFT you have to employ a Lagrangian.
Yes, exactly.
Okay. Perfect.
Any other question? No? Okay, let's thank Clara again. So the next talk will be by Barbara, who's going to tell us about two-loop running effects in the Higgs gluon coupling.
Yes. So thank you for the introduction, and I will be talking about a recent project with Stefano Di Noi and my PhD advisor Ramona Gruber. So this project is done in the Standard Model Effective Field Theory framework. SMEFT is one of the possible effective field theories that you can use to study the effects of heavy new physics particles. And I would just like to remind you how the Lagrangian is constructed. You take the standard model Lagrangian and you add to it a tower of higher dimensional operators O multiplied by dimensionless Wilson coefficient C and suppressed by powers of a heavy scale lambda to guarantee that overall the Lagrangian is dimension 4. Now, the advantage of using SMEFT is that once you compute this part, which is the deviation from the standard model prediction in terms of Wilson coefficients, you actually have to do it once, and then via matching procedure, you can translate bounds on Wilson coefficients to bounds on the UV parameters. So this picture shows one of the ways in which you can use SMEFT to aid an analysis. I will be focusing on this part here in darker purple, which is the running. The one-loop running has actually been known in the literature for a very long time at this point, while the complete two-loop running came out a couple of months after our project and is currently available. So I will be focusing on the specific subset of these two-loop RGs, in particular operators that will run into the effective Higgs-gluon coupling. I would also like to make some small pheno implications, but for the complete ones, I would also like to point out Alejo's talk after mine. So starting from the computation, which is the operator that we want to renormalize, it is the one in the Warsaw basis identified by this notation. It has 2 Higgs bosons and 2 gluons, and in the broken phase, as you can see here, it will lead to a diagram which will directly affect the Higgs boson production via gluon-gluon fusion. This is a new type of diagram, a 3-level contribution. So this diagram, this operator, if you consider weakly interacting and renormalizable theories, is loop generated, as are the operators that run into it at the one loop level. So from a loop counting point of view, we were wondering what happens if we consider the 2-loop running of potentially 3-level generated operators. And to do this, we identified the following set of operators. They belong to the so-called class 3 and class 7, so they can involve either 4 Higgs bosons and 2 derivatives, or 2 Higgs bosons, 1 derivative, and 2 quarks, and they also have the characteristics that they run proportionally to Yukawa coupling squared. For this reason, for the quark operators, we only consider the 3rd generation quarks since they are the ones with the bigger Yukawa couplings. So how do you do the computation? You have to find all the possible 2-loop diagrams which will contribute. We found that in the end, non-trivial contributions for an example of the class 7 operators will be given when you have that one of the Higgs boson in the vertex is external and the other one's connected inside to make the 2-loop diagram. And once you have the 2-loop diagrams and you add all possible counter terms, You can then all plug it into a numerical integrator. So yes, our computation is done numerically to find, in the end, the complete result. So we try to use 2 different methods in order to cross-check internally our results, which are summarized here, and they are in agreement with the complete 2-loop RG paper that came out earlier this year. Our results are the ones shown here in the first 3 lines, and as I was anticipating, they are proportional to Yukawa coupling squared. We also added these 2 rows, which were the results available at the time when we published. Next, I will be moving on to some Fino implications for which we will be making use of these first 3 lines and also the 4th one here. So these are the operators which modify the coupling of the Higgs boson to the quarks. So in the second part, we will be constructing a simplified fit to show the impact of including 2-loop RGs compared to only using the 1-loop ones. And for this, first of all, you need to select an observable. We chose to work with signal strengths for selected Higgs boson decay final states. So for each of these final states here, we've defined the signal strength as a ratio between the production cross-section in the SMEFT and the branching ratio of the Higgs into that selected final state, divided by the same quantities in the standard model. Eventually, you can also rewrite the equation in this manner by explicitly rewriting the definition of branching ratio. You can then go on to the next step, which is finding all the theory predictions for the signal strengths. And for example, here is the expression for the production cross-section of the Higgs boson via gluon-gluon fusion. I also drew some diagrams here below. So this would be the leading standard model contribution mediated by a top loop. This is the new diagram given by the OHG operator. And then there are some further operators which modify vertices that are already present in the standard model. And here is a plot that was taken from an experimental paper from which we took the measurements. Once you have all of these, you can construct your chi-square function. And then depending on whether you put your constraints on the Wilson coefficients, you have a so-called bottom-up approach, or if you go through the further step of matching to specific UV models, you can present results in the top-down approach. So starting from the bottom-up approach, the first thing that you can do is activate 1 Wilson coefficient at the heavy scale and run it down to the experimental scale. And here we report our results, which have the intention of comparing what happens if you only use 1-loop RGs in the yellow, and if you include the 2-loop effects in darker, well, orange, let's call it. Okay. So most of operators don't actually change that much when you include these 2-loop running effects, but the class 7 operators that I was mentioning before actually do show an improvement in the bound. And it can also be seen if you start moving to 2-parameter fits in which you are activating 2 Wilson coefficients and you are running down to the experimental scale. I forgot to mention that to do the running, we use the modified version of RG Solver to actually rewrite these Wilson coefficients at the heavy scale. An alternative is the top-down approach. So for this case, we try to find UV models that generate at the tree level the class 7 operators. And here the situation is not that clear, so it does not seem that there is that much of an improvement. So this is a plot for a model containing these 2 vector-like quarks. In this case, what happens is that once you do the matching to the 1-loop level, you are generating so many further Wilson coefficients compared to the ones that we are studying the running of, that you do not actually see the 2-loop running effects. And so this brings me to my conclusion. So in this project, what we wanted to do was identify, first of all, to compute the 2-loop running effects of a subset of operators into the one generating an effective Higgs-gluon coupling. And then we performed 2 different types of fit to see their impact. From the bottom-up point of view, we found that there are some scenarios in which the situation does improve, whereas for the top-down one, there are so many other operators that a more extensive study is warranted. So thank you for your attention.
Thank you very much. Questions for Barbara? So in the bottom up, you only do 1 at a time?
In the bottom up, we did 1 at a time and 2 at a time. We did more plots than this one. I just chose this one.
Okay.
We also considered the 2 class 3 operators, so the HDH box. In that case, there was not much improvement. They are the one. So we did these two together, and as is already seen in the 1 parameter fit, there was not much improvement even in the 2 parameter fit. And then we also compared HT and HB, which are still class 7 but involving the singlets, and there it was actually even more dramatic than this one, so there was a big improvement, and that was mostly due to the fact that the HT operator does not really enter the formula, it only enters via running. So there was also that difference there.
Okay. Anything else? Okay, thank you very much. Okay, so now we have Alejo who is going to tell us about the importance of the two-loop RGE in the global field.
Excellent. Thank you very much, the organizers, and good afternoon to everyone. And thanks a lot for allowing me to talk about this recent paper with my collaborators Luca Mantani and Pablo Olgoso about the global effects of the two loops RGE. As I guess we've heard quite a lot during this conference, we are in an era of precision measurements to look for new physics. And in this age, the Standard Model effective field theory is a crucial tool, is one of the ideal theoretical frameworks to get through it. And as you might know, the Standard Model effective field theory is valid up to a certain energy scale, the cutoff lambda, which is in principle at the level of the lightest masses of the new particles that we haven't found yet, and therefore we don't really know where this cutoff might be. The question is, what happens within the EFT between the cutoff and the much lower energies at which we can make our measurements, like for example the mass of the Higgs or the set pole mass? What happens is not that the parameters of the EFT remain at the same value, but they evolve in a certain way that is determined by the renormalization procedure and is encoded in what we call the renormalization group equations that, for example, Barbara showed you just before how to compute them. Let me be concrete with one example. Imagine you have some new physics model that at higher energies, at let's say 10 TeV or even higher perhaps, generates these two Wilson coefficients you see here. And then you do a measurement, let's say at the mass of the Higgs or thereabouts. Should you consider only these two Wilson coefficients or many more? The RGE tells you that because of loop effects, like for example through these diagrams, you should consider many more Wilson coefficients because many of them will be activated with a value that is dearly related to the value of the Wilson coefficients you had in the high energies. And the coefficients, the numerical coefficients you can compute via the loop diagrams here in front is what we call sometimes the mixing coefficients or the self-running, in the case the ones that relate the same Wilson coefficient to different energies. The following question is this relevant? Well, one of the main lessons in our field over the last 5 years or so is that yes, this RGE evolution is really relevant to make precise and accurate interpretations of phenomenology at LHC, high luminance LHC, and even more in the future at FCC, EE, or any kind of lepton collider where we have highly precise measurements at very low energies. And here I show you just a selection of some plots of very recent papers where you can see the difference between including RGE or not in bounds to some simple models like here and here, or in bounds to Wilson coefficients at LHC. And the message in all these papers and many more is clear. If you want to do precise interpretations, you should include these RGEs. However, all these results are based on basically what will be the leading term of the RGEs, that is the one that comes from one loop diagrams, which was computed 13 years ago for the Standard Model effective field theory. But it took the community other 12 years, almost 13, to compute this following order, the two-loop RGE. And already Barbara showed you some of the partial results and some of the partial computations that were done between 24 and 25. And only in January of this year, the full two-loop SMEFT RGE was computed by some of our colleagues, Lucas Born, Javier Fortes Martin, and Anders Thomsen, and they released it for everyone to use it. Fortunately, they didn't release only the paper, they also released an implementation of these RGEs in a mathematical notebook that made our life quite much easier. And that's what sparked the curiosity of my colleagues and I, we said, okay, maybe we can try to solve them in a similar way that we use for the one loop, and try to study the finite implications of these two loop corrections of the RGE. So that's what we did. We took this Mathematica notebook with the two loop results. We implemented it into a hacked version of the D6 tool package that it was already published with the one loop RGEs. And we interface it with our favorite global fit package, which is SMEFID. For the details on SMEFID, on how it works and the datasets, I will refer you to Jako's talk tomorrow morning, because we basically use the same datasets and the same fit framework, just with a different implementation of the RGEs. And from there, we study the phenomenology. So let me show you some of our results, starting with basically the mixing matrix, the solution of the RGEs, between 10 TeV and the set pole mass, basically, the set mass. The way of reading this is take one of the Wilson coefficients here in this column, and this row will show you which other Wilson coefficients are generated at the lower energies if you start from 10 TeV. The coloring of each cell tells you how much the mixing coefficient changes between the one loop and the two loop. It's exactly the two loop over one loop mixing ratio. So basically the extreme colors tells you where there is a big change. The very dark colors tells you that the two loop reduces the RGE mixing by around 2 orders of magnitude, and you can see that there are a few of those dots. And the very bright yellow tells you that the two loop increases the RGE mixing by also 2 orders of magnitude, more or less. The gray tells you that there is no mixing between those Wilson coefficients, even at two loops. And the red tells you some mixing coefficients that are 0 at one loop that cannot appear, but are not 0 at two loops. So are one loop zeros broken by the two loop contribution. As you can see, there are a lot of them. In fact, we know that the ones that remain gray are related to our assumptions of the standard model Yukawas, in which we set all the Yukawas to 0 except for the top. Coming back, one last comment around the broken one loop zeros, you can see the shade of red is different. The darker red indicates a higher two loop induced mixing, and there are some of them that are order 10 to the minus 2, 10 to the minus 3, which for a two loop induced mixing is unexpectedly large, or something that took us a bit by surprise. But this is just the numerical analysis of the solution of the RGEs. What's the impact of this on our interpretations of measurements and our searches for new physics? Let's start looking at that. Let's start with individual fits. This means take the high-Lumi LHC projections in blue or the FCC projections in red, turn on only one Wilson coefficient at the higher energies, and see which bounds you get and how they change when you change between one loop and two loop RGEs. We find that the two loop RGE allows you to get around that order 10% improvement in the bounds to some operators, and here I'm highlighting just 2 of them. In this case, one of them is the dimension 6 top Yukawa, and the other is the top chromomagnetic operator here on the left. It's interesting to see this improvement in the top Yukawa, in which we know that the FCC doesn't gain very much with respect to high-Lumi LHC, but you see that there is a gain, and the two-loop RGE helps you to gain a little bit more. But let's go now to the other extreme. Instead of going one operator by one operator, because we know that that is not very realistic, let's go to the extreme case of turning on 61 operators at the same time and trying to fit them all together. These are the results, and now we can see that there are several changes. There are some operators that basically receive contribution from many others because there are many more mixings, and therefore we lose sensitivity to them. This is the case of C5G here, that you can see that in the hashed, that is the two loop, we have a much worse bound than in the one loop. Similar stuff happens for the dimension 6 top Yukawa, and in the 4 heavy quark operators sector that we have here, we have some operators for which we gain sensitivity and some others for which we lose. Finally, we were not happy enough to just do fits on Wilson coefficients, so we took the typical one loop matching tools like a SOLT and Matchmaker EFT. We took vector-like fermions and scalars, we matched them to the SMEF at the one loop level, and we started doing bounds or projected bounds on the UV couplings of some of these models. And here I show you the bounds on quartic UV couplings of heavy scalars matched at one loop level. And here we found that for some UV couplings of some models, it's not for all of them, you have improvements or changes of between 2 and 5% between using one loop or two loop RG. And here you can see it here, because it's the difference between the full colored bar and the hash bar. It's just a small difference. But in most of the cases, the difference between one loop and two loop is not big. In some cases, you have a little gain. But there is one more result hidden in this plot that we found quite interesting, because it's the first time someone does it, as far as we know, which is we're showing, because for example here in the bottom you have the phi model, which is a basic 2 Higgs doublet model, where we have, in this case, we have 4 UV couplings and there are other 2. No, sorry, there is one more that is not showing this plot, but it's in another one, that is the Yukawa to the top, and we feed them all at the same time. And here we are showing that even high luminance LHC can give bounds simultaneously, fitting all at the same time, to couplings that enter via 3-level matching, that is this lambda phi, and couplings that enter only via 1-loop matching, that are all these L, phi, 2, 3, 4. This hadn't been seen before. There were results of if you have 1-loop match couplings, you can bound them, but no one had tested if you could bound it at the same time with good precision, at the same time that a 3-level generated coupling. And that leads me to the conclusion of my talk. I think it's clear that in this precision era, we need this method. We need to include the RGE effects to get precise interpretation of new physics. We provided the first complete solution of the 2-loop SMF-RGE equations. We showed that it has a much richer mixing pattern than in the 1-loop case, and this leads to several percent level effects, both at the level of Wilson coefficients and at the level of UV couplings in several models. And we also showed, as I told you, that future colliders, or even high luminance LHC, so it's relatively short-term future, can bound couplings that enter at 3-level and 1-loop level at the same time. Thank you very much.
Thank you, Alejo. Questions? Yes?
Yeah, thank you for the very nice talk. So can you go back to slide 7, I guess?
Yes.
Yes, so did I understand it correctly that adding the 2-loop RGs in many cases actually leads to worse bounds?
In these global fits with 61 coefficients, yes, that's true.
And maybe you explain, but why is that?
Basically because, the easiest case, the C5G. You have a very few measurements that constrain C5G very well, usually from Higgs physics, no? And Higgs 2 glue and things like that. But the problem is that now, at the low scale, you always have C5G at the low scale. But now you have many more operators that run into C5G. So the C5G at the low scale depends on many operators, many more operators at the high scale, that cannot be constrained anywhere else to a good degree. So basically, the much richer mixing makes that one data point or a few data points, they have to constrain many more operators. And
okay, so adding the few would be even worse then? Or like
could be worse in principle, yes. But it's just an hypothesis. I wouldn't say anything about 3 loops. No one has done RG at 3 loops.
So what is the solution to this? Like,
I would say adding more measurements would be.
So that was exactly where I was going to go with my question. Eventually you'll have more operators than measurements, and that means you get into a degrees of freedom problem, no?
Yeah, hopefully.
How far are we from that?
I would say quite far. If you add, even here, for example, we don't have flavor measurements. So if you have a flavor measurement, you can bound around 100 operators. But at the same time, do we really want to do global fits with more than 100 operators? There is not really a new physical scenario that tells you that you should have 100 degrees of freedom in your model. So probably it's not very well motivated. This is useful still to understand if your data set constrains many directions at the same time, but yeah.
Yeah, René?
Just a comment. It's also a question about
the redundancy on a given differential distribution. Technically, if different operators have use different shapes on observable, you can constrain many parameters with one measurement.
Yeah, one would even say that that's more than 1 degree of freedom because it's big. I would say I would not count that as 1 degree of freedom on the map.
Okay, but then the answer to your question would be I just need more bins.
Well, it depends on the operator, right?
No,
yeah, exactly.
I mean, it just
no, but this becomes important then. I think that's my point. Yeah.
So okay.
So my underlying question was, do we need to measure in a different way to help you constrain these operators better? That's really what I wanted to ask, but I didn't know how to ask it.
We don't know, but for sure it's something worth looking into. Like now that we know that these operators, in principle, yes, could be, but
The more differential you measure, the better.
Of course, but people also need to get their PhDs and need to get grants to do it, so they need to have arguments. So.
Yes, but here, like you have these four top operators. I mean, just give us a differential measurement of 4 tops, right?
It's very difficult to measure 4 tops when you have 2 4 tops.
But as I said, we know that indeed most of the effects come from 4 top or 4 fermions. That at 2 loop they can run into C5G much more strongly than 1 loop. Yeah.
Okay, I don't see anything else, so thank you very much, Aleppo. And the final talk is by Yashar, who is going to tell us about light Z prime resonances in diboson, multi-boson. So, once we get to the slides.
Hi everyone. This is my subject of my talk. This talk is based on the work published 3 years ago, and in collaboration with the Stefano Moretti and Shabantali. And this is my outline. First, I would like to tell you what was our motivation. The main motivation, our main motivation is coming from the atomic anomaly. Maybe you know, in 2016, the people in the atomic experiment, which is a nuclear physics experiment, and shown the anomaly in the internal pair creation of the excited beryllium decay. And in this decay, internal called the IPC. IPC is the most rare channel in the decay. So this channel is the most sensitive to new physics. So they solve in the angular distribution of the IPC, they solve an anomaly here in the angular distribution of the electron and the positron. So they also show that this anomaly can be explained by additional boson around with mass 70 MeV. After this result, they also continue their experiments with different atoms, and the helium and the carbon. Also, the people in the experimental site, particle experiment especially, they modify their instrument to investigate this additional boson, this anomaly. And one of them is Padme in Italy. And last year, also Padme showed that results this is a particle physics experiment, results show their results supporting the anomaly, atomic anomaly. So, of course, one of the most popular candidate for this boson is the vector boson, and we call it as the Z prime, and according to atomic key results, and this boson, vector boson, if we assume the vector boson, this can be contribute the IPC as the vector with the vector coupling and the axial vector coupling through fermion of the Z prime. And we wondered that we use a very simple extension of the standard model with additional U1 called the U1 prime to get an additional Z prime boson. So then, if we assume the Neve gauge coupling, the gauge coupling of the Neve U1 is around the 10 to, if we assume the 10 to minus 4 or 10 to minus 5, also this Neve U1 prime must be broken to give the Z prime mass. So we can get the with the correct region in the parameters, we can get the 70 MeV. This is satisfying the atomic anomaly. And in this model, we have also, of course, the additional Higgs field, and it's a singular Higgs field responsible for the mainly the break the additional U1. So after the electroweak breaking, we will get additional Higgs. In this work, we wonder we can find any connection in the LXC, any signatures in the LXC supporting the atomic anomaly or supporting this kind of the model. So mainly we are getting constraint from the Z prime coupling from the other experiment and showing here. So we have we scanned a parameter region, a low parameter region, by using the spectrum generator. So then, according to atomic anomaly, and of course this result from our scans, we show that the Z prime lifetime is so short, very short. So if we consider any signal in the LXC, we cannot produce, according to this model, we cannot produce any displayed vertex signal. So we need to focus on the decay on the collision point. So if you consider any signature, any search for the Z prime at LXC, we need to think two different kinds of the process. The first one, of course, the Dralian process. The second one is coming from the multi-boson process via the Higgs field, Higgs particles. When we think the first one, Dralian process, yes, we can get the enough large production rate, but if you consider the background, our decay product, especially the Z prime, can only go to electron because that is very light. So if you consider the standard model background, we cannot detect efficiently because of the decay product is too soft. So we need to choose the second one to show. In the second one, we show the two different channels, where one of the standard model like Higgs mediation. According to this channel, we can, without any cut, we can reach up to around the 0.1 femtobarn at the 14 TeV. So if you consider this channel for any discovery, we saw that we need to 500 femtobarn 10 to minus 1, femtobarn minus 1 luminosity for get any 3 sigma excess to show here. If we consider another channel, this is the exotic Higgs mediation channel. We consider here the Higgs mediation, additional Higgs, exotic Higgs mass, smaller than the standard model like Higgs mass. We can see here the standard model background coming from the Z boson. For the lower mass and the larger mass, this region, we can get the enough signal, enough access for the easily. But in the Z boson mass region, the background is so high, so we need to check this region in deeply for the run 3 and the high luminosity LST. If you consider to high luminosity LST side, we need to, if we get the 2.5 sigma significant, we need to 3,000 femtobarn luminosity, maybe after the high luminosity LST. This is the significant result for the run 2. We can see from here the left side I show only the exotic Higgs mediation, and the right side I show the both of Higgs mediation for the 4-lepton final state. And so the significance is so small for the exotic Higgs mediation. Also, this is we have not enough significance for especially for the 95 GeV mass fusion. If you consider to some results, additional Higgs results from the Atlas and CMS around the 95 GeV, this is the region is the most important for also the showing, investigating for the additional Z prime, the process, the channels which include additional Z prime here. Also, this is the significant result from the run through. According, of course, this is the calculation from the. This is for the high luminosity. If we consider to high luminosity LXT, the luminosity, we can get some signal, excess signal around for the exotic Higgs mediation channel around the 2.5 sigma around the 95 GeV mass region. So this is our conclusion, and if we support the atomic anomaly at the LXC, we think that the round 3, of course, but most importantly, high luminosity LXC is the most important to check in the multi-boson, especially multi-boson channel, to investigate, to check in the additional Higgs with the any signature with the dark H boson, I mean the Z prime. Yep. Thank you.
So I have two quick questions. For the coupling to fermions, do you assume that it's generational universal, so the Z prime couples to the electrons the same as the taus, or no?
No, only electron. Z prime can only go to the electron.
Okay. So
because the 17 MeV and it cannot go to any tau on the muon, can only go to the electron.
Okay, so you just assume that it couples only to generation 1.
Mm-hmm.
Okay.
But the background, of course, you know, the electron and muon.
Then relatedly, what is the interpretation with this model of the transition? Is it then during the nuclear transition for the
you mean the atom key?
Yeah.
Right? Yeah.
What is the interpretation for the transition? Is it a excited nuclear state in which the 17 GeV is being radiated from the electron, or is it being radiated from the nucleus?
No.
In your interpretation with this U1. Because you're assuming a U1, whereas the atomic key, it can in principle come from the nucleus or the electron.
Mm-hmm.
But you're interpreting this as coming only from the electron?
Say again, sorry.
You're interpreting that the atomic key,
Mm-hmm.
the results from atomic key is that it's an excited state, and then the electrons are emitting the 17 GeV. Or that it is coming from a mixture of both the electron and the nucleus.
Yeah, according to atomic anomaly, yeah. According to here, this is the expected IPC coming from there. And according to atomic anomaly, they are saying that we have an additional boson here to go to electron and the positron. And they saw in this electron positron angular distribution, they saw an anomaly, and it's shown here.
Sure.
Yes.
Yeah, just that it does couple to.
Coupled to, yeah.
I'm sorry.
It does couple to the nucleus. Yeah.
Okay, so it's being radiated from the nucleus. Okay.
Any other comment or question? So thank you very much, and thanks to all the speakers.
Good, welcome back to the last short talk sessions of the day. And the first one to go is Athri on dye searches in the 2B to tau channel for the C to HDM. You're going to tell us what C stands for, right?
Yeah. So, hello everyone. So, today I'm going to talk about the dye searches for 2B to tau channel for composite 2 Doublet model. So that C stands for the composite one. And the work is in progress with Stefano and one of our master student, Carlion. And it's almost done, so we will submit it very soon. So I'm not going through the motivation of dye searches because there is already 2 presentations, one yesterday and once today, where they already explained why we need dihedral searches. I'll just go in a brief way that definitely we need to know about that lambda coupling in a better way and in a precise way, because that can give us the hint about the electric symmetry breaking structure. It can also help us to probe the BSM scalar sector and the additional BSM sectors, and also the understanding about the nature of electric phase transition in early universe. So far, for the standard model dihedral production is suppressed because of a destructive interference between two major diagram via gluon fusion product for the gluon fusion production of dihedrals. So therefore, I think we should go for any powerful probe, and it can actually give us a powerful probe for new physics, so we should look for it. There are already some analysis in ATLAS and CMS. It's going on in all possible major channels. I'm not going through the details. This is the current bound on kappa lambda. It's already discussed. And today I will mainly focus on 2b2 tau channel. It's just because it's attractive in the way that it have a good balance between the large branching ratio and a manageable background. But again, we definitely have some issues. If we are doing some resonant dihedral searches, then the issue is the after detector simulation, sometimes we lose a lots of information, and also we have large background mainly from ZJJ and TT bar and QCD multijet as well. But now let's talk about what is composite 2x doublet model in a very brief way, as I have a limited time. I can say that it's a very famous well-motivated model which actually give us a well-motivated solution for hierarchy problems. And here the Higgs boson actually arise as a pseudo-Nambu Goldstone bosons from a spontaneous symmetry breaking of a high-level symmetry. And for our case, it is, let's say, like SO6 can break to SO4 and SO2, and then our Higgs boson are the Goldstone boson of that from coming from that symmetry breaking, and then they can get some mass due to the quantum corrections and the other effects. So the good thing is here that we have many additional sources which can actually directly affect our dihedral searches. One is modified Higgs couplings, modified self-interaction, Higgs self-interaction couplings, which also get modified through the scale of compositeness. And then we can also get some additional momentum-dependent Higgs interaction as well, and also we will get some heavy vector-like top partners. So here is our diagram for the whole dihedrals for through gluon fusion. We have additional 8 vector-like top partners. They can actually contribute through those loops. We have additional TT-HH coupling, which is not present in standard model, but here we have that. And also we have an additional CP even non-standard heavy scalar, which also can give us some resonant pattern. So for that we choose a good benchmark point for our analysis, which satisfy so far from all the collider constraints and all the theoretical constraints. Here you can see that actually we are now the ratio of the cross section for dihedrals compared to standard model is 1.5, so we are actually gaining. And here we have a additional Higgs, which is around 1.1 TeV, and we have additional tops which will definitely contribute through loops. And for the signal topology, as I mentioned, that we are looking for 2b2 tau channel, so we are demanding we need at least 2 beta jet and 2 tau jet. And the full simulation have been done through MadCraft, Pythia, and the detect simulation have been done with Delphis. And now let's talk about the background. So for our case, the dominant background is coming from, one is TT bar. So TT bar leptonic and semi-leptonic, both we have to consider. And then another major background is ZJJ. Now for that J, we are considering 5 flavor schemes. So for that J, we have B, and the other jets. So everything is included. So all the possible combination we have took here. And also the QCD multi-jets, we also considered that. And now there are some good observables motivated by the Atlas and CMS searches, and also some other theoretical understanding and models. So one is definitely the invariant mass of 2b2 tau, which can give us the heavy resonant reconstruction. And then definitely invariant mass of BB or tau tau, which if we can reconstruct, they should peak at the Higgs boson mass, near Higgs boson mass. And again, the PT of our B jets and tau jets, because for our case, we have a heavy particle which is decaying to 2 Higgs and additional heavy top loops. So that definitely will boost our final state particles. And for our case, those will be boosted than the normal standard model case. And the other additional parameter, which is called ZJ, that is actually gonna be one of the major parameter for our analysis. And that ZJ is actually indicating the tau polarization information. So it is actually the fraction of our leading pion carrying inside the tau jet. And now, now we are actually going through the analysis, but before that, let's talk about the issue we are facing. So the left-hand side, you can see if we reconstruct that MBB tau tau at parton level, so we can actually see that peak, the heavy Higgs peak. But as we are going to detector level, it's actually spreading out because of smearing effects and all the issues. So definitely we are losing a lot of information here, but let's see. So now I am going to plot the distribution of our major variables for signals and the backgrounds, and it's a normalized distributions. And the left-hand one is the invariant mass of 2b. So you can see for our case, it is actually nearly picking at the Higgs boson mass. And so here we can give a we can do a good job, but definitely for MBB tau tau, it is spreading out. But again, as we have a boost factors through the additional heavy Higgs, definitely we can get a boosted. So if the tail is actually going further than the standard model one, so we are definitely gaining something. And the another variable is again the PT of B1, as we have boosted B jet, so definitely that can be a good variable to eliminate the standard model major backgrounds. And another variable we reconstructed, it's the ratio of MBB and MBB tau tau, and that is actually peaks at very low value for our signals, where it will peak at higher values for our standard model major backgrounds. And another one, that as our B jets are highly boosted, they are definitely very close to each other. That's why the delta between two B jets are very small for our signal, where for normal backgrounds they are on the higher side. And again, you can see the ZJ variable is actually very good. Actually, is one of the major variable to reduce the TT bar background. And the main issue is that for TT bar case, the tau is mainly coming from the W boson decay, and that's why it is kind of like its helicity is already fixed. Kind of, it has to be left-handed because our standard model neutrinos only are left-handed. But for our signal, it's coming from a Higgs decay, so it can have one left-handed, one right-handed. So it is this. So it don't have that particular shape in that way. So it's more flat. So after that, with playing with those variables, we are just making a cart flow strategy to trying to, and our main motivation, if we can find out a region of signal region where we can eliminate most of our backgrounds. And here is the final result of our table. So here you can see those are the number of events we can get for 14 TVLHC at 3000 femtobarn inverse luminosity. And those are the number of events for standard model, our model, and the major standard model backgrounds. And all of those cards actually playing a major role in each of every steps. So, but definitely there are a few which is MBB divided by MBB tau tau. That is actually, I think, card B, which is playing a very major role. And the main thing is the ZJ parameter, you can see after applying the ZG on the last stage with cuts G, we can end up a signal region where we can almost eliminate all of our backgrounds, but we can still survive with few number of signals. And also you can see if it is standard model, then we will end up around 8 number of signals, but if it will kind of a benchmark coming from composite Twix doublet model, we can get around 13. So there are actually significant deviation from standard model if we can analyze in that way. So that's, I think, the motivation behind this work. So we can show that in high luminosity LHC, those kind of searches actually can be a good probe to find if there are this kind of new physics involved or not. And there's my conclusion, and I think I already talked about everything. So yeah.
Any questions or comments for Atri? Yes.
Thanks for the talk. So if you go back, please, to the slide where we have this ZG distribution.
This one?
Yes. So this is, if I understand correctly, a ratio of PT, right?
I'm sorry?
This is the ratio of the PT of the PTs, right?
Yeah.
So I didn't really get how this can help you in distinguishing between.
Okay, so the thing is, usually, the main thing is the parameter usually we talk about in lots of people, you can see it's called PT imbalance inside the tau or everything. So it is like if you have, let's say, a particle is decaying to 2 particles, and so the PT difference between that daughter particles divided by whole PT, which is giving the PT imbalance kind of factor inside that jet, it's actually give the information about the polarization of the decaying particle. So it's like if it is completely left-handed, then actually, so it's kind of, it depends on structure like 1 minus cos square theta, and if it is right-handed, then it's like this, and for right-handed it's like this. And that cos theta at pattern level and I think the cos theta is center of mass frame, when you will translate it to left frame, that's exactly equivalent to that parameter, that PT imbalance, the PT difference between those 2 parameters divided by whole PT. So yeah, there is a lot of paper where people show that how you can translate. So, but if you will translate in the left frame, that is exactly the measure of cos theta in your center of mass frame. So yeah.
Good. Any more questions, comments? If not, let's thank. Oh, sorry, Ray.
Yeah. I had a question at the start of your talk. So, how did you pick your specific model point? Because you had all these sort of not very round numbers for all the Higgs masses.
So like this. Yeah.
So obviously there's an underlying physics motivation there. That's
the thing is we have definitely, this is a bit complicated model. So you have the model parameter space and you integrate out everything at your scale. So it is definitely computationally heavy. But if you scan a lot of benchmark points, and then you have to allow the benchmark point which is actually satisfying all the constraints so far we have from theoretical and the experimental side, we end up with a few good number of points, and that is one of the point where actually we can get the maximum cross section so far we have in the resonant case. But we actually also have non-resonant analysis points as well, which I haven't showed here, but we have those kind of points also where we can gain something. So that was the main motivation to choose this point, but we also have the points like where the heavy Higgs mass is around 800 or something as well.
So maybe a follow-up question, and I don't mean this in any mean way, but does that really mean that the number of significant digits here, particularly like for F, let's pick one, does that mean that the models are excluded when these change beyond these 3 decimals?
No, that's not true.
Okay,
yeah.
Good.
It's just the benchmark I just select. Yeah, I could have just write 796, then also it will not change that much.
Okay. Yeah.
Maybe one useful piece of information for you is that in this model, the standard model like Higgs mass come from the standard model valve.
Okay, so the 125
goes
in and makes these numbers.
Yeah, and all the other Higgses in the model, they guess the mass from the composite scale, which is constrained to be 1 TeV. So that's why you end up from 800 to 1100.
That's the answer. Very nice, thank you. Yeah.
Okay, let's thank Atri again. The next one is my homonymus, I think. On ZH factor implication of 2HDM with electroweak phase transitions.
Perfect. Thanks a lot. So let me start with a quick introduction and motivation for this project. We all know that the standard model is a great success, but we also know that somehow it must be extended because there are some phenomena that cannot be explained within this framework. Just to give a couple of examples, we have dark matter and the baryon asymmetry in the universe. However, most of the collider experiments currently agree within the standard model. But now the question is, what does it mean, current? Well, the present for the moment is LHC, so it's a hadronic collider. And the next step will most likely be a lepton collider, which for the sake of concreteness for this talk, I will assume it to be FCC-EE, but most of the things I'm going to say can be generalized, which will feature less observables if compared to the richness of a hadronic collider, but very precisely measured because of the clean environment it offers. So the question I'd like to try to address in the next 10 minutes is, can a precise measurement of Higgs stratum be the first observable deviations with respect to the standard model? So we see this is actually kind of a pessimistic approach, right? A kind of a pessimistic scenario, because we're assuming that nothing new will come up in the next stages, but only in several decades. So I'll just try to give you the main ideas and I point you to the paper for the full story. So talking about the shortcomings of the standard model, I already mentioned the baryon asymmetry. Let's say what this actually means is trying to address the question of why there's more matter rather than antimatter in the universe. And and this provides us a motivation to investigate a strong first-order electroweak phase transition. Why? Let me try to be a bit more specific on this point. If we start from a symmetric universe, as we assume is the case at the Big Bang, then in order to achieve the observed baryon asymmetry in the universe, we need to meet the three Sakharov conditions, which are B violation, of course, which indeed is present already in the standard model. But to meet the other two, we have to extend the standard model. And these two are the C and CP violation, which is present in the standard model, but not with a strength such to explain the baryon asymmetry that we observe today. And we must be out of the thermal equilibrium. And this is precisely where the strong first-order electroweak phase transition come into play, as also anticipated in the talk this morning by Pamela. So we need to add BSM physics, which in the context of this talk means the 2 Higgs double model, type 1. So the idea is that we supplement the standard model with another Higgs doublet. And this means that the phenomenology changes because we have additional scalars together with the standard model Higgs boson. Now, as already mentioned, collider bounds are mostly compatible within the standard model. And in the language of the 2 Higgs double model, this translates to the so-called alignment limit. So the Higgs have standard model coupling with standard model particles. But even with this assumption, the parameter space is quite large. So we need to somehow focus on the parts of the parameter space that favor a phase transition. And this has been obtained by performing a scan. So the strategy is that we extract a random point for all of these 3 parameters in this bound, and then we check if they satisfy the state-of-the-art theoretic and experimental bounds. If the outcome of this first test is positive, then we check if this parameter point can realize a first-order electroweak phase transition, and we also compute the strength of it to assess if we can call it a strong first-order electroweak phase transition. Then, if also this check has been passed, we finally compute collider implication. And then this brings me to the next slide. So we start from the assumption that we don't see anything before the Higgs stratum measurement. So we shouldn't observe anything at the Z-pole run for FCC. We can see that the constraint on the oblique parameter constrain quite a lot the 2 Higgs parameter space by taking a look on the plot on your left-hand side. While if we look at the plot on the right-hand side, we can see that what I already anticipated you, that we must be somehow in the alignment limit, because we see here this parameter cosine beta minus alpha is close to 0. Now, beta and alpha are parameter of the Lagrangian. We don't need to know them in detail for the moment. Just know that the Higgs coupling with standard model coupling go as the sign of this beta minus alpha, which to be in a standard model-like scenario, we must require that the cosine is close to 0, which is precisely what we see. What else can we learn? Well, we can learn that the points that favor a phase transition but do not provide large deviations at the z-pole run favor small mass splitting between the new exotic scalars, as we can see on the plot on the left-hand side. And we also see that points that favor strong first-order electroweak phase transition favor relatively small mass scale. So these new particles shouldn't be too heavy, as we can see here. But then the question is natural. If these new particles are not so heavy, where are they? Well, if we assume that they are not too heavy, but at least heavy enough to decay into a TT bar final state, then we should be able to track them with direct searches. However, direct searches are potentially affected by interference effect. So, for example, in this case, we could have a creation via gluon fusion of one of these heavy scalars, but then there is all the QCD reducible background. So if we do the computation, then this is the outcome of our results, and we can see that the inclusion of interference effect can actually dump the production cross-section. And the take-home message is that interference effect actually may hide the new scalars at LHC searches. So this finally brings me to Higgs stratum, the second stage, at least based on the current plan for the future collider, future lepton collider. The current predictions, projections for the precision are quite astonishing, I would say, because we would be able to measure this with a precision which is below 0.5%. We have seen, however, that if we don't observe anything else before this measurement, then the constraints on an oblique parameter forces us in the alignment regime of the 2X double model. And if we want also to generate a strong first-order electroweak phase transition, then we must be in the non-decoupling regime. So, once again, the question, is it possible to see deviations only in Higgs stratum? Well, we did a computation, and the answer actually is yes, it's possible. So, parameter points that realize strong first-order electroweak phase transition and are standard model compatible at earlier stages are either potentially detected at FCC if we include the one-loop correction, because we can see here the red points are all above the sensitivity threshold of FCC, while the blue points are below, which are the leading order ones. So if we incorporate the NLO correction, we can actually observe this. And this finally brings me to my conclusions. So we have investigated the collider implication of scenarios that favor a strong first-order electroweak phase transition in a very pessimistic scenario. So we assume that no new physics is observed before the Higgs stratum run. Despite that, most of the points are actually detectable if we assume, like with a precise Higgs stratum measurement. And this stems from two reasons. We have important radiative corrections stemming from these extra degrees of freedom with respect to the standard model, but this is possible only because of the high precision that we can obtain at a lepton collider. Now let me say that this was done for the 2 Higgs double model, but most likely some of these conclusions can be generalized also to other BSM scenarios. And finally, I want to stress once again that our assumptions have been very, very pessimistic, because we have assumed that nothing interesting will come up in the very next decade. So this is maybe too pessimistic. Well, let's hope so. Thanks a lot.
Any questions or comments for Stefano?
Thanks for your talk. With which level of confidence could you say that you can see the FCC? Like how many sigmas do you deviate with respect to the standard model?
Well, more than that, I would say that like we can be optimistic here, because we have been very optimistic with the theory uncertainty. So I don't know if this answers your question, but this sensitivity can be obtained assuming that this is purely experimental. Let's say this precision.
Sure.
Mistaken.
Yeah, no, but my question is like the prediction in the cross section with the true HDM, by how many sigmas does it deviate from with respect to a standard model, no?
Well, it's hard to draw a global picture, right? For that you would maybe need a proper fit. This is just a scan, so we should just take it as an indication somehow.
And the standard model also includes the one loop correction.
Yeah. Both of them, like, yes, this is the deviation with respect to the standard model, both at LO and NLO consistently.
Good.
Yes, please.
Yeah, so I have a remark, and now probably I will formulate it in the wrong way, but I think that one of the problems of the ZH channel, apart from being indirect, is that indeed if there can be very large variation in lambda 3, but that by looking at ZH, this is practically mediated by the strength of the GZ.
Yes.
So it could be that also ZH actually dumps the effects of new physics that instead could be directly visible in Higgs.
Mm-hmm. Yeah. We are actually working on a follow-up precisely on this direction to try to precisely pinpoint which is the handle.
So I want to be negative in what...
No, but you're definitely right. That's a very interesting question. We are trying to address it right now to see precisely what's driving what, and it's harder than expected, actually.
I can imagine.
Okay, let me try to be positive then. I have a question. While playing with BSMPT, have you checked what kind of gravitational waves you get? What is the signal-to-noise ratio, the frequency spectrum? Because some future generation interferometers will come online well before FCC-EE.
I think not for this project, but definitely it's an interesting direction because BSMPT does this natively in the version 3 at least. So not for this project. We didn't investigate the direction, but it's definitely something we could do.
Okay.
Perfect.
Thank you. Thanks, Stefan, again. Then I think we have Alvaro on signature of extended scalar sector with CP violation via group fusion at the ILUMI LHC.
How does this work?
I don't know. There must be a button with an arrow on it.
Okay, this is difficult.
Well, you can point there as well. Yeah. You just step away. Be careful at the step there.
I'll try not to fall down. Okay, hi everyone. I hope you're all holding up well for this second to last talk today. In the following, I shall be presenting preliminary results on which follow in the footsteps of what my dear colleague Rodrigo Capucha presented last year at the COMETA event in Krakow, which tries to tackle a very simple yet at the same time very profound question, if you think of it. Namely, the following question. If the CP violation we so desperately need, for instance, for explaining the barrier symmetry of the universe, happens to be hidden in some extended scalar sector yet to be discovered by us, then is there any straightforward, dare I say economical manner to assess the existence of these sources of CP violation in such extended scalar sectors? Now, the premises for our work are rather straightforward. For those of you that were not at last year's event, or for that matter, for those of you that don't keep up with our production, let me briefly outline them. For the sake of argument, we will assume the existence, or the realization of in nature of some such extended scalar sector. Think of 2x doublet models or the like. And for the sake of argument, again, we will assume knowledge, of at least partial knowledge, of this extended scalar sector. So knowledge of at least one additional exotic scalar, let's call it capital HA, aside, of course, from the knowledge of the 125 GeV boson, with its very good approximation CP even behavior. Now, with these premises, as Rodrigo pointed out last year, if we observe any of the first two processes on the slide, on shell preferably, we have clear and unambiguous signatures of CP violation. And this rests on three realizations. First of all, provided that loop effects are small, couplings of the type HA to two vector bosons suggest, or rather would imply the CP evenness if we start from, let's say, from a place of assuming that CP is a good symmetry. Now, second of this, in any Lorentz invariant renormalizable theory, couplings of the type HA to ZH imply opposite CP assignments to the scalars in the process. That is, either one is CP even and the other is CP odd, or the other way around. Again, assuming, for the sake of argument, that CP were a good symmetry. Now, if we supplement these points with the additional information, additional a priori information of the CP state of one of the scalars, in this case the 125 lowercase h, we can immediately see that either of the first two processes clearly signal that CP cannot be a good symmetry, because we have the vertex on the left-hand side suggesting the intermediate scalar to be CP even, yet the right-hand side of the Feynman diagram suggesting HA has to be CP odd. That is, you cannot make consistent CP assignments to this guy HA, and for that matter also not to the 125 Higgs boson. Now, as you can see, you always need three pieces of information, something like information on two vertices and the information of the would-be CP properties of a third scalar, which is why in principle Lorentz fusion processes on their own, which only provide two such pieces of information, do not allow you to make such statements easily. Yet it would be nice to harness these guys. Ultimately, they tend to come larger cross-section, although this is of course model dependent. But you can always try and observe this process over here and complement this guy with the observation of the pure vector boson fusion or associated production on this side here. And this would constitute what we call a joint signature of CP violation. And this was essentially what we did on our previous work that Rodrigo tried to motivate last year. Namely, we essentially went through all possible instances, well, all possible signature containing at least one instance of either vector boson fusion or vector associated production in generic models with at least one, if not two, exotic scalars. And we built these so-called joint signatures of CP violation. Now, something we realized rather later than we would, that we are, let's say, something we realized later than we're comfortable admitting is that you can entirely forego vector boson fusion or associated production. You can build such signatures out of Lorentz fusion processes alone. Namely, Exhibit A, you can try and generate, always on shell, such intermediate scalars and try to observe their decays both into the HZ final state, which suggests CP oddness of the intermediate scalar, as well as try and observe the decay into the di-Z final state, which suggests CP evenness. Again, it's not possible to make a definite CP assignment to this intermediate scalar. If for some reason you're not a friend of di-Z final states, you can always go for di-Higgs final states, which we have talked a lot about these days. And this works exactly the same. And the good thing is, as I said, although this is model dependent in some sense, these processes will tend to come with larger cross-section. So the name of the game is to try and see if it's possible for any model to observe such joint CP violation signatures. And we wanted to benchmark the LHC. And in order to remain consistent with what we did in our previous work, and in order not to cheat the system in a sense and remain realistic about the amount of CP violations that we can expect, we took one of the more conservative models regarding CP violation on the market, namely the complex Lewis-Studded model. Complex, I say this because I was saying to HDM, not to confuse with the C2HDM that was mentioned in two talks before mine. And, well, this is, as the name suggests, a 2x doublet model that in the Higgs spaces satisfies an approximate C2 symmetry only softly broken by this M12 square term, which is also the place where CP violation starts to creep in, because we will allow this guy to be complex, as well as this lambda-5 quantum coupling over here. which would suggest two independent CP-violating phases, which however collapse down to one as soon as we impose minimization conditions on the potential. So in this sense, it is economical. Furthermore, this model is provides us with up to 3 different scalars that are CP indefinite and can be ordered without loss of generality in this manner, which will give us these 2 input parameters, if you will, 3 input parameters. We will further have this charged Higgs boson over here, and we will have these Euler angles, which are important because these are the guys that diagonalize your mass matrix. And furthermore, we have another important parameter with this, which is the standard of beta, the ratio between the gaps in these spaces over here. And now, the point is, well, further information. I mean, as you all know, Twig's doublet models need to impose, well, they come in different types in order to, here it is. Yeah, in order to avoid, well, essentially flavor violating processes, you essentially impose these different types on, in the sense, in the way how the doublets couple to the different fermions of the field. So the point of pointing out all of this is that all of the parameters I've mentioned before are going to enter the couplings that we're interested in. So essentially the gauge couplings of the Higgses. And the name of the game at this point is to see if we can find sets of parameters or parameter configurations that could be realized in nature, that is, we have to evade all sorts of constraints, yet at the same time that render the CP violating signatures that we're looking for visible, if not now, at least by the end of the high luminosity LHC runtime, which we did with ScanRes. I will not talk much about this, it was also briefly introduced by my predecessor on stage. And, well, as I said, the name of the game is to essentially generate sets of parameters and see if we're able to see them, or if there are prospects of them, these signatures being visible up to the end of the high luminosity LHC runtime. Now, first we start with this plot over here. This is for the type 1 C2HDL. And essentially what I'm plotting here are the production cross-sections, production and decay cross-sections of this intermediate scalar into the ZH final state, or pre-final state, then into leptons and bottom quarks. In 3 different scans. In orange, the points where no EDM constraints have been applied. In blue, where the present strongest electron EDM constraints have been applied. And in cyan, the points which pass even the strongest present electron EDM projections. And we do this for the different configurations where we can, since we can assign the standard modelings to different Higgses in our model. And in red, in the continuous red line here, marks the current limits on the resonant search of the ZH final state. And lots could be said about the projections of these limits, but we had a wonderful talk about this today. And well, for the sake of being mindful of time, I will not delve too much into this. Let me just state that even without taking into account these projections, just remaining up to this naive square root of L extrapolation of the present limits, we're able to capture many points in these first 2 panels, which will become our candidate points, which we now have to project onto the accompanying process, that is the production of this intermediate scalar decaying to 2 Z bosons. Okay? The orange, blue, and cyan points are projected onto this process, and we see that there is no clear structure in these plots, in the sense that the orange, blue, and cyan points are all over the place, but the bottom line is that we have plenty of points that we would expect to be able to see by the end of the runtime of the high luminosity LHC. Let me also briefly state, because this is rather conspicuous, the fact that these plots end at 500 is an artifact of our choice of data. Basically, we are working with the data of our previous work, where we essentially scanned only up to more or less 500 GeV for technical reasons. This will, God willing, be filled out by the end of this project. As I pointed out, if you don't like ZZ final states, you can always go for Dynix final states with limits that are more recent. And ultimately, the conclusions are the same. We're able to capture plenty of points in these regions over here. Now, just for a brief comparison to our previous work, we're working with the same sets of points. So essentially, this provides a good comparison in a sense. But our previous work contains lots of different signatures. I won't delve into all of them. I just say that as a general feature of our previous work, we were very much hampered by these processes for containing vector-associated production, which tend to come with much lower cross-sections in the end. That is, you always have to go to, mostly you have to go to these ultra-optimistic projections to have candidate points, which you then filter through the remaining processes of your signatures. And we don't encounter this problem here because we evade vector-associated production altogether by using just World Fusion signatures. So in this sense, I would say that our results will be more promising, although these are all, of course, very preliminary at this stage. And just to conclude, let me show you some pictures of how this looks like the Latin-specific model, where we're not constrained to the data of our previous work. This is an entirely new scan, and we see that we have artificially cut at 1,000 JeV in our scans. Eventually, this will be filled out to the right, but even here we already see that even applying all kinds of constraints, we're able to capture lots of points, both in the CH final state and in the projection onto of these orange, blue, and cyan points onto the ZZ and HH final state, which I would say looks promising, but again, this is all very preliminary. We hope to get there soon. And with this, I conclude. We hope to complete this picture anytime soon, and I hope this is of interest enough that you keep up to date with this upcoming work. Thank you. Thank you.
Any questions or comments? If not, I have one.
Yes.
How do you separate your hypothesis where you have a CP mixed state from the case in which you have two Higgses with defined CP, one CP even, one CP odd, and they just happen to be degenerate? As you get in many of these models embedding a 2HDM supersymmetric compositeness, if you embed a 2HDM into models of the electroweak scale like compositeness, we've seen it before, as supersymmetry, you get that the capital H and the A are degenerate. So how do you separate your assumption from this one? What you could what you could do is to look at triple product correlations, because this object decay into 4 fermions, whether it's 4 leptons or 2B and 2 leptons. You can measure the charge of all these fermions. From a B jet, you can measure the semitonic decay, so you can define triple product correlators. If they're 0, then it's my hypothesis. If they're not 0, it's your hypothesis.
Yes, of course. I mean,
you should look into that.
Eventually, one has to do that. Of course, that. If I may answer to this.
Yeah.
Of course, that's something you would have to do to rule out your hypothesis. Of course, in some sense, this of course goes against the motivation of the method of having something simple in the sense that you observe some case and voila, you see CP evaluation. But of course, if you want to have solid conclusions, eventually you will have to correlations.
Let's thank Albert again.